Science is made by men, a self-evident fact that is far too often forgotten. Werner Heisenberg.
It is a profound and necessary truth that the deep things in science are not found because they are useful. They are found because it was possible to find them. J. Robert Oppenheimer.
Author's note. To watch the bombers come off the production line at Ford Motor Company's Willow Run was to be awed hour by passing hour with the unbeatable industrial war machine America developed to win World War II. Willow Run opened just 2 months before the attack on Pearl Harbor in 1941. Before America was in the war, but as officials and leaders came to understand that it wouldn't be long before the country was called to combat. It stretched across nearly 7 million square feet, each of which had been carefully organized and custom-built to make bombers with all the precision and speed that Henry Ford's automobile factories were known for. There were 11 major assembly lines and 69 smaller ones, each stage of manufacturing and construction joining together like streams into an ever larger and onrushing river that poured bombers out faster than anyone had ever imagined possible. Throughout the factory floor, it was often women working a prescribed 54-hour week who put together the 300,000 rivets required for each bomber. One of those workers at Willow Run, Rose Will Monroe, would be among the women forever immortalized as Rosie the Riveter. The result of this carefully choreographed industrial ballet was that a new bomber rolled out of the plant every 63 minutes, the start of a long journey to the front lines of Europe and the Pacific. And Willow Run was just one plant making one kind of bomber. All told, the United States manufactured about 50,000 bombers for action in World War II, some 18,000 B-24s, as well as about 12,700 B-17s, nearly 10,000 B-25s, 5,200 B-26s, and toward the war's end, nearly 4,000 B-29s. Those 50,000 planes took to the skies filled with crews of brave and often scared young men. And at home, female Army pilots known as WASPs, dashingly and romantically dressed in leather jackets and scarves that would make them instant fashion icons. The romance, though, mostly existed only in one's imagination. The life expectancy of these air crews in combat was often short. From 1942 onward, their bombs rained down with an almost unending and inescapable ferocity on Axis positions, ships, and equipment, including some 656,400 tons of bombs on Japanese targets in the Pacific, and, with the help of the Royal Air Force, some 2.7 million tons of bombs on Europe. Entire cities, like Dresden and Tokyo, burned in single nights. Many of these aerial angels of death were adorned with playful names, mascots, and painted pinup girls. But in the end, history remembers the name of just 2 of those 50,000 planes, the Enola Gay and Boxcar. We remember those 2 planes not because of how many bombs they dropped, but because of how few. 1 mission each, 1 bomb each, dropped on 2 different cities, 3 days apart, in the final week of the final theater of the war. Those bombs, too, had names now also forever etched in history: Fat Man and Little Boy. Globally, World War II killed upward of 60 million people. The National World War II Museum estimates the toll at 15 million combatants and 45 million civilians. And it was a war filled with horrors that continue to echo across history. The Bataan Death March, the Tokyo firebombings, the siege of Stalingrad, and the 6 million Jewish victims dead in Europe from the Holocaust. But the atomic bombs, weapons that killed 100,000 people faster than a human could react to the flash of the explosion, are not mere history. They announced the beginning of a new post-war atomic era that remains present and threatening to our daily life 8 decades later. The making of those 2 bombs stands as one of humanity's most monumental achievements, a project conducted completely in secrecy under immense time pressure that delivered to the Earth a never-before-seen source of tremendous energy. It was a technology that would transform the politics and geopolitics of our world. As the head of the U.S. science effort Vannevar Bush concluded, "The merging of efforts of science, engineering, technology, industry, labor, finance, and the military brought about the atomic bomb. In scale relative to the scale of its time, the building of the pyramids offers a possible comparison. While World War II was fought in places like Guadalcanal, El Alamein, and Bastogne, in the skies over Britain, Germany, and Japan, and in the seas of the North Atlantic, Midway, and Leyte Gulf, the war was won in factories like Willow Run and in laboratories at Bletchley Park, MIT, Los Alamos, and the University of Chicago, where inventions like radar, the proximity fuse, and the atomic bomb were created, and advances made in meteorology, computers, and physics. Robert Furman, an engineer on the Manhattan Project, reflected decades later, although World War II was a big military operation, with perhaps 11 million men and women in uniform before it was over, it was equally a scientists' and mathematicians' war. It is one of the great ironies of World War II that the weapon that would end the war with Japan was rooted firmly in the rise of the Third Reich. The story of the building of those atomic bombs began long before World War II. As teams of physicists in the US and Europe raced to unlock the secrets of the atom in the 1920s and 1930s. A small group of visionary scientists who understood the massive destructive potential of their discoveries long before any government or military did. It was Hitler's purge and persecution of Jews that led to a flood of refugee talent departing Europe, and specifically a group of groundbreaking physicists who had been busy inventing a new atomic science, decamping for schools in the US, putting them in the right places at the right times to participate in something called the Manhattan Project. Together, they formed perhaps the most talented group of scientists who have ever come together for a single purpose in world history. Having fled fascism and seen its evils up close, many also knew the esteemed scientists, led by the giant Werner Heisenberg, who would be working on the same questions in Nazi Germany, and were terrified by the consequences if Adolf Hitler unlocked the bomb's mysteries first. They woke each day in an all-out fearful race to preserve freedom and democracy. Set on a stage as large as World War II, it's easy to lose sight that all of this, the brutality of war, the puzzle of grand strategy, the mystery of science, the advance of technology, was being lived through the individual lives and experiences of scientists, soldiers, sailors, and civilians. This oral history of the road to the atomic bomb and its first, and thus far only, horrifying use on the cities of Hiroshima and Nagasaki, two cities specially saved by U.S. war planners from earlier bombing missions to better demonstrate the monstrosity of the split atom, is meant to capture that human-level experience. Today, the Manhattan Project stands as instant shorthand for ambition, audacity, and daring. When COVID hit in 2020, U.S. officials immediately turned to the moniker to capture the race to build a vaccine, and more recently there have been calls by Congress for a Manhattan Project-style effort around artificial intelligence, semiconductor chips, and other pressing scientific challenges. And yet what continues to capture our fascination with the Manhattan Project is there has never been an effort like it before or since. There is no doubt that its short 3-year life from 1942 to 1945 forever transformed warfare and the world. As Project Director General Leslie Groves wrote, "There has never been an improvement in weapons comparable in degree and in sudden impact to the atomic bomb. In the case of other developments, such as explosives, the airplane, the tank, long-range artillery, armor-clad warships, submarines, and even rifles, it took years, if not decades and centuries after their first use, for their revolutionary influence upon warfare to be felt. In the case of the atomic bomb, it took only a few hours." The project was indeed every bit as audacious as popular memory now imagines. A crash wartime effort spread across a dozen key locations around the country, with whole new cities and facilities carved out of mountains and deserts to employ hundreds of thousands of people. Scientists and engineers discovering new elements and fundamental rules of the universe, and inventing new technologies in a matter of just weeks and months, in the hope of building a bomb more powerful than any before, out of materials that at the start of the war existed only in microscopic amounts. And all of it, from the cities to the science to the people, classified and cloaked in silence and mysteries so total that the spouses of the key participants only learned the reality of the effort when it was announced on the radio by President Truman on August 6, 1945. Much of the crew of the Enola Gay learned the word atom only as the bomb was being loaded aboard. As its pilot, Colonel Paul W. Tibbets, reflected, the atom bomb was probably the best-kept military secret since a handful of Greek soldiers got inside the gates of Troy in the belly of a wooden horse. This is not meant to be a comprehensive history of the war with Japan, nor a technical explanation of nuclear fission or the atomic bomb. Great books by Stefan Graff, Lansing Lamont, Richard Rhodes, and others have already trod that ground. Nor is it meant to be a detailed character study of the fascinating personalities who assembled under the umbrella of the Manhattan Project. Again, well-trod ground by writers like Kai Bird and Martin J. Sherwin in their magisterial biography of J. Robert Oppenheimer, American Prometheus. I have in certain instances streamlined the nuclear science and the twists and turns engaged in the development of the atomic bombs, skipping over certain tangential experiments, dead ends, cul-de-sacs, and red herrings to focus primarily on the main and ultimately successful projects. The truth about the much-feared German bomb effort is interesting itself. Germany never came close to an atomic weapon, in part because of the raging anti-Semitism that kept the Third Reich from enlisting the help of Jewish scientists. There is a fascinating book to be written, one I've long hoped to do myself, about the U.S. hunt for atomic intelligence in Europe, but it's a story I largely keep outside this book, in the interest of streamlining the story herein. Similarly, the Russian and Japanese efforts to make a working device, neither of which advanced far during the war, also sit outside this book. Instead, this is the story of the daring, square-dancing, pottery-buying, graphite dust-covered, mutton-eating, poker-playing men and women who made the bombs a reality, and the adventurous lives they lived against the backdrop of one of the grandest stages and highest-stakes projects in world history. Many of these events unfolded simultaneously or near simultaneously across the 1930s and 40s. But in order to keep the narrative straight, I have generally tended to keep geographic or thematic comments together as these parallel stories unfurl. To assemble this oral history, I mined more than 100 books and dozens of archives on multiple continents that contain thousands of personal memories. Altogether, the preliminary draft stretched to more than 1.4 million words of quotations, reports, testimony, and first-hand accounts, ranging from large-scale oral history projects, science memoirs, Nobel Prize lectures, and recollections from military reunions, to government reports and letters from bomb survivors in Hiroshima and Nagasaki, as well as the 1,000-page transcript of the Atomic Energy Commission's infamous 1954 security hearing focused on J. Robert Oppenheimer. Despite the 80-year remove from the events that follow, parts of the story continue to emerge. Sections of the Oppenheimer hearing were only declassified finally in 2014, and the first news reports from Nagasaki by American journalist George Weller, lost to history for decades, were only uncovered in the early 2000s. Unlike any other oral history project I've done, not all of the testimonies herein were given voluntarily. As one witness in the Oppenheimer hearing noted, "I would like the record to show that I am appearing here by military orders and not on my own volition." Throughout, I have edited quotations and memories for clarity and concision, clarifying antecedents and fixing verb tenses, standardized and westernized spelling and names, and clarified certain misremembered details for historical accuracy. A full guide to the quote sourcing is included at the back of the printed book, allowing interested readers to understand how I've woven together the roughly 500 voices included here into a grand symphony to tell a fresh story of the Manhattan Project and the end of the war with Japan. Many of the underlying sources and first-person memoirs that I've drawn upon are wonderful and fascinating reads on their own, although most are long out of print. But taken together, their memories create a vast tapestry larger and more all-encompassing than any one of the first-person testimonies could witness at the time on their own, and, in this new context, even richer in their implications. For the most part, I've chosen to identify individuals by the name and position they held during the period they're discussing. However, I have generally not provided specific titles and affiliations for the few dozen core scientists of the Manhattan Project that you will come to know here. They shifted repeatedly and often in short order during the course of the multi-decade story, flipping from one university to another 1 year to the next, and in the war, from one lab to another, depending even on the month. Similarly, among the military, wartime promotions or unit transfers were frequent, and for some figures like Colonel Tibbets and other members of the B-29 crews of that 509th Composite Group, I've generally chosen the rank they held at the time of the bombings in August 1945 for consistency in identification. For most workers in the sprawling Manhattan Project labs and factories, I've generally identified them by occupation rather than precise hierarchy or job title. Pregnant throughout this book is the debate that the US, Japan, the world, historians, and military strategists remain locked in today. A debate that will never be fully settled about the morality and necessity of the use of the atomic bombs and the total war that engulfed the Pacific in the final months of the conflict in 1945. Was Japan ready to surrender soon anyway? Was the second bomb used on Nagasaki necessary at all? Did the atomic bombs save more lives than they took in the cold calculation of war? And if so, does that make their use against large civilian populations any more acceptable? How much of the US calculus on using the bomb was less about Japan than about Russia and the coming conflict of the Cold War? Of course, by the time the atom bomb arrived, the war in Europe was over, but the conclusion of the war with Japan appeared still distant. Since 1942, the US and its allies had marched steadily up the islands of the Pacific, drawing ever closer to Japan, reversing its imperial ambitions and dismantling its fearsome navy one battle, one torpedo, and one bomb at a time. Every inch of scores of Pacific islands, with names like Tarawa, Peleliu, Iwo Jima, and Okinawa, now forever evocative of heroism, was paid for in American blood. It's easy to forget how costly those final stages of the Pacific campaign were, and how, in the summer of 1945, the war appeared as if it would stretch not just weeks or months, but a year or more ahead. In fact, during just the first 3 months of Harry Truman's presidency, the U.S. suffered roughly half the casualties that it had in the Pacific since Pearl Harbor. The cost of the war in Japan was no less. Entire cities were being burned in single fiery bombing missions, and as the U.S. naval blockade tightened on a country that imported vast energy and food resources, some 200,000 Japanese civilians were starving to death each month. World War II was a conflict that shattered the lines of morality and the traditional divides in warfare between civilians and combatants. As James D. Hornfischer, one of the premier modern scholars of the conflict, wrote, "The question of morality in warfare is vexing. Is there a moral way to kill someone? Is a bullet preferable to starvation? Starvation to incineration?" The ebb and flow of that debate surely has influenced some of the memories captured by the participants over the years. Many of the memories of the 509th Composite Group, the Army Air Force unit that delivered the bombs to Japan, and others were gathered after history took a strong turn against the bombing in the 1980s and 1990s, and controversy erupted over the display of the Enola Gay at the Smithsonian Institution. We will, as a society, surely never satisfy the what-ifs and could-have-beens, though recent scholarship by historians like Evan Thomas in his book Road to Surrender have made a convincing case that hardliners in the Japanese government were not anywhere close to surrender, even after the second bomb. In fact, a military coup unfolded in the Imperial Palace the night before the surrender was announced, with troops rushing unsuccessfully to uncover and destroy the Emperor's recorded announcement. Regardless of the ultimate moral calculation to use atomic weapons, the result of those twin bombings in August 1945 was so horrific that the world has sought to avoid ever using these terrible weapons again. Even so, the US, the Soviet Union, and a dozen other countries pursued building tens of thousands of weapons, many times more powerful than those dropped on Japan. Today, several thousand nuclear weapons remain on constant alert, hidden in missile silos and submarines beneath the ocean, ready to annihilate most life on our planet in 30 minutes or fewer, at the personal order of the US or Russian president. 80 years into the nuclear age, there is still no check or balance, nor second opinion necessary to issue this world-ending order by these two presidents. Any study of modern post-war history makes clear that we have avoided global nuclear war since, as much by luck as by skill. The bombings of Hiroshima and Nagasaki now belong almost entirely to history. Captain Charles D. Don Albury, the last surviving crew member to see both bombings, died in May 2009. But the quest to ensure our world's safety and remove these awful weapons from our planet continues to this day. A quest particularly inspired and driven by the survivors of the bombings in Hiroshima and Nagasaki, known as the Hibakusha. In 2024, Nihon Hidankyo, the Japan Confederation of A and H bomb survivors organizations, won the Nobel Peace Prize for their ongoing work to ensure that they are the last to suffer the consequences of an atomic or thermonuclear bomb. On August 12th, 3 days after the second atomic bomb was dropped on Nagasaki, while all of the Pacific Theater waited anxiously for word that Japan was prepared to finally surrender, a B-29 radio operator named Richard Nelson sat down on the lush Marianas Island of Tinian to write his parents. He had an update he wanted to share. We finally named our airplane. Colonel Tibbets named it after his mother. It is called Enola Gay. Then he added a second thought before signing his letter, All my love, Rich. Perhaps, he wrote, by the time this gets there, you will have also heard of our ship. Indeed, by the time the letter arrived in Los Angeles, California, they had. And it's a name, one of two, that the world will never forget, even long after the last witnesses of that day pass.
Forward. Dawn at Trinity.
Laura Fermi, spouse of physicist Enrico Fermi. Early in July, men had started to disappear from the mesa, and the word Trinity had floated with insistence in the air. By July 15th, nobody who was anybody was left in Los Alamos, wives accepted, of course.
Otto R. Frisch, physicist, British delegation to the Manhattan Project. We all went in cars and buses to the test site, codenamed Trinity, in the desert near Alamogordo, also known as El Jornado del Muerte, Spanish for the Journey of Death.
William L. Lawrence, reporter, The New York Times. I had been with the atomic bomb project a little over 2 months. I had visited all the secret plants, which at that time no one mentioned by name. Oak Ridge, Hanford, Los Alamos, the Martian laboratories at Columbia, Chicago, and California universities. I had seen things no human eye had ever seen before, things that no one had ever thought possible. I had watched men work with heaps of uranium-235 and plutonium great enough to blow any city off the map. I had prepared scores of reports on what I had seen, every one of them marked top secret and locked in a special top secret safe.
Lawrence, a science writer at the Times, was recruited in the spring of 1945 by the Manhattan Project to write the official announcements and press releases about the creation of the atomic bomb. He spent the summer of 1945 on loan to the Manhattan Project, then returned to the Times.
Otto R. Frisch. A steel tower about 100 feet tall had been constructed to carry the explosive device. When it finally arrived and was being hoisted to the top, I was standing there with George Kistyakovsky, our top expert on explosives, at the bottom of the tower. How far, I asked him, do we have to be for safety in case it went off? Oh, he said, probably about 10 miles. So, on that case, I said, we might as well stay and watch the fun.
William L. Lawrence. The bomb was set on a structural steel tower 100 feet high. 10 miles away to the southwest was the base camp. This was HQ for the Scientific High Command, of which Professor Kenneth T. Bainbridge of Harvard University was field commander. Here were erected barracks to serve as living quarters for the scientists, a mess hall, a commissary, a post exchange, and other buildings. Here the vanguard of the atomists, headed by Professor J.R. Oppenheimer of the University of California, scientific director of the Atomic Bomb Project, lived like soldiers at the front, supervising the enormously complicated details involved in the epic-making tests. Here early that Sunday afternoon had gathered Major General Leslie R. Groves, Commander-in-Chief of the Atomic Bomb Project, Brigadier General T.F. Farrell, hero of World War I, General Groves' deputy, Professor Enrico Fermi, Nobel Prize winner and one of the leaders in the project, President James Bryant Conant of Harvard, Dr. Vannevar Bush, Director of the Office of Scientific Research and Development, Dean Richard C. Tolman of the California Institute of Technology, Professor R.F. Bacher of Cornell, Colonel Stafford L. Warren, University of Rochester radiologist, and about 150 other leaders in the atomic bomb program.
Major General Leslie Groves, Director, Manhattan Project. After arriving at the Alamogordo Base Camp on July 15th, a brief review of the situation with Oppenheimer revealed that we might be in trouble. The bomb had been assembled and placed at the top of its 100-foot-high steel tower, but the weather was distinctly unfavorable.
Kenneth T. Bainbridge, Director, Trinity Test Site. The weather prognosis was poor.
Major General Leslie Groves. The weather that evening was quite blustery and misty with some rain.
William L. Lawrence. Base camp was a dry, abandoned reservoir, about 500 feet square, surrounded by a mound of earth about 8 feet high. Within this mound, bulldozers dug a series of slit trenches, each about 3 feet deep, 7 feet wide, and 25 feet long. 3 other posts had been established, south, north, and west of zero, each at a distance of 10,000 yards. These were known, respectively, as S-10, N-10, and W-10. Here the shelters were much more elaborate. Wooden structures, their walls reinforced by cement, buried under a massive layer of earth. S-10 was the control center. Here, Professor Oppenheimer, as scientific commander-in-chief, and his field commander, Professor Bainbridge, issued orders and synchronized the activities of the other sites.
Major General Leslie Groves. There was an air of excitement at the camp that I did not like, for this was a time when calm deliberation was most essential. Many of Oppenheimer's advisors at the base camp were urging that the test be postponed for at least 24 hours. I felt that no sound decision could ever be reached amidst such confusion, so I took Oppenheimer into an office that had been set up for him in the base camp, where we could discuss matters quietly and calmly.
Edward Teller, theoretical physicist, Los Alamos lab. Rain. In the desert in July.
Major General Leslie Groves. I had become a bit annoyed with Fermi when he suddenly offered to take wagers from his fellow scientists on whether or not the bomb would ignite the atmosphere, and if so, whether it would merely destroy New Mexico or destroy the world. He had also said that after all, it wouldn't make any difference whether the bomb went off or not, because it would still have been a worthwhile scientific experiment. For if it did fail to go off, we would have proved that an atomic explosion was not possible. Afterward, I realized that his talk had served to smooth down the frayed nerves and ease the tension of the people at the base camp, and I have always thought that this was his conscious purpose. Certainly, he himself showed no signs of tension that I could see.
Kenneth T. Bainbridge. The first possible time for the detonation of the real bomb had been set for 2 a.m. July 16th, and the arming party was scheduled to arrive at Point Zero, the tower supporting the bomb, before 11 p.m. July 15th. At that hour, Don Hornig would connect the cables to the bomb and detach the detonating unit used in rehearsals.
Berlin Brixner, optical engineer and photographer, Los Alamos lab. July 16th, 1945 came.
Major General Leslie Groves. Oppenheimer and I agreed to meet again at 1 a.m. and to review the situation then. I urged Oppenheimer to go to bed and to get some sleep, or at least to take a rest, and I set the example by doing so myself. Oppenheimer did not accept my advice and remained awake. I imagine constantly worrying.
Boyce McDaniel, physicist, Los Alamos lab. When I heard of the delay, I went back to the barracks to try to catch a little nap. That was a fruitless endeavor. To sleep during the excitement was impossible. I finally arose and went outside to check on the weather. It was still drizzly and overcast. I could hear one of the observation planes above the clouds trying to locate the site.
Brigadier General Thomas F. Farrell, Chief of Field Operations, Manhattan Project. For some hectic 2 hours preceding the blast, General Groves stayed with the director, walking with him and steadying his tense excitement. Every time the director would be about to explode because of some untoward happening, General Groves would take him off and walk with him in the rain, counseling with him, and reassuring him that everything would be all right.
Major General Leslie Groves. About 1 a.m., Oppenheimer and I went over the situation again and decided to leave the base camp, which was 10 miles from the bomb, and go up to the control dugout, which was about 5 miles away.
Brigadier General Thomas F. Farrell. The scene inside the shelter was dramatic beyond words. In and around the shelter were some 20-odd people concerned with last-minute arrangements prior to firing the shot. The shelter was cluttered with a great variety of instruments and radios.
Kenneth T. Bainbridge. When the time came to go to Point Zero, I drove Joe McKibben and Kishtakovsky in my car. I had selected them to be in the arming party. On the way in, I stopped at S10 and locked the main sequence timing switches. Pocketing the key, I returned to the car and continued to Point Zero.
Major General Leslie Groves. While the weather did not improve appreciably, neither did it worsen. It was cloudy with light rain and high humidity. Very few stars were visible. Every 5 or 10 minutes, Oppenheimer and I would leave the dugout and go outside and discuss the weather. I was devoting myself during this period to shielding Oppenheimer from the excitement swirling about us so that he could consider the situation as calmly as possible. For the decisions to be taken had to be governed largely by his appraisal of the technical factors involved.
Berlin Brixner. By 3 a.m., we were at our camera stations preparing to photograph the explosion.
Major General Leslie Groves. As the hour approached, we had to postpone the test. First for an hour, and then later for 30 minutes more, so that the explosion was actually 3½ hours behind the original schedule.
Edward Teller. The night seemed long and became even longer when the test was postponed.
Major General Leslie Groves. I was extremely anxious to have the test carried off on schedule. Every day's delay in the test might well mean the delay of a day in ending the war.
Kenneth T. Bainbridge. Finally, just before 4:45 a.m., Chief Meteorologist Jack Hubbard gave me a complete weather report and a prediction that at 5:30 a.m., the weather at Point Zero would be possible but not ideal. I called Oppenheimer and General Farrell to get their agreement that 5:30 a.m. would be T=0.
Rudolph Piles, physicist, British mission to the Manhattan Project. Finally, the news came through that the test would proceed.
Berlin Brixner. By 5 o'clock, the weather was clearing, and shortly thereafter the countdown started.
Otto A. Frisch. Now it would be only minutes before the explosion took place.
Major General Leslie Groves. Once the decision was made to go ahead, no additional orders were needed. At 30 minutes before the 0 hour, the 5 men who had been guarding the bomb to make certain that no one tampered with it left their point of observation at the foot of the tower.
Kenneth T. Bainbridge. After turning on the lights, I returned to my car and drove to S10, arriving about 5 a.m. I unlocked the master switches, and McKibben started the timing sequence at minus 20 minutes, 5:09:45 a.m. At minus 45 seconds, a more precise automatic timer took over. At the final seconds, another circuit sent out electronically timed signals for the still more precise pulses needed by many special instruments.
Major General Leslie Groves. Leaving Oppenheimer at the dugout, I returned to the base camp.
William L. Lawrence. At our observation post on Campania Hill, the atmosphere had grown tenser as the 0 hour approached. We had spent the first part of our stay eating an early morning picnic breakfast that we had taken along with us. It had grown cold in the desert, and many of us, lightly clad, shivered. We knew there were 2 specially equipped B-29 superfortresses high overhead to make observations and recordings in the upper atmosphere, but we could neither see nor hear them.
Otto A. Frisch. We sat around through the night, waiting for the weather to clear up. For some hours, I dozed in the car, waking up whenever the loudspeaker said something. In between, it was playing dance music.
Major General Leslie Groves. Our preparations were simple. Everyone was told to lie face down on the ground, with his feet toward the blast, to close his eyes, and to cover his eyes with his hands as the countdown approached 0. As soon as they became aware of the flash, they could turn over and sit or stand up, covering their eyes with the smoked glass with which each had been supplied.
Rudolph Piles. We had been given pieces of dark glass through which to look at the spectacle.
Boyce McDaniel. Finally, at T-minus 10 minutes, all of us at the base site crouched on the ground behind an earthen barricade, watching the light glowing on top of the tower.
Otto R. Frisch. The very first trace of dawn was in the sky.
Edward Teller. Just a shade of pink had appeared.
Brigadier General Thomas F. Farrell. As the time interval grew smaller and changed from minutes to seconds, the tension increased by leaps and bounds. We were reaching into the unknown, and we did not know what might come of it.
Joseph L. McKibben, Group Leader, Manhattan Project. Sam Allison was the announcer on the radio and gave the countdown. He had a wonderfully senatorial voice. When I turned on the automatic timer at minus 45 seconds, a bell chimed every second to assist in the countdown.
Berlin Brixner. I removed the waterproof covers from the Mitchell and other cameras on the roof of my bunker, sat down behind the Mitchell, and listened on the intercom to the countdown from the timing station at S10. I shivered, partly from thoughts about the expected explosion, and partly from the wet, cold desert air. Then, at minus 30 seconds, the cameras began to run.
Major General Leslie Groves. The quiet grew more intense. I myself was on the ground between Bush and Conant.
Val L. Fitch, Technician, Special Engineer Detachment, Los Alamos. About half a minute before the scheduled moment of detonation, my boss, Ernest Titterton, a member of the British mission to Los Alamos, suggested that since there was nothing more for me to do, I might as well go outside the bunker to get a good view. This I did, taking with me the 2x4-inch piece of nearly opaque glass which someone had handed me earlier.
Edward Teller. We all were lying on the ground, supposedly with our backs turned to the explosion. But I had decided to disobey that instruction and instead looked straight at the bomb. I was wearing the welder's glasses that we had been given so that the light from the bomb would not damage our eyes. But because I wanted to face the explosion, I had decided to add some extra protection. I put on dark glasses under the welder's glasses, rubbed some ointment on my face to prevent sunburn from the radiation, and pulled on thick gloves to press the welding glasses to my face to prevent light from entering at the sides.
Boyce McDaniel. I remember thinking, this is a very dramatic moment. I must concentrate on it so that I can remember it. I looked around me at the leaders of the program and at my friends. I remember especially II Robbie, Fermi, and Bacher, each staring intently into the darkness.
William L. Lawrence. Suddenly, at 5:29:50, as we stood huddled around our radio, we heard a voice ringing through the darkness, sounding as though it had come from above the clouds. 0 minus 10 seconds. A green flare flashed out through the clouds, descended slowly, opened, grew dim, and vanished into the darkness.
Otto R. Frisch. I sat on the ground in case the explosion blew me over, plugged my ears with my fingers, and looked in the direction away from the explosion as I listened to the end of the count.
Edward Teller. We all listened anxiously as the broadcast of the final countdown started. But for whatever reason, the transmission ended at minus 5 seconds.
Brigadier General Thomas F. Farrell. Dr. Oppenheimer, on whom had rested a very heavy burden, grew tenser as the last seconds ticked off. He scarcely breathed.
Major General Leslie Groves. As I lay there in the final seconds, I thought only of what I would do if, when the countdown got to 0, nothing happened.
Kenneth T. Bainbridge. My personal nightmare was knowing that if the bomb didn't go off or hang fired, I, as head of the test, would have to go to the tower first and seek to find out what had gone wrong.
Edward Teller. For the last 5 seconds, we all lay there, quietly waiting for what seemed an eternity.
Otto R. Frisch. 5.
J. Robert Oppenheimer, Director, Los Alamos Lab. Years of hard and loyal work culminated on July 16th, 1945.
Otto R. Frisch. 4.
George B. Kistchakowski, Director, X Division, Explosives, Los Alamos Lab. The Trinity test was the climax of our work.
Otto R. Frisch. 3.
William L. Lawrence. Silence reigned over the desert.
Otto R. Frisch. 2.
Rudolf Piles. The big moment came.
Part 1. Exploring the Atom. 51 BC to 1941. Particles unseen. The journey toward the atomic bomb dates back nearly as far as recorded science, as ancient thinkers strove to understand the building blocks and rules of the world around us. That our world was made of tiny particles was posited in ancient Greece, when the philosopher Democritus first came to believe that the world was made of atoms. His moniker comes from the Greek word atomos, which means uncuttable or indivisible. Nothing, he imagined, could be smaller. The quest to understand atoms would unfurl for centuries and generations after, and only really take off at the start of the 20th century. In fact, nearly all of modern physics, from the theory of relativity to quantum physics, has unfolded in just about a single human lifetime.
Albert Einstein. In the beginning, if there was such a thing, God created Newton's laws of motion together with the necessary masses and forces. This is all. Everything beyond this follows from the development of appropriate mathematical methods by means of deduction.
Lucretius, Roman philosopher. Besides, the clothes hung out along the shore, wherein they take the clinging moisture, prove that nature lifts from over all the sea unnumbered particles. When tiny salt eats into great sea cliffs, you cannot see the process of the loss at any given moment. Nature's work is done by means of particles unseen.
Diogenes Laertius, Greek biographer, writing circa AD 225. Democritus's opinions are these. The first principles of the universe are atoms and empty space. Everything else is merely thought to exist.
Sir Isaac Newton, English physicist, writing in 1704. All these things being considered, it seems probable to me that God in the beginning formed matter in solid, massy, hard, impenetrable, movable particles, of such sizes and figures, and with such other properties, and in such proportion to space, as most conduced to the end for which he formed them. And these primitive particles, being solids, are incomparably harder than any porous bodies compounded of them, even so very hard as never to wear or break in pieces, no ordinary power being able to divide what God himself made one in the first creation.
Ruggero Giuseppe Boscovich, Italian physicist, writing in 1764. If the matter is worked back to the genuine and simplest natural principles, it will be found that everything depends on the composition of the forces with which the particles of matter act upon one another. And from these very forces, as a matter of fact, all phenomena of nature take their origin.
John Dalton, English chemist and physicist, writing in 1810. Matter, though divisible in an extreme degree, is nevertheless not infinitely divisible. That is, there must be some point beyond which we cannot go in the division of matter. I have chosen the word atom to signify these ultimate particles in preference to particle, molecule, or any other diminutive term, because I conceive it is much more expressive. It includes in itself the notion of indivisible.
Lisa Meitner. Though I may try to tell you something of the development of physics since the beginning of the 20th century, I naturally cannot give you a connected or comprehensive report. I can only pick out a few things which I especially remember, and which form, as it were, a magic musical accompaniment to my life.
Otto R. Frisch. Incredible though it may seem, at the turn of the century, many respectable scientists did not believe in atoms.
C.P. Snow. Modern physics began with the discovery of the particles of which atoms are made. First electrons, then protons and neutrons. These discoveries began to be made in the last years of the 19th century. Emilio Segre. In 1895, a German physicist, Wilhelm Röntgen, found that cathode rays produce a type of radiation when they hit a solid object. He called them X-rays, X for unknown, for these highly penetrating rays were unlike anything then known.
Wilhelm Röntgen. Of what nature the rays are is not entirely clear to me. I had not spoken to anyone about my work. To my wife, I mentioned merely that I was doing something of which people, when they found out about it, would say, "Die Röntgen ist wohl verrückt geworden. Röntgen has really gone crazy." I mailed the preliminary paper, and then the devil was to pay.
Emilio Segre. His paper was unbelievable, but with it he also sent X-ray photographs of hands, which provided evidence that could not easily be dismissed. Upon reading Röntgen's paper, many scientists ran to their laboratories, brought out their spark coils, and set about finding out whether they could see the X-rays. They did. By January 1896, news of the discovery of X-rays had created a tremendous commotion all over the world. In 1901, Röntgen received the first Nobel Prize for Physics. Pierre Curie. Antoine Becquerel discovered in 1896 the special radiating properties of uranium and its compounds.
Otto Hahn. For more than 100 years, uranium, discovered by M.H. Klaproth in 1789, had had a quiet existence as a somewhat rare but not particularly interesting element. It was distinguished from all the other elements in one particular respect. It occupied the highest place in the table of elements. As yet, however, that did not have any particular significance.
Pierre Curie. Uranium emits very weak rays which leave an impression on photographic plates. These rays pass through black paper and metals. They make air electrically conductive. The radiation does not vary with time, and the cause of its production is unknown.
Otto Hahn. The echo of Becquerel's fundamental observations on the radioactivity of uranium in scientific circles was at first fairly weak. 2 years later, however, they acquired an exceptional importance when the Curies succeeded in separating from uranium minerals 2 active substances, polonium and radium.
Pierre Curie. In making measurements, Marie found that certain of these were more active than they should have been. She then made the assumption that these substances contained radioactive chemical elements, which were as yet unknown. We first found a highly radioactive substance which we called polonium, and then, in collaboration with Gustave Beaumont, a second highly radioactive substance which we called radium.
Marie Curie. All the elements emitting such radiation I have termed radioactive, and the new property of matter revealed in this emission has thus received the name radioactivity. From that time onward, numerous scientists devoted themselves to the study of radioactivity.
Otto R. Frisch. It felt that atoms were talking to us, but in a code we couldn't decipher.
Ernest Rutherford, writing in 1904. If it were ever found possible to control at will the rate of disintegration of the radio elements, an enormous amount of energy could be obtained from a small quantity of matter.
Abraham Pais. The birth of quantum theory, 1900, and relativity theory, 1905, marked the beginning of an era in which the very foundations of physical theory were found to be in need of revision. 2 men led the way toward the new theoretical concepts. Max Carl Ernst Ludwig Planck, professor at the University of Berlin, possessed, perhaps obsessed, by the search for the universal function of frequency and temperature, and Albert Einstein, technical expert at the Swiss Patent Office in Bern.
I. Robbie. In 1905, Einstein enunciated the theory of special relativity from a general consideration of the nature of clocks, the measurement of time, and the remarkable consistency of the velocity of light as measured on different systems moving relatively to one another. As a straightforward deduction from this theory, he enunciated the equivalence of mass and energy.
Albert Einstein. E equals mc squared. Energy equals mass times the speed of light squared.
Glenn Seaborg, chemist, UC Berkeley. The speed of light is a very large number. The speed of light squared is a ridiculously large number. So a very small amount of mass converts to a relatively large amount of energy.
Max Planck. Einstein's work on relativity probably exceeds in audacity everything that has been achieved so far in speculative science, and even in epistemology. Non-Euclidean geometry is child's play by comparison.
Otto R. Frisch. A few papers were published which extended Einstein's reasoning, but it took another 8 years before the floodgates were opened by a young Danish physicist, Niels Bohr, through his proposed model of the atom. You must have seen it many times, decorating almost any publication related to atoms. A dot surrounded by several circles, usually foreshortened into intersecting ellipses. That model has now been out of date for half a century. But symbols have long lives. Father Time is still depicted with a sandglass, not a wristwatch.
Arthur Holly Compton. In 1911, Ernest Rutherford, later Lord Rutherford, discovered the nucleus of the atom.
Mark Oliphant. In 1912, Niels Bohr spent nearly 6 months with Rutherford, during which he became fascinated with the structure of the atom as revealed by Rutherford's work. Chadwick was much impressed by Bohr, by his intuitive grasp of and interest in all science, and by his kind and generous nature. They became lifelong friends. Niels Bohr, writing on June 19, 1912. It could be that I've perhaps found out a little bit about the structure of the atoms. If I'm right, it would not be an indication of the nature of a possibility, but perhaps a little piece of reality. I may yet be wrong, for it hasn't been worked out fully yet. You can imagine how anxious I am to finish quickly.
Otto R. Frisch. No other physicist of our time, except perhaps Einstein, has so strongly influenced our thinking in general, not just in physics. His model of the atom brought him immediate fame in 1913, with the electrons circling around the nucleus like miniature planets, confined to certain allowed orbits, except when they jumped from one orbit to another in the process of absorbing or emitting radiation. That picture was so astonishing and unorthodox. Bohr himself was very much aware of the crudeness of that model. It resembled the atom no more than a quick pencil sketch resembles a living human face. But he also knew how profoundly difficult it would be to get a better picture.
Niels Bohr. Abstract thinking, which throughout the ages has been one of the most powerful of man's aids in lifting the veil that shrouds the laws of nature from the eyes of the uninitiated observer, has proved of the utmost importance for enabling the insight into the structure of atoms.
Werner Heisenberg. To those of us who participated in the development of atomic theory, the 5 years following the Solvay Congress in Brussels in 1911 looked so wonderful that we often spoke of them as the golden age of atomic physics. The great obstacles that had occupied all our efforts in the preceding years had been cleared out of the way. The gate to that entirely new field, the quantum mechanics of the atomic shell, stood wide open, and fresh fruits seemed ready for the plucking.
Arthur Holly Compton. In 1919, Rutherford made the further startling discovery that when an alpha particle, i.e. a helium nucleus, strikes the nucleus of a nitrogen atom, a proton, i.e. a hydrogen nucleus, is sometimes emitted. Here was artificial transmutation, the changing of one chemical element into another. Helium acts on nitrogen to produce hydrogen. What is more, nuclear energy is released. This was shown by the fact that the proton escaped with an energy greater than that of the incident alpha particle. Here, at last, was a lead toward the release of atomic power.
C.P. Snow. As soon as Rutherford got into radioactivity, he was set on his life's work.
Arthur Holly Compton. On writing about it to an American friend, Rutherford commented that the influence of this discovery on the course of history might eventually be greater than that of the World War that had just been fought.
Henning Pleyel. Lord Rutherford suggested that apart from protons and electrons, there also existed particles of the same weight as a proton but without any electric charge. To this particle was given in advance the name of neutron. This neutron had long been searched for, but without any result.
The world of physics through the first half of the 20th century was a very tiny community, a fact represented in part by the groundbreaking science of Marie Curie's daughter Irene, who went on to marry physicist Frédéric Joliot and make key discoveries building on her mother's work. Discoveries were traded between and built upon one after another across this small field as the 1920s and 1930s progressed. Few of those discoveries would prove as transformative as the quest for Rutherford's elusive neutron.
Enrico Fermi. Joliot and Irene Curie, at the end of the year 1933, obtained the first cases of artificial radioactivity by bombarding boron, magnesium, and aluminium with alpha particles from a polonium source. They produced thus 3 radioactive isotopes of nitrogen, silicon, and phosphorus, and succeeded also in separating chemically the activity from the bulk of the unmodified atoms of the bombarded substance.
Leo Szilard. In 1932, while I was still in Berlin, I read a book by H.G. Wells called The World Set Free. This book was written in 1913, 1 year before the World War, and in it, H.G. Wells describes the discovery of artificial radioactivity and puts it in the year 1933, the year in which it actually occurred. He then proceeds to describe the liberation of atomic energy on a large scale for industrial purposes, the development of atomic bombs, and a world war which was apparently fought by an alliance of England, France, and perhaps including America, against Germany and Austria, the powers located in the center part of Europe. This book made a very great impression on me.
Herbert L. Anderson. The solid scientific fact that H.G. Wells had at his disposal when he wrote this book was what was known then about natural radioactivity, that uranium disintegrated by emitting alpha particles. This was a process yielding 1,000,000 times more energy per atom than in ordinary combustion. The trouble was that it took place very slowly. What was needed, H.G. Wells realized, was a way to speed it up. Then, from a pound or two of uranium, enough energy could be obtained to light a great city, power the wheels of industry, drive airplanes, and, inevitably, fashion devastating weapons of war. Those who knew Szilard would understand instantly why this idea would excite him, and why he would keep turning it over and over in his mind until he could figure out what he could do with it.
Leo Szilard. In London in September 1933, I read in the newspapers a speech by Lord Rutherford. He was quoted as saying that he who talks about the liberation of atomic energy on an industrial scale is talking moonshine. This set me pondering as I was walking the streets of London, and I remembered that I stopped for a red light at the intersection of Southampton Row. It suddenly occurred to me that if we could find an element which is split by neutrons, and which would emit 2 neutrons when it absorbed 1 neutron, such an element, if assembled in sufficiently large mass, could sustain a nuclear chain reaction. I didn't see at the moment just how one would go about finding such an element, or what experiments would be needed, but the idea never left me. In certain circumstances, it might become possible to set up a nuclear chain reaction, liberate energy on an industrial scale, and construct atomic bombs. The thought that this might be in fact possible became a sort of obsession with me.
Laura Fermi. In January 1934, the French physicists Frédéric Joliot and his wife Irene Curie announced that they had discovered artificial radioactivity.
Mark Oliphant. One morning, Chadwick read the communication of the Curie-Joliot in the French physics journal Compte Rendu.
James Chadwick. As I told Rutherford about the Curie-Joliot observation and their views on it, I saw his growing amazement. And finally, he burst out, "I don't believe it." Such an impatient remark was utterly out of character, and in all my long association with him I recall no similar occasion. I was convinced that there was something quite new, as well as strange. A few days of strenuous work were sufficient to show that these strange effects were due to a neutral particle, and to enable me to measure its mass. The neutron, postulated by Rutherford in 1920, had at last revealed itself.
Niels Bohr. We not only believe the existence of atoms to be proved beyond a doubt, but also we even believe that we have an intimate knowledge of the constituents of the individual atoms. According to our present conceptions, an atom of an element is built up of a nucleus that has a positive electrical charge, and is the seat of by far the greatest part of the atomic mass, together with a number of electrons, all having the same negative charge and mass, which move at distances from the nucleus that are very great compared to the dimensions of the nucleus or of the electrons themselves. In this picture we at once see a striking resemblance to a planetary system, such as we have in our own solar system.
Richard Feynman, physicist. If, in some cataclysm, all of scientific knowledge were to be destroyed, and only one sentence passed on to the next generations of creatures, what statement would contain the most information in the fewest words? I believe it is the atomic hypothesis, or the atomic fact, or whatever you wish to call it, that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another.
Otto R. Frisch. Atoms are not that small. About 1,000 times smaller than microbes, which you can see under an optical microscope. An ion microscope shows quite clearly the beautiful regular pattern of atoms on the point of a sharp needle. But atomic nuclei are really small. Try to think of something 1,000 times smaller than an atom, and you are still not down to the size of atomic nuclei. You need another factor of 20 or so. If an atom were enlarged to the size of a bus, the nucleus would be like the dot on this eye.
Maurice Goldwater, physics student. What one might call the neutronic age started there in 1932 with Chadwick's discovery of the neutron.
Arthur Holly Compton. It is this particle whose use, 10 years later, made possible the nuclear chain reaction.
I. Robbie. The neutron is really what makes the atomic bomb tick.
Otto Hahn. It was especially the Italian scientist Enrico Fermi who first realized the great importance of neutrons for the production of nuclear reactions.
Laura Fermi. After Enrico learned of Joliot and Curie's discovery, he decided he would try to produce artificial radioactivity with neutrons. Being a man of method, he did not start by bombarding substances at random, but proceeded in order, starting from the lightest element, hydrogen, and following the periodic table of elements. Hydrogen gave no results. When he bombarded water with neutrons, nothing happened. He tried lithium next, but again without luck. He went on to beryllium, then to boron, to carbon, to nitrogen. None were activated. Enrico wavered, discouraged, and was on the point of giving up his researches, but his stubbornness made him refuse to yield. He would try one more element. That oxygen would not become radioactive, he knew already, for his first bombardment had been on water. So he irradiated fluorine. Hooray! He was rewarded. Fluorine was strongly activated, and so were other elements that came after fluorine in the periodic table.
Enrico Fermi. A systematic investigation of the behavior of the elements throughout the periodic table was carried out by myself, with the help of several collaborators, namely Amaldi, D'Agostino, Pontecorvo, Rassetti, and Segre. Eduardo Amaldi, We worked with incredible stubbornness. We would begin at 8 in the morning and take measurements, almost without a break, until 6 or 7 in the evening, and often later.
Otto Hahn. Fermi and his co-workers irradiated practically all of the elements of the periodic system with neutrons and made numerous artificial radioactive elements.
Laura Fermi. When, in the course of their researches, they came to bombard with neutrons the last element of the periodic table, uranium, whose atomic number is 92, they found that it became active, that more than one element was produced, and that at least one of the radioactive products was none of the existing elements close to uranium. Theoretical considerations and chemical analysis seem to indicate that a new element of atomic number 93, an element which does not exist on Earth because it is not stable, was among the disintegration products of uranium.
Robbie. Fermi and his school of physicists in Italy were among the first to realize the power of the neutron. Since the neutron carries no charge, there is no strong electrical repulsion to prevent its entry into nuclei. In fact, the forces of attraction which hold nuclei together may pull the neutron into the nucleus. When a neutron enters the nucleus, the effects are about as catastrophic as if the moon struck the Earth. The nucleus is violently shaken up by the blow, especially if the collision results in the capture of the neutron. A large increase in energy occurs and must be dissipated, and this may happen in a variety of ways, all of them interesting.
Laura Fermi. They sent their first report to Ricerca Scientifica in May 1934, not to claim the discovery of a new element, but rather to relate what indications they had found that such an element might have been produced. The New York Times published a 2-column article under a 2-line headline, Italian produces 93rd element by bombarding uranium.
Lisa Meitner. From 1934 to 1938, Otto Hahn and I were able to resume our joint work, the impetus for which had come from Fermi's results in bombarding heavy elements with neutrons.
Otto Hahn. I remember our co-worker, Max Delbrück, who was Lisa Meitner's assistant, expressing his amazement that after having received this exciting news about Fermi's work in Italy, we could sleep a wink before repeating the experiments. That decision led to the work on which Lisa Meitner and I thereupon started, work that lasted more than 4 years. We were soon joined by Fritz Strassmann, who had been working at our institute since 1929. We soon ascertained that Fermi was right, but we also found that what happened when uranium was bombarded with neutrons was very complicated indeed.
Luis Alvarez. Soon afterward, a German chemist, Ida Nodak, published a critical demurrer. Fermi could not claim the discovery of new transuranium elements, she argued, until his unidentified radioisotopes had been compared with every element in the periodic table. No one took Nodak seriously. The notion that uranium could turn into a lighter element in the middle of the periodic table under bombardment by nothing more energetic than thermal neutrons was self-evidently ridiculous. To do so, it would have to split.
Laura Fermi. A controversy over element 93 had started and dragged on inconclusively.
Luis Alvarez. I was bothered at the time that the Fermi transuranics didn't fit the pattern of other radioactive elements. Instead of decaying, as we said, downhill to the floor of the Valley of Stability, they decayed uphill into a region that ought to be progressively more unstable. I knew something was off-key, as did everyone familiar with nuclear theory. But the correct explanation entailed such a radical departure from contemporary understanding that no one pursued the matter.
Darkness falls on Europe. The advances of physics through the 1930s were inseparable from the darkening clouds of far-right fascism on the European continent. The rise of Adolf Hitler and his National Socialist Party in Germany and Benito Mussolini in Italy destabilized much of Europe's scientific progress, particularly as anti-Semitic politics and pogroms targeted many of the biggest names in physics. Those fascist governments came to power alongside ruinous inflation caused by the fallout of World War I. Over the course of 1923, the German mark fell from 400 to the dollar to 7,000, to finally 4.2 trillion to the dollar by November. Foreigners found themselves living like royalty, as pensioners starved. Even beyond Germany and Italy, scientists across Europe watched the enveloping cloak of fascism warily, nowhere more so than in Hungary. While there were just 350 Jewish families in Hungary on the eve of World War II, that small group possessed one of the greatest generations of scientific talent in world history, including physicists Eugene Wigner and Edward Teller, computer pioneer John von Neumann, and the space-defining aerospace engineer Theodor von Karman. Out of the prospering but vulnerable Hungarian Jewish middle class came no fewer than 7 of the 20th century's most exceptional scientists, historian Richard Rhodes wrote. The mystery of such a concentration of ability from so remote and provincial a place has fascinated the community of science. None of them, nor their colleagues elsewhere in the continent, would find themselves immune to the hate and war of the 1930s.
Albert Einstein, writing in December 1919. Anti-Semitism is strong here, and political reaction is violent. Werner Heisenberg. The end of the First World War had thrown Germany's youth into a great turmoil. The reins of power had fallen from the hands of a deeply disillusioned older generation, and the younger one drew together in an attempt to blaze new paths, or at least to discover a new star by which they could guide their steps in the prevailing darkness. The summer of 1922 ended on what, for me, was a rather saddening note. My teacher had suggested that I attend the Congress of German Scientists and Physicians in Leipzig, where Einstein, one of the chief speakers, would lecture on the general theory of relativity. The lecture theatre was a large hall with doors on all sides. As I was about to enter, a young man pressed a red handbill into my hand, warning me against Einstein and relativity. The whole theory was said to be nothing but wild speculation, blown up by the Jewish press, and entirely alien to the German spirit. At first I thought the whole thing was the work of some lunatic, for madmen are wont to turn up at all big meetings. However, when I was told that the author was a man renowned for his experimental work, I felt as if part of my world were collapsing. All along I had been firmly convinced that science at least was above the kind of political strife that had led to the civil war in Munich, and of which I wished to have no further part. Now I made the sad discovery that men of weak or pathological character can inject their twisted political passions even into scientific life.
Rudolf Peierls. The economic situation in Germany was getting worse, unemployment was high, and political life was becoming more violent. Assassinations had been common during the whole period of the Weimar Republic, and now the brown shirts of the National Socialists were increasing in number and in aggressiveness. Yet few people had any inkling of the disaster that was imminent.
Sigmund Freud, December 7, 1930. We are moving toward bad times. I ought to ignore it with the apathy of old age, but I can't help feeling sorry for my 7 grandchildren.
Leo Szilard. I reached the conclusion something would go wrong in Germany very early. I reached in 1931 the conclusion that Hitler would get into power, not because the forces of the Nazi Revolution were so strong, but rather because I thought that there would be no resistance whatsoever.
Albert Einstein, writing in his diary, December 1931. I decided today that I shall essentially give up my Berlin position and shall be a bird of passage for the rest of my life. Otto R. Frisch. I have never been politically conscious. In the early 30s in Hamburg, I didn't pay any attention to the general crisis atmosphere. With a sarcastic smile, I observed the repeated changes of government and the much joked-about ineptness of Hindenburg, the famous general who had been made president of the Republic of Germany. When a fellow by the name of Adolf Hitler was making speeches and starting a party, I paid no attention. Even when he became elected chancellor, I merely shrugged my shoulders and thought, nothing gets eaten as hot as it is cooked, and he won't be any worse than his predecessors.
Louis Fisher, correspondent, The Nation. How did Hitler come to power in Germany? Hitler's policy, at home and abroad, has always been to reveal his plans. Hyper-suspicion of propaganda, however, led many people to doubt what he said. The Nazis boasted that they would rule Germany, and Hitler painted a picture of his future game. Heads will roll, he said. He would destroy democracy. Yet democracy tolerated him and helped him take office in order to destroy democracy. This peaceful death of German democracy is one of the strangest chapters in history. German democracy marched to its grave with its eyes wide open and singing, "Beware of Adolf Hitler." Democracy is temperate. Its foe is extremism. In Germany, extremism was the thermometer of a sick social system and an ailing economy.
Eugene Wigner. Most Germans seemed strangely unconcerned with Hitler. They had not sought him, but when he came, they said, "Well, the man is impressive. Let us see what he does." Few of them expected him to lead Germany into a disastrous war. They watched with interest as he blamed their hardships on Jews and on other nations. But most of them thought he would stop short of a war. After all, Hitler had managed to take power in Germany without a war.
Bulletin. International News Service, January 30th, 1933. Adolf Hitler, Nazi chieftain who began life as a house painter and street sweeper, achieved his life's ambition today when he was appointed Chancellor of the Reich.
John Gunther, Europe correspondent, Chicago Daily News. The night of February 27th, 1933, a few days before the March 5th elections which were to confirm Hitler's chancellorship, the building of the German Reichstag in Berlin was gutted by fire. This fire destroyed what remained of the German Republic. It not only burned a public building, it incinerated the Communist, Social Democratic, Catholic, and Nationalist parties of Germany. It was discovered at about 9:15 on a winter evening back in 1933, but its embers are burning yet. In the flames of the Reichstag fire disappeared the old Germany of Bismarck, William II, and the Weimar Constitution. In its smoke arose Hitler's Third Reich.
Leo Szilard. Hitler came into office in January 33, and I had no doubt what would happen. I lived in the faculty club of the Kaiser Wilhelm Institute in Berlin-Dahlem, and I had my suitcases packed. By this I mean that I had literally 2 suitcases standing in my room which were packed. The key was in it, and all I had to do was turn the key and leave when things got too bad. I was there when the Reichstag brand occurred, and I remember how difficult it was for people there to understand what was going on. A friend of mine, Michael Polanyi, who was director of a division of the Kaiser Wilhelm Institute for Physical Chemistry, like many other people, took a very optimistic view of the situation. They all thought that civilized Germans would not stand for anything really rough happening.
Otto R. Frisch. I didn't take Hitler at all seriously at first. I had the feeling, well, chancellors come and chancellors go, and he will be no worse than the rest of them. Things began to change. And of course, when the racial laws were published, by which people of partly or wholly Jewish origin had to be dismissed from the universities, I realized that my days were numbered.
Edgar Ansel Maurer, Berlin correspondent, Chicago Daily News. The elimination of Jews from German public life, if not from Germany altogether, was one of the chief promises of National Socialist propagandists, and apparently rarely failed to elicit approval.
Ralph W. Barnes, datelined Nuremberg, Germany, September 15, 1935. Stringent new laws depriving German Jews of all the rights of German citizens and prohibiting marriages between Jews and Aryans, Gentiles, were decreed by a subservient, cheering Reichstag here tonight, after an address by Chancellor Adolf Hitler.
Hermann Göring, Air Minister and Prussian Premier, German Reich. We must preserve the Germanic and Nordic purity of the race, and must protect our women and girls with every means at our disposal. In this pure bloodstream will blossom forth a new era of Germanic happiness. Never again will we let our Germanism be infected and ruined by Jewish infiltration. Our newly won freedom requires a new symbol. The swastika has become for us a holy symbol. It is the anti-Jewish symbol of the world.
Eugene Wigner. The situation for Jews in Germany rapidly became intolerable. I would now need a permanent home outside Europe. I hoped against hope that fascism would subside and Hitler be replaced or subdued, but I did not expect it to happen. By 1933, I saw Europe as a sinking ship.
Leo Szilard, how quickly things move you can see from this. I took a train from Berlin to Vienna on a certain date, close to the 1st of April 1933. The train was empty. The same train, on the next day, was overcrowded, was stopped at the frontier, the people had to get out, and everybody was interrogated by the Nazis. This just goes to show that if you want to succeed in this world, you don't have to be much cleverer than other people. You just have to be one day earlier than most people. This is all that it takes.
Werner Heisenberg. The golden age of atomic physics was now fast drawing to an end. In Germany, political unrest was increasing. For a time, I tried to close my eyes to the danger, to ignore the ugly scenes in the street. But when all is said and done, reality is stronger than all our wishes. Otto R. Frisch. Disturbing rumors were rife. Some of my Jewish friends had warned me not to be out at night, because Jews had been beaten up in the dark. I remember walking home late one night when I heard fast footsteps ring out in the empty street. I wondered if it was one of those anti-Semitic brutes on the rampage. Of course, to break into a run would have given me away at once. I kept my speed, though the footsteps rapidly came nearer, and finally pulled up beside me. A burly fellow in SA uniform pulled off his cap and greeted me with politeness. It was the son of my landlady. He explained to me that he had to join this paramilitary force because otherwise he would not have been allowed to complete his law studies. There were many like him who disliked the Nazis, but couldn't afford not to join. The persistent stories of concentration camps, of synagogues burnt, of beatings and torture, all were stoutly denied by the German newspapers as mere horror propaganda put out by the enemies of Germany. Some of my friends told me the stories were true. Indeed, that the truth was worse. But I wouldn't believe that Germany had changed so suddenly and so horribly, and that all the newspapers could so consistently be telling lies.
Kurt Mendelsohn, chemist. Breslau, where I had a post at the university in 1933, was ahead of most German cities in establishing Nazi terror. We decided to leave forthwith, ostensibly to spend Easter in Berlin. In Berlin, I bought a ticket to London. When I woke up in London, the sun was shining in my face. I had slept deeply, soundly, and long, for the first time in many weeks. The night before, I had arrived in London and gone to bed without fear that at 3 a.m. a car with a couple of SA men would draw up and take me away.
P.B. Moon, physicist, Cambridge. Rutherford did a very great deal for the refugees from Hitler's Germany, finding places for some of them in his laboratory and scraping together what money he could to keep them and their families going until they could find established posts. Otto R. Frisch. In Copenhagen, I heard for the first time the suggestion that the fire that had devastated the German parliament had not been started by the accused communist van der Lubbe, but had been deliberately laid by the Nazis in order to work up public opinion against the communists. It was an idea that startled me at first, but then seemed plausible. After my return to Hamburg, my one remaining colleague in the department, Knauer, gave me dinner at his lodgings and wanted to hear what people abroad said about the fire. Although he had become a Nazi, Knauer had never let the anti-Semitic party line interfere with our friendship. Quizzed about the fire, I tried to hold my peace and talk of other things. But when he insisted, I did tell him that people were convinced that the fire had been laid by the Nazis for political reasons. He was horrified. But how can anybody think such a thing of people like Hitler or Goering? Just look at their faces. Knauer kept his friendly and helpful attitude to the last, and made my departure easy by finding a small freighter that was going to London and had one cabin for a passenger. On that cockleshell, on a windy day in October 1933, I left Germany with all my belongings in several trunks, which kept sliding forth and back in my cabin as the ship rolled and pitched across the North Sea, while I braced myself in my berth, unable to sleep. Werner Heisenberg. When I returned to my Leipzig Institute at the beginning of the summer term of 1933, the rot had begun to spread. Several of my most capable colleagues had left Germany, others were preparing to flee. Even my brilliant assistant, Felix Bloch, had decided to emigrate, and I myself began to wonder whether there was any sense in staying on.
Bulletin, Associated Press, August 2nd, 1934. Adolf Hitler made himself absolute dictator of Germany today. He concentrated in his own hands the functions of president and of chancellor as soon as the aged president Paul von Hindenburg had died at Neudeck.
Laura Fermi. It was almost unbelievable. Germans were the traditional foes of Italians. Since the First World War, a fallen foe. The newly risen Führer of Germany was held to be a none-too-intelligent imitator of the Duce, a puppet obediently waiting for directives from the fascist master. The puppet had taken some initiative of his own. In March 1935, he had denounced the Versailles Treaty and declared that Germany would rearm. The Führer had in store another of his spring surprise moves. In March 1936, his troops occupied the demilitarized Rhineland. By then, Mussolini was on bad terms with France and England, but dreaded and opposed a strong Germany.
Leo Szilard. When the German troops moved into the Rhineland and England advised France against invoking the Locarno Pact in March 1936, I knew that there would be war in Europe.
Eduardo Amaldi. Physics as soma. Roughly, physics is the cure, a reference to Aldous Huxley's Brave New World, was our description of the work we performed, while the general situation in Italy grew more and more bleak, first as a result of the Ethiopian campaign, and then as Italy took part in the Spanish Civil War.
Eugene Wigner. Hitler's campaign against the Jews cost him most of the greatest people I had studied with. If Hitler did not personally fire us all from our jobs, he made life unsafe for us in Nazi countries, and he forced us to follow politics. Many other important physicists fled as well, Enrico Fermi, Edward Teller, Hans Bethe among them. Most of us resettled in the United States. Perhaps the United States should erect a great stone monument to Adolf Hitler for his dedication to advancing the American natural sciences. Not even Joseph Stalin scattered scientists like Hitler.
Fleeing fascism. By 1938, war was enveloping Europe, and those scientists who could plan their escapes came mostly to U.S. and British institutions, labs, and universities. But the physicists of Europe had one last important discovery to contribute: the process that would come to be known as fission, the chain reaction that unlocked the near-inexhaustible energy of the atom and illuminated the path toward both atomic weapons and nuclear power.
Laura Fermi. The Italian government seemed to have gone crazy. The first anti-Semitic laws were passed early in September. We at once decided to leave Italy as soon as possible. Enrico wrote 4 letters to 4 American universities, in which he stated that his reasons for not accepting their previous offers had ceased to be. He dared write nothing more specific. We were still in the Alps, and 4 letters, all in the same handwriting, all going to America, if mailed at the same village, could not fail to arouse suspicion. We took advantage of a car trip and mailed Enrico's letters at 4 towns miles apart. Enrico received 5 offers of positions in America. He accepted that of Columbia University. To Italian officials, he declared that he was embarking on a 6-month visit to New York.
Emilio Segre. In the fall of 1938, at a physics meeting in Copenhagen, Fermi was confidentially informed by Bohr that his name was high on the list of candidates for a Nobel Prize. Such a disclosure was most unusual, but was prompted by an effort to ascertain that the award would not embarrass him. There had been cases in which dictatorships had forced a recipient to renounce the award, or had otherwise harassed him. The Swedish Academy was thus taking precautions. The nomination to the award was hardly surprising. but it called for some adjustments in Fermi's immigration plans.
Laura Fermi. To prospective emigrants who would be allowed to take along $50 apiece when leaving Italy for good, the Nobel Prize would be a godsend. However, the existing monetary laws required Italian citizens to convert any foreign holdings into lire and bring them into Italy. Hence our decision to go to Stockholm and from there directly to the United States if Enrico were to be awarded the Nobel Prize.
Emilio Segre. Once Fermi made a decision, he never looked back.
Laura Fermi. Early on the morning of November 10, 1938, I found myself answering the telephone in the hall of our home. "Is this Professor Fermi's residence?" asked the operator's voice. "I wish to inform you that this evening at 6, Professor Fermi will be called on the telephone from Stockholm." My drowsiness vanished at once. A call from Stockholm. I ran back into our bedroom. Enrico's head was still sunk in the hollow of his soft pillow. "Wake up, Enrico! This evening you'll be called on the telephone from Stockholm." Calm, but immediately alert, Enrico propped himself up on his elbow and replied, "It must mean the Nobel Prize."
Emilio Segre. On December 6, 1938, the Fermi family, Enrico, Laura, the two children, Nella and Giulio, and the maid, boarded the train at Rome. Amaldi and Rossetti went to the station to say goodbye. Everyone understood that the departure signified the end of a memorable period in their lives.
Laura Fermi. There was the prize award on December 10th, the anniversary of Nobel's death. Only the prizes for literature and for physics were awarded in 1938. Pearl Buck, the American writer of novels with Chinese background, and Enrico sat in the center of the stage in the concert hall. Enrico sat stiff because he could not do otherwise. Stiff with the expectation of a dreaded but likely mishap. That the heavily starched front of his evening shirt might suddenly snap and thrust out in a protruding arc between the silk lapels of his full dress suit, with an explosive sound at his first incautious move, as it had done many times before. Although dedicated to measurement, Enrico had not yet recognized that fronts of ready-made shirts were too long for him.
Edward Teller. The Fermis used the prize money to travel on to New York, where Enrico settled in as a professor at Columbia.
Emilio Segre. The Fermis landed in New York on January 2, 1939, and Fermi turned to his wife and said, "We have founded the American branch of the Fermi family." I can imagine his smile.
The Fermis were hardly the only ones to find their quiet lives of science interrupted as the war years began. Even as some others fled, the work continued, and uncovering the next step in the quest to understand and harness the atom fell to the newly displaced Lisa Meitner and her colleague chemists Otto Hahn and Fritz Strassmann, along with her nephew Otto Frisch.
Edward Teller. The chairman of the physics department at the George Washington University asked me to give a talk about atomic theory to the faculty of the university. During the question period following my lecture, someone asked, "How long before a practical use of nuclear energy might be worked out?" I predicted, "It may take a year, 100 years, or it may never happen." I was wrong. As I was speaking, two chemists at the Kaiser Wilhelm Institute in Berlin were beginning to examine the first key to unlocking nuclear energy. That key had been lying around unused for half a dozen years.
Otto R. Frisch. Lisa Meitner had been working in Berlin with the chemist Otto Hahn for about 30 years, and during the last 3 years they had been bombarding uranium with neutrons and studying the radioactive substances that were formed. Otto Hahn. In spite of more or less trivial interference on the part of the regime, work had been going ahead smoothly so far. Professor Lisa Meitner had not been troubled by anybody in those first years, for, being an Austrian, she was protected by her foreign nationality. Professor Thiessen, director of the Kaiser Wilhelm Institute of Physical Chemistry, which had meanwhile been transformed into a model institution of National Socialist science, treated Lisa Meitner with all due courtesy for as long as she stayed in Berlin. But now came the year 1938. Otto R. Frisch. The occupation of Austria in March 1938 changed my aunt, the physicist Lise Meitner, technically from an Austrian into a German. She had acquired fame by many years' work in Germany, but now had to fear dismissal as a descendant of a Jewish family. Moreover, there was a rumor that scientists might not be allowed to leave Germany. So she was persuaded, or perhaps stampeded, into leaving at very short notice, assisted by friends in Holland. Otto Hahn. Now for Lise Meitner too, the situation became critical.
Lise Meitner. I decided that it was high time to get out with my secrets.
Otto Hahn. We decided to get her across the frontier illegally and as quickly as possible. On the evening of 16th July, Professor Costa arrived from Holland and came straight to the Institute. He brought with him an assurance that the Dutch would permit Lise Meitner to enter Holland without a visa. Aided by our old friend Paul Rosbo, we spent the night packing the clothes she most needed and some of her valuables. I gave her a beautiful diamond ring that I had inherited from my mother, and which I had never worn myself but always treasured. I wanted her to be provided for in an emergency. On the morning of 17th July, accompanied by Professor Costa, Lise Meitner left in all secrecy, not knowing what that day might hold in store for her. We agreed on a code telegram, in which we would be let known whether the journey ended in success or failure.
Lise Meitner. I took a train for Holland on the pretext that I wanted to spend a week's vacation.
Otto Hahn. The danger consisted in the SS's repeated passport control of trains crossing the frontier. People trying to leave Germany were always being arrested on the train and brought back. Lise Meitner was lucky. She succeeded in crossing the frontier to safety.
Lise Meitner. At the Dutch border, I got the scare of my life when a Nazi military patrol picked up my Austrian passport, which had expired long ago. I got so frightened, my heart almost stopped beating. I knew that the Nazis had just declared open season on Jews. For 10 minutes, I sat there and waited. 10 minutes that seemed like so many hours. Then one of the Nazi officials returned and handed me back the passport without a word. 2 minutes later, I descended on Dutch territory, where I was met by some of my Holland colleagues. There I obtained my Swedish visa.
Otto R. Frisch. In the autumn, she accepted an invitation to work in Stockholm at the Nobel Institute, led by Manne Siegbahn. I had always kept the habit of celebrating Christmas with her in Berlin. This time she was invited to spend Christmas with Swedish friends in the small town of Kungälv, near Gothenburg, and she asked me to join her there. That was the most momentous visit of my whole life. Otto Hahn. When we had carried out the indicator experiments that proved barium was present, I wrote some personal letters to Lise Meitner, telling her of our results. In my letter of 19th December, I wrote, "The thing is, there's something so odd about the radium isotopes that for the moment we don't want to tell anyone but you. The half-lives of the 3 isotopes are pretty accurately determined. They can be separated from all the elements except barium. All reactions are correct, except for one, unless there are some very weird accidental circumstances involved. The fractionation doesn't work. We are more and more coming to the awful conclusion that our radium isotopes behave not like radium, but like barium. Strassmann and I agree that for the time being nobody should know but you. Perhaps you can put forward some fantastic explanation. We ourselves realize it can't really burst into barium."
Fritz Strassmann. Lise Meitner was the intellectual leader of our team, and therefore she belonged to us, even if she was not present for the discovery of fission.
Otto R. Frisch. When I came out of my hotel room after my first night in Kungälv, I found Lise Meitner studying a letter from Hahn, and obviously worried by it. I wanted to tell her of a new experiment I was planning, but she wouldn't listen. I had to read that letter. Its content was indeed so startling that I was at first inclined to be skeptical.
Laura Fermi. Lise Meitner became the first scientist outside Germany to learn of Hahn's and Strassmann's discovery. She realized what had happened. Some uranium atoms had split into 2 almost equal parts. In order to talk the matter over at leisure, the aunt and nephew took a long walk in the snow. Physical exercise, they thought, might clear their minds. Lisa Meitner did most of the talking, urgently, convincingly.
Otto R. Frisch. We both sat down on a tree trunk. All that discussion had taken place while we walked through the wood in the snow, I with my skis on, Lisa Meitner making good her claim that she could walk just as fast without, and started to calculate on scraps of paper. Lisa Meitner remembered the empirical formula for computing the masses of nuclei, and worked out that the two nuclei formed by the division of a uranium nucleus together would be lighter than the original uranium nucleus by about 1/5 the mass of a proton. Now, whenever mass disappears, energy is created, according to Einstein's formula E equals mc squared, and 1/5 of a proton mass was just equivalent to 200 MeV. It all fit.
Arthur Holly Compton. Here would be a source of energy enormously greater than any that science had heretofore known.
Laura Fermi. Once he became convinced, Frisch felt, like his aunt, that they should not keep the news to themselves. They decided to inform Niels Bohr at once. Bohr lived in Copenhagen, Denmark, and so aunt and nephew hastened from Sweden to that city.
Otto R. Frisch. I traveled to Copenhagen in considerable excitement. I was keen to submit our speculations, it wasn't really more at the time, to Bohr, who was just about to leave for the USA. He had only a few minutes for me, but I had hardly begun to tell him when he smote his forehead with his hand and exclaimed, "Oh, what idiots we all have been! Oh, but this is wonderful! This is just as it must be! Have you and Lisa Meitner written a paper about it?" "Not yet," I said, "but we would at once." And Bohr promised not to talk about it before the paper was out.
Arthur Holly Compton. The conversation became so intense that only with difficulty could Bohr tear himself away to catch the train.
Otto R. Frisch. The paper was composed by several long-distance telephone calls, Lisa Meitner having returned to Stockholm in the meantime. I asked an American biologist who was working with Hevesy what they called the process by which single cells divide in two.
William A. Arnold, Frisch lab partner. Frisch looked up at me and said, "You work in a microbiology lab. What do you call the process in which one bacterium divides into two?" I answered, "Binary fission." He wanted to know if you could call it fission alone, and I said you could.
Otto R. Frisch. Fission, he said. So I used the nuclear fission in that paper. It was sent off to Nature. About 5 weeks passed before Nature printed those notes.
John A. Wheeler, nuclear physicist, Met Lab. On Monday, January 16th, 1939, I taught my morning class at Princeton University, then took a train to New York and walked to the dock where the Danish physicist Niels Bohr was scheduled to arrive on the MS Drottningholm. I was not the only one who decided to welcome Bohr personally. While I was waiting on the dock, who should turn up but the Italian physicist Enrico Fermi and his wife, Laura, who, with their 2 children, had arrived in the United States only 2 weeks earlier.
Herbert L. Anderson. Bohr came through New York on his way to Washington. He was anxious to see Fermi's reaction to his great news. Bohr came right over and grabbed me by the shoulder. "Young man," he said, "let me explain to you about something new and exciting in physics." Then he told me about the splitting of the uranium nucleus. Suddenly, everything I had done in that last 5 years began to make sense. Neutrons brought about the fission of uranium, and neutrons had become my field.
I. Robbie. By nightfall, Fermi was already speculating on the size of the crater which would be produced if 1 kilogram of uranium were to disintegrate by fission. Similar scenes were occurring all over the world. The race for the atomic bomb was on.
Luis Alvarez. I learned about the discovery of nuclear fission in the Berkeley campus barbershop while my hair was being cut. Buried on an inside page of the San Francisco Chronicle was a story from Washington reporting Niels Bohr's announcement that German chemists had split the uranium atom by bombarding it with neutrons.
Associated Press. 200 million volts of energy created by atom explosions. San Francisco Chronicle, Monday, January 30th, 1939, page 2. American scientists heard today of a new phenomenon in physics: explosion of atoms with a discharge of 200 million volts of energy.
Luis Alvarez. I stopped the barber in mid-snip and ran all the way to the radiation laboratory to spread the word.
Philip H. Abelson. My memories of the day that news of uranium fission came to the Berkeley Radiation Laboratory are vivid. That morning, as a member of the cyclotron crew, I was at the control console, operating the machine. About 9:30 a.m., I heard the sound of running footsteps outside, and immediately afterward, Alvarez burst into the laboratory. When Alvarez told me the news, I almost went numb.
Luis Alvarez. As people arrived at the laboratory that morning, we told them the news. Everyone found it hard to believe. I tracked down Robert Oppenheimer. He instantly pronounced the reaction impossible and proceeded to prove mathematically that someone must have made a mistake. The next day, Ken Green and I demonstrated the reaction. I invited Robert over to see the very small natural alpha particle pulses on our oscilloscope and the tall, spiking fission pulses 25 times larger. In less than 15 minutes, he not only agreed that the reaction was authentic, but also speculated that in the process, extra neutrons would boil off that could be used to split more uranium atoms and thereby generate power or make bombs. It was amazing to see how rapidly his mind worked.
Glenn Seaborg. I do not recall ever seeing Hoppy so stimulated and so full of ideas. As it turned out, I was privileged to witness his first encounter with the phenomenon that was to play such an important role in shaping the future course of events in his life.
J. Robert Oppenheimer. Letter to William Fowler, January 1939. The U business is unbelievable. We first saw it in the papers, wired for more dope, and have had a lot of reports since. In how many ways does the U come apart? At random, as one might guess, or only in certain ways? It is, I think, exciting, not in the rare way of positrons and mesotrons, but in a good, honest, practical way.
In Oppenheimer's letters, this letter is dated January 28th, 1939. But there's reason to believe it was written at least a bit later, since it seems like word of the events didn't get to Berkeley until 2 days later.
Philip Morrison. When fission was discovered, within perhaps a week, there was on the blackboard in Robert Oppenheimer's office a drawing, a very bad and execrable drawing, of a bomb.
Adjusting to the new world. For the still tiny circle of scientists who understood the potential of fission, the leap from the theoretical to the potential of an atomic bomb came quickly, and with fierce urgency, given how many had fled Nazism and the creep of authoritarian regimes of Europe. They resolved to force their newly adopted home country of the U.S. to pay attention.
Eugene Wigner. Eagerly, Leo Szilard and I discussed the atomic bomb with our university colleagues. Szilard knew the crucial questions. How could we reach the men who controlled American warfare? And how could we persuade them of the military value of an atomic bomb project? Our academic colleagues, for all of their eminence, had little authority in warfare and few resources. Szilard knew that we could hardly make an atomic bomb without federal support. But he disliked this idea, and like most men, he was reluctant to face that which he disliked. He was afraid that the government would saddle uranium research with an awful load of bureaucracy.
Arthur Holly Compton. In the United States, the first steps toward putting atomic energy to military use were taken almost immediately after uranium fission was discovered. At the urging of Szilard and Fermi, Professor George B. Pegram of Columbia University wrote to Admiral S.C. Hooper, then director of the Technical Division of Naval Operations.
Eugene Wigner. Enrico Fermi was invited to meet some Navy men, including a man named Ross Gunn. The talk was a distinct failure. Fermi got nothing more from it but $2,000 for isotope research. The Army and the Navy had their own thinking, and they found atomic bombs alien. They said it's just some crazy worrying by a few foreigners. And in a way they were right. There was something crazy about touting an atomic bomb, when so little of the crucial work had been done.
Laura Fermi. On that same March 16th, when Professor Pegram had written his letter, Hitler had annexed what was left of Czechoslovakia after the Munich dismemberment. War was approaching. There could be little doubt of it.
Edward W. Beatty, Jr., correspondent, United Press. The murder of Czechoslovakia is just a little red-inked stamp on page 19 of my passport, with the date of March 14, 1939, and the word Prejezd, which I guess must mean entry. There is no exit stamp because the German army marched in next day, and it took a military pass to leave Prague. The one scene that was most poignant was the entry of the first heavy German column into Wenceslas Square in mid-morning of March 15th. Dense snow slanted down. The crowd jammed so close it was almost impossible to move. A rumble grew down the side street, and the first German tanks and armored cars, their crews sitting tight-lipped with submachine guns at the ready, turned into the square. As they clattered across the pavement, a wave of sound swept with them and grew into a chorus of thousands of voices as the Czechs sang their national anthem into the mouths of German guns.
Edward Teller. The four of us who had worked in Germany knew well the excellence of the physicists who were likely to be considering similar questions about fission. We argued that, from now on, we should not publish the results of fission research, lest the Nazis learn from them and apply them to making a nuclear explosive. Bohr, however, took the opposite view with deep conviction.
Niels Bohr. Openness is the basic condition necessary for science. It should not be tampered with.
Edward Teller. He thought we were unduly alarmed. Separating the two forms of uranium and accumulating a sufficient quantity of U-235 would require efforts so huge as to be impractical. You would need to turn the entire country into a factory, he declared.
Arthur Holly Compton. Now that a chain reaction appeared likely, uranium fission became a matter involving the nation's safety. At Leo Szilard's urgent plea, the new discovery was withheld from publication.
Leo Szilard. At this point, Wigner and I began to worry about what would happen if the Germans got hold of large quantities of the uranium which the Belgians were mining in the Congo. We began to think, through what channels could we approach the Belgian government and warn them against selling any uranium to Germany? It occurred to me that Einstein knew quite well the Queen of the Belgians, and so I suggested to Wigner that we visit Einstein, tell him about the situation, and ask him whether he might not write to the Queen.
Eugene Wigner. Einstein somehow knew the Belgian royal family, so we felt he ought to write this letter. It was not customary for physicists to be on familiar terms with European royalty, but then Einstein was not an ordinary physicist.
Leo Szilard. We knew that Einstein was somewhere on Long Island, but we didn't know precisely where. So I phoned his Princeton office, and I was told he was staying at a Dr. Moore's cabin at Peconic, Long Island. Wigner had a car, and we drove out there and tried to find Dr. Moore's cabin.
Eugene Wigner. July 16, 1939 was a Sunday. Szilard and I got terribly lost trying to find the house.
Leo Szilard. We drove around for a half an hour, asking everybody we met. No one knew Dr. Moore's cabin.
Eugene Wigner. We knew the street name, and along the way asked a good many people where the street was. No one could tell us.
Leo Szilard. We were on the point of giving up and going back to New York when I saw a boy aged maybe 7 or 8 standing on the curb. I leaned out of the window and I said, "Say, do you by any chance know where Professor Einstein lives?" The boy knew that, and he offered to take us there, though he had never heard of Dr. Moore's cabin.
Eugene Wigner. There we found Einstein dressed in an old shirt and unpressed pants, apparently perfectly content to be thinking only of physics.
Leo Szilard. We discussed the situation with Einstein. This was the first Einstein had heard about the possibility of a chain reaction. He was very quick to see the implications, and perfectly willing to do anything that needed to be done.
Eugene Wigner. Einstein was not interested in nuclear physics. Indeed, he thought that all of quantum theory was largely an error. And who knows, perhaps someday Einstein will be proved right on that. Though, if so, it has certainly been quite a useful error. On this July day we spoke deeply. As usual, we spoke German. Einstein was quite receptive. Though he had rarely thought about nuclear chain reactions before, within 10 minutes he grasped the situation. He understood the meaning of a chain reaction scientifically, remarking that for the first time in history, men would tap energy from a source other than the sun.
Leo Szilard. Einstein was willing to assume responsibility for sounding the alarm, even though it was quite possible that the alarm might prove to be a false alarm. The one thing that most scientists are really afraid of is to make a fool of themselves. Einstein was free from such a fear. And this, above all, is what made his position unique on this occasion.
Eugene Wigner. Einstein realized the political and military meaning of nuclear fission, that it could yield explosives strong enough to make the Nazis invincible. And Einstein was just as horrified as I was by that prospect. He volunteered to do whatever he could to prevent it.
Leo Szilard. This story shows that we were all green. We did not know our way around in America. We did not know how to do business, and we certainly did not know how to deal with the government.
Herbert L. Anderson. Szilard acted on a suggestion from Gustav Stolper, a Viennese economist and friend of long standing. He went to see Alexander Sachs, a Lehman Corporation economist, reputed to have ready access to the White House.
Leo Szilard. Stolper telephoned Dr. Sachs, and I went to see him, and I told him my story. Sachs said that if Einstein were to write a letter, he would personally deliver it to President Roosevelt, and that he thought that it was no use going to any of the agencies, the War Department, or any of the government departments, because they would not know how to handle this. This should go to the White House.
Alexander Sachs. I felt it was essential that an opinion should be written by the one man whom the world recognized as the preeminent scientist of our day. Not only the preeminent scientist, but one of the greatest humanitarians, because he had left Nazism. He had anticipated the trend of events.
Herbert L. Anderson. The best approach was to go directly to the top.
Leo Szilard. This sounded like good advice, and I intended to follow it. In the meantime, Teller had arrived in New York, and I asked Teller to drive me out to Long Island. He had a car. Edward Teller. In early August, he asked, "Could you drive me to the end of Long Island to see Einstein tomorrow?" Szilard accomplished the extraordinary, but he had not learned to drive. Unfortunately, Szilard knew only Einstein's general whereabouts, not his address. Once we were in the right neighborhood, we began inquiring about the famous professor, with no result. Finally, we asked a little girl with long braids, about 8 years old. She had never heard of Professor Einstein, but she knew a nice old man with long white hair. We were, she told us, almost in front of his house. Leo Szilard. Teller and I discussed with Einstein this new approach of writing to the president. Einstein was perfectly willing to do this. We discussed a little bit what should be in this letter. I said I would draft it, and send Einstein perhaps 1 or 2 drafts for him to choose. I prepared a long draft and a short draft.
Janet Coatsworth, secretary to Leo Szilard. I was quite young when I worked as a secretary, but he was always very patient with me. He was dictating one day in 1939, and he mentioned a dreadful weapon, and he also said something about writing to the President of the United States. That convinced me. I was sure I was working for a nut. A nice nut, but a nut. I am quite certain he was aware of this most unflattering judgment of mine, for he began to look very amused, and his face took on a look of absolute mischief and merriment.
Leo Szilard. We did not know just how many words one could put in a letter which a president is supposed to read. How many pages does the fission of uranium rate? So I sent Einstein a short version and a longer version. Einstein thought the longer one was better. Edward Teller. Einstein read the letter with great care. Einstein signed the letter, and we left.
Albert Einstein. Letter to President Franklin D. Roosevelt. Some recent work by E. Fermi and L. Szilard, which has been communicated to me in manuscript, leads me to expect that the element uranium may be turned into a new and important source of energy in the immediate future. Certain aspects of the situation which has arisen seem to call for watchfulness, and if necessary, quick action on the part of the administration. In the course of the last 4 months, it has been made probable, through the work of Joliot in France, as well as Fermi and Szilard in America, that it may become possible to set up a nuclear chain reaction in a large mass of uranium, by which vast amounts of power and large quantities of new radium-like elements would be generated. Now it appears almost certain that this could be achieved in the immediate future. This new phenomenon would also lead to the construction of bombs, and it is conceivable, though much less certain, that extremely powerful bombs of a new type may thus be constructed. A single bomb of this type, carried by boat and exploded in a port, might very well destroy the whole port, together with some of the surrounding territory. However, such bombs might very well prove to be too heavy for transportation by air. In view of this situation, you may think it desirable to have more permanent contact maintained between the administration and the group of physicists working on chain reactions in America. I understand that Germany has actually stopped the sale of uranium from the Czechoslovakian mines which she has taken over. That she should have taken such early action might perhaps be understood on the ground that the son of the German Under-Secretary of State, von Weizsäcker, is attached to the Kaiser Wilhelm Institute in Berlin, where some of the American work on uranium is now being repeated.
No, Szilard. The letter was dated August 2nd, 1939. I handed it to Dr. Sachs for delivery to the White House.
Alexander Sachs. I saw it and waited for a proper opportunity to see the President. I felt the mere delivery of memoranda was insufficient. Our system is such that national public figures are punch-drunk with printer's ink. This was a matter that the Commander-in-Chief and the head of the nation must know. I could only do it if I could see him for a long stretch and read the material so it came in by way of the ear, and not as a soft mascara on the eye.
Eugene Wigner. Within 2 months, England and Germany were at war.
General Douglas MacArthur. On September 1, 1939, Hitler attacked and successfully overran Poland.
Stanislav Ulam. It was a very hot, humid New York night. I could not sleep very well. It must have been around 1 or 2 in the morning when the telephone rang. Dazed and perspiring, very uncomfortable, I picked up the receiver, and the somber, throaty voice of my friend, the topologist Witold Hurewicz, began to recite the horrible tale of the start of war. Warsaw has been bombed. The war has begun, he said. At that moment, I suddenly felt as if a curtain had fallen on my past life, cutting it off from my future. There has been a different color and meaning to everything ever since.
Otto A. Frisch. Hitler had been presented with an ultimatum, asking him either to withdraw his troops from Poland or to consider himself at war with Britain. We all sat round the radio, and there was a great feeling of tense sobriety when we were told that the deadline had passed and that the war was on.
Luis Alvarez. War came to Europe and changed all our lives.
Alexander Sachs. I brought the material over to President Roosevelt and met with him on October 11th, 1939. The President remarked, "Alex, what you are after is to see that the Nazis don't blow us up." I said, "Precisely." He then called in military aide General Edwin Watson, lovable Pa Watson, and said, "This requires action." General Watson went out with me, and the informal group was established.
Edward Teller. Roosevelt acted at once. The President set up an advisory committee on uranium and appointed D. Lyman Briggs, the head of the Bureau of Standards, its chairman. Briggs called a meeting for October 21st.
Eugene Wigner. The first meeting I attended at the National Bureau of Standards was in Washington, D.C. on October 21, 1939. Early in the meeting, Szilard pointed out that making a chain reaction would require money to perform experiments and to acquire uranium supplies and graphite. Szilard also suggested creating a permanent committee between the physicists and the government. Teller and I supported Szilard. The colonels kept rather aloof. I had the feeling that these soldiers and government men were just like the others I had approached. They were friendly, they smiled, but they never expected to see a working atomic bomb in this world.
Leo Szilard, the Washington meeting was followed by the most curious period in my life. We heard nothing from Washington at all. I had assumed that once we had demonstrated that in the fission of uranium neutrons are emitted, there would be no difficulty in getting people interested. But I was wrong. It is an incredible fact in retrospect that between the end of June 1939 and the spring of 1940, not a single experiment was underway in the United States which was aimed at exploring the possibilities of a chain reaction in natural uranium.
Arthur Holly Compton. The failure of the appeal of Einstein and his associates hinged on the fact that research in new fields of science had not been recognized by the United States government as a significant source of national strength. There was at Washington no individual or office having power to deal adequately with a new scientific development whose importance, though urgent and vital, was ill-defined. It was simply not in our tradition. The truth is that our government, like its citizens, even in late 1939, had hardly begun to ready itself for war.
Edward Teller. During that academic year, the fission research at Columbia developed slowly. I was uncertain whether I wanted to remain a bystander or become a participant. I was content and pleased with the way my small world was running. Although I was happy in academia, the possibility of the new weapon made me worry. In early May 1940, together with a few thousand other scientists, I was invited to attend a Pan-American Congress at which President Roosevelt was to speak. 2 days before the meeting, the phony war turned into a fast-moving conquest. Using modern tanks and dive bombers to prepare the way, the Nazi armies swept triumphantly through Holland, Belgium, and Luxembourg. The Nazi Blitzkrieg, the lightning strike war, was terrifyingly effective. I decided to accept the invitation and hear the president. President Roosevelt talked that day about inherent human rights and the blessings of democracy, and about the progress made through science and technology in conquering disease and poverty. Then he became more specific about the war.
Franklin D. Roosevelt, President of the United States, address before the 8th Pan American Scientific Congress, Washington, D.C., May 10, 1940.
You who are scientists may have been told that you are in part responsible for the debate of today because of the processes of invention for the annihilation of time and space. But I assure you that it is not the scientists of the world who are responsible, because the objectives which you have looked to, all of those objectives have been headed toward closer and more peaceful relations between all nations through the spirit of cooperation and the interchange of knowledge. The great achievements of science, yes, and of art, can be used in one way or another to destroy as well as to create. They are only instruments by which men try to do the things that they most want to do. Can we continue our peaceful construction if all the other continents in all the world embrace, by preference or by compulsion, a wholly different principle of life? No, I think not. Surely it is time to use every knowledge, every science that we possess, to apply common sense, and above all, to act with unanimity and singleness of purpose. I am a pacifist. You, my fellow citizens of 21 American republics, are pacifists too. But I believe that you and I, in the long run, and if it be necessary, will act together to protect, to defend, by every means at our command, our science, our culture, our American freedom, and our civilization.
Edward Teller. Seated in the crowd of thousands that day, I had the peculiar feeling that the President was speaking directly to me. Perhaps that is what is meant by charisma. But I also suspected that, out of all those present, the President and I were probably the only people who associated using every knowledge, every science we possess, with the race for the atomic bomb. Roosevelt's speech resolved my dilemma. I was one of the fortunate, helped to escape from the Nazi threat. I was now enjoying the comforts and many benefits of living in a democracy. I had the obligation to do whatever I could to protect freedom. Not long after Roosevelt's address, I went off to give a Sigma Pi Sigma lecture series. While I was traveling from campus to campus, the Nazi armies were sweeping through France. Every day the situation looked more terrible. The brave resistance at Dunkirk provided the only little spark of hope. But in the midst of the Nazi victory, I hardly noticed it.
Vannevar Bush. Germany swept across France, conquered it with ease, and nearly trapped the whole British army. Russia stood aside to wait for the rest of Europe to exhaust itself and then to pounce. Nazi submarines threatened to cut off Britain's food supplies and starve her out. Hitler's might have been vastly underestimated. It looked as though later we might face alone a Nazi enemy master of all the production facilities of Europe, allied with Japan to conquer the world, and in a fair way to do it.
Senator James F. Burns, Democratic U.S. Senator from South Carolina.
Burns held a variety of key top positions through the Roosevelt and Truman years. At the start of the war in Europe, he was in the Senate, but he was nominated to the Supreme Court in 1941, then left in 1942 to aid the war effort, spending the duration as first the Director of the Office of Economic Stabilization and later the Director of the Office of War Mobilization from 1943 to 1945. In 1945, in the final month of the war, Harry Truman nominated him to be Secretary of State.
It was the disaster at Dunkirk that at last aroused our people. Our hatred of war was at odds with our growing recognition that the conflagration was creeping ever closer to our shores.
Vannevar Bush. We were all drawn together early by one thing we deeply shared: worry. We were agreed that the war was bound to break out into an intense struggle, that America was sure to get into it one way or another, sooner or later, that it would be a highly technical struggle, that we were by no means prepared in this regard.
Arthur Holly Compton. The government's unpreparedness for handling uranium research was one of several examples that shocked certain members of the National Academy of Sciences into action. At their suggestion, President Roosevelt created the National Defense Research Committee.
Vannevar Bush. The National Defense Research Committee was launched on June 27, 1940, over a year before we entered World War II, as a civilian organization of scientists and engineers for the purpose of developing new weapons for military use.
Laura Fermi. Why were the persons acting this drama all foreign-born? In Italy, I reflected, universities are government-controlled. A channel between universities and government is always in existence and does not need to be opened. These people, these Hungarian, German, and Italian-born, knew the organization in dictatorial countries. It occurred to them that there might be ties between research and military applications, that in Germany all scientific work might have been enrolled in the war effort. In the face of a national emergency, totalitarian regimes are more efficient than democracies, at least during the first stages of the game. They are better equipped. A dictator holds in his hands all the strings and can pull them and mobilize the country at a moment's notice. A democracy has either no strings at all or long pieces of red tape.
Emilio Segre. Fermi used to say, whenever somebody bragged about his pilgrim ancestry, or when he heard about the daughters of the American Revolution, that he and other newly arrived refugees were the true new pilgrims, who understood and appreciated some American ideals better than the American-born.
Alexander Sachs. One great advantage that we had was that these refugees, these scientists themselves, responded to that very spirit of freedom that brought the Pilgrim Fathers over here. They were saturated by ideas and motives which the regimented scientists could not have, and so the transplanted and the American scientists, if given the means, would make advances much faster.
Eugene Wigner. It was refugees from other parts of Europe who saw most clearly that a war was coming. We reported the menace to our adopted countries. Both in England and in the United States, we did all we could to herald the danger and to alert those in power.
The Maud Committee. While nuclear fission research stalled in the U.S. and war began in Europe, other scientists in the United Kingdom continued to calculate the possibility of a bomb and worriedly advocated for action, even as they similarly struggled to navigate unfamiliar government bureaucracies.
Otto R. Frisch. Back in Copenhagen, I did some experiments which gave the first physical, not chemical, evidence of fission. But on the whole, I felt, as I wrote to my mother, like a man in the jungle who finds he has caught an elephant by the tail and does not know what to do next. The idea clearly opened fascinating vistas, but I did nothing about it. Threat of war had become palpable in the spring of 1939, and I did not feel like starting any new work that might soon be stopped. Having left Germany because of Hitler's race laws, and believing that Denmark was now in danger of invasion, I felt that I had better go elsewhere. I gratefully accepted an invitation from Mark Oliphant, head of the physics department of the University of Birmingham, to visit him during the summer of 1939 to discuss what had best be done. We were still discussing when war was declared, and I stayed.
Rudolf Piles. Quite soon tribunals were set up to classify all enemy aliens into 3 categories. Those in the first category were trusted and freed from practically all restrictions. The second category were those about whom too little was known and for whom the restrictions continued. And the third category were suspected of being enemy agents and were interned. We were placed in the first category.
Otto R. Frisch. After studying the theory of thermal diffusion, I decided to build a Clusius separation tube to produce a small sample of enriched uranium. This experiment was begun in an unused lecture room, because by that time all the laboratories in the physics department were being used for development work on radar. That was, of course, highly secret work to which I was not admitted, being technically an enemy alien. For my work, not much help could be offered, so my Clusius tube made slow headway and was finally abandoned. My friend and colleague, Rudolf Piles, had improved a formula first proposed by Francis Perrin for estimating the critical size of a chain-reacting assembly. That formula contained parameters such as the fission cross-section and the number of neutrons emitted per fission, which were hardly known at the time. I had to make guesses which were over-optimistic, as I later realized, and was staggered to get the result that a couple of pounds of uranium-235 would be sufficient to make an atomic bomb.
Rudolf Piles. One day in February or March 1940, Frisch said, "Suppose someone gave you a quantity of pure 235 isotope of uranium. What would happen?" We started working out the consequences. We had all the data to insert in my formula, and we were amazed how small this turned out to be. We estimated the critical size to be about a pound, whereas speculations concerned with natural uranium had tended to come out with tons. Our estimate turned out to be rather too low, but the order of magnitude was right.
Otto R. Frisch. We came to the conclusion that with something like 100,000 similar separation tubes, one might produce a pound of reasonably pure uranium-235 in a modest time, measured in weeks. At that point, we stared at each other and realized that an atomic bomb might, after all, be possible.
Rudolf Piles. We were quite staggered by these results. In a classical understatement, we said to ourselves, even if this plant costs as much as a battleship, it would be worth having.
Otto R. Frisch. I have often been asked why I didn't abandon the project there and then, saying nothing to anybody. Why start on a project which, if it was successful, would end with the production of a weapon of unparalleled violence, a weapon of mass destruction, such as the world had never seen? The answer is very simple. We were at war, and the idea was reasonably obvious. Very probably some German scientists had had the same idea and were working on it. A German scientist, Gustav Hertz, had been one of the first to separate isotopes, of neon, not uranium, in significant quantities, and the possibility was well known to the physics community.
Rudolf Piles. For all we knew, the Germans could already be working on such a weapon, and the idea of Hitler getting it first was most frightening. It was our duty to inform the British government of this possibility. At the same time, our conclusion had to be kept secret. If the German physicists had not yet seen the point, we did not want to draw their attention to it. Frisch and I sat down to write a memorandum stating our analysis and conclusions. It was written in two parts. One was technical and gave the arguments, and the other was non-technical and summarized the conclusions. We discussed radioactivity and the spread of radioactive fallout. We pointed out that use of this weapon would probably kill large numbers of civilians, and this may make it unsuitable as a weapon for use by this country. But as there was no effective defense other than the threat of retaliation with the same weapon, it would be worth developing as a deterrent, even if one did not intend to use it as a means of attack. We did not entrust this document to a secretary. We typed it up ourselves, or rather I did, because I had a typewriter and was familiar with it.
Otto R. Frisch. Piles and I went to talk it over with Oliphant.
Rudolf Piles. We did not know how to send a secret communication, or for that matter, where to send it.
Mark Oliphant. Piles and Frisch came to me in 1940. They convinced me that if the less prevalent isotope of uranium could be separated in a pure form, it might be possible to make a weapon.
Otto R. Frisch. He told us to send our report to Henry Tizard, who was advising the government on scientific problems concerned with warfare. That report was sent off within a couple of weeks, and was decisive in getting the British government to take the atomic bomb seriously.
Rudolf Piles. Tizard passed the paper on to G.P., later Sir George Thomson, who was the chairman of a committee concerned with the possibility of a nuclear chain reaction. The committee was about to disband itself. They saw no immediate prospect of success.
Mark Oliphant. The committee generally was electrified by the possibility of the Piles-Frisch memo.
James Chadwick. I was asked if I would take charge of the experimental work required to look into this matter. Of course, I said, yes.
Rudolf Piles. The name of the new committee was the Maud Committee, and that name had an amusing origin.
Otto R. Frisch. A telegram had been received from Niels Bohr, which ended with greetings to Maud Ray, Kent. Nobody had heard of such a person, and we all tried to read some subtle meaning into that name. We were all convinced that Bohr wanted to convey some secret message.
Rudolf Piles. This puzzle led to the suggestion of the name Maud Committee, or MAUD, to look more official. It was unfortunate that many people associated with it were convinced the letters stood for Military Applications of the Uranium Disintegration.
Otto R. Frisch. Much later, we learned that Maud Ray was an old friend of the Bohr family.
Rudolf Piles. I needed some regular help, someone with whom I would be able to discuss the theoretical technicalities. I looked around for a suitable person and thought of Klaus Fuchs. He was a German who as a student had been politically active as a member of a socialist student group, which was essentially communist, and had to flee for his life from the Nazis. In due course he got a full clearance and started work in May 1941. Fuchs became a lodger in our house, and he was a pleasant person to have around. His appointment did indeed provide me with support in the research work that was as efficient as I had hoped.
James Chadwick. I remember the spring of 1941 to this day. I realized then that a nuclear bomb was not only possible, it was inevitable. Sooner or later, these ideas could not be peculiar to us. Everybody would think about them before long, and some country would put them into action. I had nobody to talk to. The chief people in the laboratory were Frisch and Rotblad. However high my opinion of them was, they were not citizens of this country, and the others were quite young boys. There was nobody to talk to about it. I had many sleepless nights. I did realize how very, very serious it could be, and I had then to start taking sleeping pills. It was the only remedy. I've never stopped since then. I don't think I've missed a single night in all those years.
Rudolf Piles. It was decided to increase the resources necessary for this work and to set up an organization that could handle a larger project. The project received a new code name, Tube Alloys. It meant nothing, but sounded like a very dull but practical organization.
Robert Serber. The Maud Committee reported that a bomb could be built in 2 years, at a cost of £50 million.
Mark Oliphant. The minutes and reports of the Maud Committee had been sent to Lyman Briggs, chairman of a similar committee in the United States, and we were puzzled to receive virtually no comment. In 1941, I went to the United States on radar business and was asked to make discreet inquiries about this situation. I called on Briggs in Washington, only to find that this inarticulate and unimpressive man had put the reports in his safe and had not shown them to members of his committee.
Leo Szilard. Oliphant realized that something was very wrong and that the work on uranium was not being pushed in an effective way. He traveled across this continent, from the Atlantic to the Pacific, and disregarding international etiquette, told all those who were willing to listen what he thought of us. Considerations other than those of military security prevent me from revealing the exact expressions which he used.
One of the key stops Oliphant made during his cross-country Paul Revere-style warning trip was Berkeley, California, where Professor Ernest O. Lawrence had founded the Radiation Laboratory. Much of the RAD Lab, as it is known for short, centered around Lawrence's ever-expanding ambitions for a cyclotron, a massive magnet array that helped in atomic experiments. The University of California, Berkeley, which also hosted a theoretical physics division led by J. Robert Oppenheimer, had by the start of the 1940s become a central focal point for anyone interested in the atom.
Mark Oliphant. Amazed and distressed, I reported the situation to Vannevar Bush and James B. Conant, who were responsible for the application of science to a war in which America was rapidly becoming involved, although officially still neutral. Not satisfied with their response, I raised the question with Ernest Lawrence, inventor of the cyclotron and the most dynamic member of the Briggs Committee. He was deeply interested, and I am sure that it was his influence which led to a very rapid escalation of effort in America.
Arthur Holly Compton. Lawrence had come as a graduate student to the University of Chicago in the fall of 1923, when I began my work there as a young professor of physics. After he had gone to the University of California as professor of physics, Lawrence stopped one day in Chicago to show me his plans for a device that he called a cyclotron. This can be described most simply as an electric motor whose rotating armature is replaced by a revolving stream of atomic particles. When these particles gain enough speed, they fly out at a selected point in the periphery of the field magnets, forming a high-energy beam that is useful for many experimental purposes. I encouraged him to go ahead with its construction. Its success was remarkable, and the use of the cyclotron was of epical importance in nuclear physics. His radiation laboratory at Berkeley early became a mecca for nuclear physicists and chemists from all over the world.
Emilio Segre. Few machines were to be as productive of important discoveries in nuclear physics as the 60-inch cyclotron, which started working at the beginning of 1940.
Luis Alvarez. Ernest Lawrence's greatest invention was doing physics in cooperative teams. I was enormously stimulated by it.
Glenn Seaborg. Ernest Lawrence had been awarded the 1939 Nobel Prize for his invention of the cyclotron. Lawrence was off playing tennis. His secretary had difficulty convincing the people at the Berkeley Tennis Club that the message was worth calling him off the court to receive. Lawrence was not only the first Nobel winner at the University of California, but also the first from any state university in the United States. Major breakthroughs in science had traditionally come in Europe, especially Germany and England. When American scientists emerged, Harvard practically held a monopoly. It was one of the first steps in proving that we were building a public university that could compete with the best of the private institutions.
Arthur Holly Compton. Ernest Lawrence was also one of those who early showed his alertness to the need for American science to get ready for the military showdown between the Axis powers and the free world.
Ernest O. Lawrence. The Nazis have taken every advantage of modern technical developments, while the Allies have gone along traditional lines. I hope we will look at the problem of warfare scientifically. We need research and more research.
Roosevelt. If Congress knew the true history of the atomic energy project, I have no doubt, but that it would create a special medal to be given to meddling foreigners for distinguished services, and Dr. Oliphant would be the first to receive one. He discussed his concern with E.O. Lawrence, who in turn approached Compton, and as a result of this agitation, it was decided to reorganize the project.
Arthur Holly Compton. In early September of 1941, Ernest Lawrence called me by phone from Berkeley. Certain new developments made him believe it would be possible to make an atomic bomb. I made a date for Lawrence to see me in Chicago the following week when James B. Conant, president of Harvard University, was also to be there. It was a cool September evening. My wife greeted Conant and Lawrence as they came into our home and gave us each a cup of coffee as we gathered around the fireplace. Lawrence began by telling briefly of new results from England and how this work was confirmed by experiments in the United States. This work had convinced him of the feasibility of making an atomic bomb using only a few kilograms of fissionable material. He described recent Berkeley experiments, indicating that the bomb could be made equally well either with uranium-235 or with a new chemical element discovered in his laboratory, which was soon afterwards named plutonium.
Glenn Seaborg. Under normal circumstances, we would have rushed to publication to establish our claim to the discovery of a new element. But the war had changed everything. The world would not learn of the discovery for more than 4 years. At first, we gave the new element no name, simply referring to it as 94. But even that revealed too much for casual conversations around the faculty club or the lab, so we adopted the code name of Copper for element 94 and Silver for element 93. This code worked well enough through 1941, until some experiments required the use of some real copper, which we then referred to as honest-to-God copper. A year after its discovery, we finally named our new element. It was so difficult to make from such rare materials that we thought it would certainly be the heaviest element ever formed. So we considered names like extremium and ultimium. Fortunately, we were spared the inevitable embarrassment that one courts when proclaiming a discovery to be the ultimate in any field by deciding to follow the nomenclatural precedents of the two prior elements, uranium and neptunium. We briefly considered the form plutium, but plutonium seemed more euphonious. Each element has a 1 or 2 letter abbreviation. Following the standard rules, this symbol should be PL, but we chose PU instead. We simply followed the planetary precedent.
James B. Conant. Discoveries of fundamental significance had been made by American physicists largely working outside the official framework of the Advisory Committee. Using the atom smasher Lawrence had invented, the cyclotron, his associates in Berkeley had produced the hitherto unknown element number 94. It was christened plutonium. Before long, experiments with tiny amounts of material had confirmed what the theoreticians had surmised, namely that the new element, like one of the uranium isotopes, underwent spontaneous fission. Already, though hardly enough of the element had been manufactured to be seen, more than one physicist in the United States and England had begun to whisper that the large-scale production of plutonium might prove to be the essential step in a scheme for releasing atomic energy.
Arthur Holly Compton. The most critical problem in making a plutonium bomb was to establish a nuclear chain reaction that would supply the neutrons needed to make plutonium-239 from U-238. It was thus the idea of the plutonium bomb that gave military significance to the chain-reacting pile.
James B. Conant. Bush enlarged the National Academy Committee and asked for another review of the situation. The two new members of Compton's committee were the chemical engineer, W.K. Lewis, and a physical chemist who had transformed himself during the past year into the NDRC expert on explosives, Professor George B. Kiszczakowski of Harvard. Kiszczakowski was well aware of the research work on separating uranium-235, but had been thinking in terms of power. When I retailed to him the idea that a bomb could be made by the rapid assembly of two masses of fissionable material, his first remark was that of a doubting Thomas. "It would seem to be a difficult undertaking on a battlefield," he remarked.
George B. Kiszczakowski. I was brought in with a specific assignment of describing what would be the effect of an atomic explosion of several kiloton TNT equivalent force, which was, at that time, of course, an unknown quantity. I brought one of my young associates to do a careful survey calling together all of the information on accidental large, mostly industrial, explosions. Out of that, we plotted a scaling wall with the size of the damaged area as a function, an estimated size. I also described how explosives could be used to initiate the nuclear explosion. I described it as a case when you have the fissionable material in the middle and the explosives around it, and I said you just explode it so that it explodes symmetrically on all sides.
James B. Conant. A few weeks later, when we met, George's doubts were gone. "It can be made to work," he said. "I am 100% sold." My doubts about Briggs's project evaporated as soon as I heard George Kiszczakowski's considered verdict. I had known George for many years. I had complete faith in his judgment. If he was sold on Arthur Compton's program, who was I to have reservations?
Abraham Pais. Much has been written about Einstein's letters to President Roosevelt on the importance of the development of atomic weapons. Opinions on the influence of these letters are divided. It is my own impression that this influence was marginal. He only decided to go ahead with full-scale atomic weapons development in October 1941. At that time, he was mainly influenced, I believe, by the British efforts. In his later years, Einstein himself said more than once that he regretted having signed these letters. Had I known that the Germans would not succeed in producing an atomic bomb, I would not have lifted a finger.
Second Lieutenant R. Gordon Arneson, Staff Assistant for Atomic Energy, War Department. It was only when the British came up with their Maud Committee report, which said a bomb was feasible, that we got energized.
Arthur Holly Compton. I called our National Academy Committee together once more in Cambridge, Massachusetts in mid-October. Two major questions remained to be answered. First, how destructive would an atomic bomb be? Second, what would it require in time and cost to produce the bomb? I asked the theoretical physicists on our committee to solve the first problem. The second I put to the engineers. To neither of the questions were the experts willing to attempt an answer. After some discussion, I suggested a total time of between 3 and 5 years, and a total cost, assuming that only one method of producing U-235 or plutonium would be followed, of some hundreds of millions of dollars. None of the committee members objected. The time estimate was used in our submitted report. At the suggestion of Bush, the cost estimate was played down, lest the government should be frightened off. I have always been rather proud of these forecasts, considering the limited data. The actual time required was 3 years and 8 months. The cost of producing the plutonium used during the war was about $400 million. The total atomic bomb program used about $1,500 million by the end of the war, but this involved carrying through to production not one, but 4 methods for making fissionable material. I presented the report personally to Vannevar Bush on November 6, 1941. We spent an hour discussing its contents and what the next action should be. Bush took the report at once to President Roosevelt. In Bush's hands was also a report from the British that covered the same general ground. The British and American reports agreed that the bombs could probably be made, that they would be so destructive that they might well turn the tide of the war, and that this possibility was one of which the Germans were well aware.
James B. Conant. In the last days of November, Bush sent the report of Arthur Compton's committee to the President. This report was explicit about an atomic explosive. A fission bomb of superlatively destructive power will result from bringing quickly together a sufficient mass of element U-235.
Arthur Holly Compton. The first steps toward getting the atomic program underway had already been worked out between Vannevar Bush and James Conant in agreement with the President's Committee on Top Policy. Conant was to head a small group given the name of the S1 Committee, which was to see that the investigations went ahead with all possible speed.
James B. Conant. The responsibility for the atomic business was taken out from the National Defense Research Committee and given to this special group, of which I was chairman, reporting to Bush.
Arthur Holly Compton. The members of the S1 Committee were Chairman Dr. Conant, Vice Chairman Dr. Lyman J. Briggs, Director of the National Bureau of Standards, to whom the President had originally delegated the government's responsibility for study of the field of atomic energy, Dr. Edgar V. Murphy, Director of Research for the Standard Oil Development Company of New Jersey, Ernest Lawrence, Harold Urey, and myself. After the meeting of the committee, I went with Bush and Conant to lunch at the old Cosmos Club.
James B. Conant. Compton was talking about producing a new element, plutonium, which had not yet been seen except in microscopic amounts. Yet it was proposed to produce large amounts of plutonium by the operation of a pile. The contents of the pile would then be put through a series of chemical reactions in order to separate the plutonium from the uranium. To my objection that the chemistry of the element was largely unknown, Compton replied that intensive research would produce the necessary knowledge.
Arthur Holly Compton. This was Saturday. I went from the luncheon table to my room and wrote out a preliminary plan of attack and an initial operating budget. Though devising the method for building the bomb was my most important assignment, it did not seem to call for first attention. If plutonium was to be made, we needed to get into action at once.
Laura Fermi. It was only on December 6, 1941, the day before Pearl Harbor, 3 years after the discovery of uranium fission in Germany, that the decision to make an all-out effort in atomic energy research was announced by Vannevar Bush, director of the Office of Scientific Research and Development.
Arthur Holly Compton. This was December 6th, 1941. The nation had yet one day of peace.
December 7th, 1941. Just as Germany's war in Europe began with Hitler's advances across Europe in the 1930s, Japan had been steadily advancing through Asia that decade as well, starting even earlier with the conquering of Manchuria in 1931. In 1937, Japan launched a full-scale war with China by invading the mainland. Its capture of the then capital, Nanking, in December 1937 was followed by the mass murder and rape of civilians. Perhaps upwards of 200,000 were killed in the Rape of Nanking, which presaged other brutal atrocities and war crimes as Imperial Japanese forces began a wider conquest across the Pacific. Through the summer of 1941, the still isolationist-minded U.S. had tried to navigate around becoming involved in the conflicts in either Europe or the Pacific. After years of heeding the isolationist political currents at home, Franklin Roosevelt found his hand forced by the surprise Japanese attack on Pearl Harbor, which killed some 2,400 U.S. personnel, destroyed much of the U.S. Pacific Fleet, and cleared the way for the Empire of Japan to sweep down across the Pacific to the very edge of Australia in the months ahead. The attack spurred the U.S. into war in a matter of days, and gave even more urgency to the efforts to research an atomic bomb.
Joseph C. Grew, U.S. Ambassador to Japan. In 1931 came their invasion of Manchuria. In 1937 came their invasion of China south of the Wall, and while their army eventually floundered in China due to the magnificent fighting spirit of Chiang Kai-shek, his courageous armies, and his determined people, nevertheless, the warfare which then ensued proved a practical training for the Japanese soldiers and sailors, who tirelessly developed and perfected the tactics they subsequently used in their landings and conquests to the south.
Robert Guérin, Tokyo correspondent, Havas News Agency.
Havas, originally founded in 1835 and the world's oldest news service, was relaunched and renamed after the French occupation by the Nazis as Agence France-Presse.
10 years of imperialistic expansion, marked by the conquest of Manchuria in 1931, the step-by-step invasion of northern, central, and southern China from 1937 to 1939, the first move against Singapore with the Tonkin invasion in 1940, and the occupation of Cochin China in 1941, led the Japanese war toward fusion with Hitler's war. It was entirely natural that the two should blend into a single world conflict.
Matsuo Kato, U.S. correspondent, Domain News Agency. In July, the Japanese army marched into Indochina. Convinced that the move into Indochina was to establish a springboard for a southern invasion, the United States on July 26, 1941, froze all Japanese assets in America, an action that had previously been taken against Axis Germany, and peace conversations were, for the moment, meaningless.
Henry C. Wolfe, war correspondent. A general war in the Pacific appeared imminent, but the United States matched Nippon's moves with several blitz moves of her own. We clapped an oil embargo on Japan and froze her credits in America. We incorporated the armed forces of the Philippines into the Army of the United States, and we made Lieutenant General Douglas MacArthur commander of the combined Filipino-American defense establishment.
General Douglas MacArthur. We began an 11th-hour struggle to build up enough force to repel an enemy. Too late. Washington had come to realize the danger. My orders from Washington were not to initiate hostilities against the Japanese under any circumstances. The first overt move in the Philippine area must come from the enemy.
Robert Guérin. For 6 months, nationalist propaganda whipped up by the German colony, exploited by the military clique, had violently assailed America and exalted Hitler's victories. The United States, said the newspapers, by imposing economic sanctions on Japan, depriving it of oil, scrap iron, loans, trade, was strangling Japan. America must reconsider its attitude, or Tokyo's patience would run out. Threats by General Hideki Tojo, successive waves of troop mobilization, civil defense drills, all clearly pointed to war.
Joseph C. Grew. When the Japanese militarists, committed absolutely to the course of conquest, took measure of their military resources and perceived the extent of democratic rearmament, they had to gamble. The gamble was heroic, but not that of a mere game of chance. Their well-planned campaigns southward were brilliant accomplishments.
Matsuo Kato. The shadow of Hitler's Germany hung heavily over Japanese official thinking. The military education of many officers of the army had been largely German-influenced, and pro-German sentiment was predominant in army circles as a result. The fact that Nazism was an ideal doctrine for a militaristic state made many of these same officers pro-Nazi also, and the pressure of the China War had made Japan a virtual military dictatorship long before she attacked the United States and Great Britain. Admiration for German military methods and emulation of them led Japan's military leaders into the error of believing that Germany would certainly be victorious in the European War, and that any course except to support her would be folly.
Nogi Harumichi, university student, Patriotic Students Alliance. Beginning in 1939, Hitler's newsreels were shown every day. When I played hooky, I always went to see them. I'd watch those stirring movies about Hitler and wonder, what's the matter with the Japanese army in Manchuria? Why can't they just annihilate the British or the Americans? Hitler took all of Poland and united it with Germany. Japanese youth at that time adored Hitler and Mussolini. and yearned for the emergence of a Japanese politician with the same qualities. We wanted decisive action.
Robert Guillain. It had mainly been Hitler's insistence and example that had pushed Tokyo into the war. The Japanese were dazzled by the early German victories, fascinated by Hitler, bewitched by the promise of the coming partition of the world. This ineluctable train of events coincided with a calculated, premeditated design. Japan was bursting with a desire to prove itself as much a world power as the Western countries of which it had so long been the docile, patient pupil. This Asian people was determined to force its way onto the stage of history by chasing the white race out of Asia. This was an old ambition, nursed since Japan's first contact with the Western world.
Matsuo Kato. After Japan's surrender, Lieutenant General Ryukichi Tanaka, former chief of the Military Administration Bureau, summarized in a newspaper article the Army's estimate of the military situation before Pearl Harbor. Germany was expected to smash Russia by the end of 1942. If Great Britain then capitulated to Germany, as seemed likely, the American people would lose their stomach for war. Therefore, Japan could anticipate victory by the end of 1942. Fantastic now, that hypothesis gave the Army the foundation of its political power. On the diplomatic side, Germany had convinced Matsuoka that the tripartite alliance could provide Japan with a means of neutralizing the United States in the Pacific.
Robert Guillain. The war against America was the coronation of 3 generations of effort that had already crystallized in war 3 times. In China in 1895, against Tsarist Russia in 1904, and World War I, which Japan entered in 1915. All this indicates that we must look beyond the logical causes of the Pacific War. Its true causes were basically emotional.
Masahachi Kikuchi, Officer Candidate, Imperial Japanese Army. We grew up in a world where everyone who was not Japanese was perceived as an enemy. Chinese, British, American. We were schooled to regard them all as evil, devilish, animalistic. Conflict was commonplace for our generation, from Manchuria onwards.
Second Lieutenant, Tominaga Shozo, 232nd Regiment, 39th Division, Imperial Japanese Army, based in central China. A new conscript became a full-fledged soldier in 3 months in the battle area. As the last stage of their training, we made them bayonet a living human. When I was a company commander, this was used as a finishing touch to training for the men and a trial of courage for the officers. Prisoners were blindfolded and tied to poles. The soldiers dashed forward to bayonet their target at the shout of, "Charge!" Some stopped on their way. We kicked them and made them do it. After that, a man could do anything easily. Everyone became a demon within 3 months.
Matsuo Kato. Although as early as September 1941, some members of the Japanese embassy staff were darkly predicting war, or at least a showdown, I was convinced throughout that war could be avoided. Renewed talks with President Roosevelt and Secretary Hull began at the White House on November 17, and by November 20 there was considerable hope that a solution might be reached. Secretary Hull's note of November 26, which stated the United States' position toward Japan, was called by the press the take-it-or-leave-it note. The November 26 note to the Japanese government should have made it obvious that there was no longer hope for the negotiations, but there still seemed not the slightest inkling in the embassy that war was to strike within a few days.
Robert Guillain. It is easy to see today what madness it was for Japan to attack the United States in December 1941, but I can attest that even at the time, there was not a single foreigner living in Tokyo to whom that folly was not glaringly evident. Not one of the foreign observers whose painful privilege it was to watch the march of events closely failed to foresee from the very first day that the disproportion between the United States and Japan must sooner or later lead to an American victory.
Edwin Nakasone, age 14, Oahu, Hawaii. December 7th, 1941. Mama and Papa asleep, the rest of the family asleep. I'm having breakfast. Our kitchen door faced the west.
There's a mountain range, the WWII range, and then there's a cut, the Kole Pass. I was watching it, eating my breakfast. I recall vividly my breakfast was Kellogg's cornflakes. We didn't have enough milk, and we didn't have too much in the way of icebox room, so a lot of time we were eating it with carnation milk. I see this beautiful formation of about 15 planes coming through Kole Pass, and they swooped down on Schofield Barracks and began strafing. They swooped up into the air and went after Wheeler Airfield. There again, in beautiful formation, they dove down, one after another, and I see little pellet-like things dropping down from the planes. And I said, "Oh my God, they're making a horrible mistake." I was of the opinion that this is the Navy playing war games against the Army and bombing Wheeler Airfield. I hear this boom, 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 and see all this debris going up. We're no more than 3 miles away, up on the heights looking down. I could see quite clear what was going on. I dashed outside, looked up, and there was a Zero fighter coming, no more than 2,000 feet at the most above in the air, and I see the great big red balls of Japan on both wings and the fuselage. I was most surprised. To this day, I still recall the Japanese pilot. The cockpit was open. He had his neckerchief around him, flowing out. He had the goggles on, and I still remember his face as he came roaring over our homes.
Private Russell McGurty, Gun Director, USS Arizona, U.S. Marine Corps. That morning at 07:55, I was getting ready for Liberty, getting cleaned up in the forward head. I felt a small thud like a water barge striking us, and I felt another thud like that. I discovered later it was bombs exploding. I went up on deck, and there were guys pointing up in the air at planes going overhead, and there were explosions over on Ford Island. General quarters sounded, and then machine gun fire, and our anti-aircraft guns came into action. The Japanese planes were swooping all around us, and I watched torpedo planes coming in low from across the harbor, heading toward Battleship Row. Then there was a really violent explosion in the front part of the ship, which caused the old Arizona to toss and shake. First the ship rose, shuddered, and settled down by the bow. We got to the deck, and it was chaos. There were charred bodies everywhere. The passageways were like white-hot furnaces.
Leonore Rickert, nurse, U.S. Navy, Pearl Harbor Naval Hospital. I was on duty on Sunday morning, December 7th. I looked over toward Ford Island and could see things blowing up and knew we had a problem. When the captain came to the ward, he said the Japanese were attacking. New patients were starting to come in, and they were burned from being thrown off the ships and into the water, where there was burning oil. They were terribly burned.
Captain Paul W. Tibbetts, Engineering Officer, 90th Squadron, 3rd Attack Group. On a Saturday, in the first week of December 1941, at Fort Bragg, North Carolina, we went up to fly attack missions over some ground troops as part of an Army maneuver. The next day, we flew back to Savannah. It was a reasonably sunny day, and I had tuned my radio to a station in Savannah. Suddenly, the music in my earphones ceased, and a voice broke in. A mile over the red clay earth of Georgia, I learned that the Japanese had bombed Pearl Harbor.
Edward Teller. Our closest friends that year, the Fermis, the Mayers, and the Urays, all lived outside New York City, in Leonia. Therefore, although we lived near the university, Michi and I did a considerable amount of commuting. One Sunday in December, Michi and I stopped to buy gas on our way to the Fermis. The gas station attendant was listening to a radio inside, and when he finally came out to the car, he told us that Pearl Harbor had been bombed. "Where is Pearl Harbor?" I asked. So it was that we learned that the United States was at war.
Frances Perkins, U.S. Secretary of Labor. It was shocking. There was terrific excitement. We sat down near the desk of the president. The president's pride in the Navy was so terrific that he was having actual physical difficulty in getting out the words that the Navy was caught unawares, that bombs dropped on ships that were not in fighting shape and not prepared to move, but were just tied up. I remember that he said twice to Knox, "Find out, for God's sakes, why the ships were tied up in rows."
Henry Stimson, U.S. Secretary of War, Diary, December 7th, 1941. When the news first came that Japan had attacked us, My first feeling was of relief that the indecision was over and that a crisis had come in a way which would unite all our people. This continued to be my dominant feeling, in spite of the news of catastrophes which quickly developed. For I feel that this country united has practically nothing to fear, while the apathy and divisions stirred up by unpatriotic men have been hitherto very discouraging.
General George C. Marshall, Chief of Staff, U.S. Army. A democracy has a very hard time in a war, particularly at the start of a war. They can never get ready in advance. The conditions are such that they are very susceptible to surprise action, and the arbitrary government like the Hitler government has every advantage in those respects. They are just bound to win at the start unless they are very, very stupid. Of course, in the end, if the democracy is a firm democracy, it builds up a power which outlasts the other, and the dictatorship bogs down. But it hadn't bogged down yet.
Commander Edwin Layton, Intelligence Officer, U.S. Pacific Fleet, Pearl Harbor. One final shock was in store for the President before the day came to a close. News arrived at the White House just before midnight that an air raid had wiped out most of the Philippines Air Force. It was a reprise of Pearl Harbor. The Japanese planes from Taiwan swept in well-coordinated waves to strafe and bomb Clark Field and the other airstrips north of Manila at lunchtime. General Louis Brereton's planes were swallowed like sitting ducks in a holocaust of exploding bombs and blazing gasoline. In less than half an hour, 3/4 of the fighters in MacArthur's command had been reduced to charred skeletons. At a single blow, it had removed our ability to strike back and guaranteed the success of the impending Japanese invasion of the islands.
Sergeant Paul Metro, Radar, 393rd Bombardment Squadron. The next day, President Roosevelt came on the radio to announce the declaration of war on Japan. 2 days later, Germany and Italy declared war on the U.S.
Tojo Hideki, Prime Minister of Japan. Radio address, December 8th, 1941. I am resolved to dedicate myself, body and soul, to the country, and to set at ease the august mind of our sovereign. And I believe that every one of you, my fellow countrymen, will not care for your life, but gladly share in the honor to make of yourself His Majesty's humble shield. The key to victory lies in a faith in victory. For 2,600 years, since it was founded, our empire has never known a defeat. This record alone is enough to produce a conviction in our ability to crush any enemy, no matter how strong. Let us pledge ourselves that we will never stain our glorious history, but will go forward. The rise or fall of our empire and the prosperity or ruin of East Asia literally depend upon the outcome of this war. Truly, it is time for the 100 million of us Japanese to dedicate all we have and sacrifice everything for our country's cause.
Scribe First Class Noda Mitsuharu, Clerk, Headquarters Combined Fleet, Imperial Navy. After the successful attack on Pearl Harbor, we sailors talked about the opportunities we might get. My dream was to go to San Francisco, and there head up the accounting department in the garrison unit after the occupation. All of us in the Navy dreamed of going to America.
Part 2. Imagining a Bomb. 1941 to 1942. Setting up the Met Lab. While the United Kingdom rejoiced that the U.S. had finally joined the war, the early months of World War II for the U.S. were dark. The Japanese Navy and Army marched down through the Pacific, defeating U.S. garrisons in the Philippines, taking Hong Kong, Singapore, and Burma, among many others, seizing island after island, virtually all the way to the edge of Australia. Spurred on by America's official entry into the war, the nation's nuclear physicists descended on Chicago to dive into the practical questions of a now suddenly all-too-serious effort to make atomic weapons a reality, and how to build and harness chain reactions. The new team in Chicago, headed by Arthur Holly Compton, grew almost as exponentially as a chain reaction itself. Just 45 strong in March, by June, The Met Lab boasted a staff of more than 1,200.
Arthur Holly Compton. The attack on Pearl Harbor was, from an immediate technical point of view, very well done. It was skillfully planned, executed with precision, and gave a crippling blow to our Navy. But from a broader military perspective, what a mistake! Its immediate effect was to unite all Americans toward the nation's defense. If we invited a scientist to take part in our project, his only question was whether it was this or some other branch of the war effort in which he could be more useful. Universities and business organizations gave us every possible cooperation. The war must be won.
Glenn Seaborg. It felt as if there was not a moment to waste. It's hard for anyone who didn't live through World War II to imagine the desperation and sense of impending doom that we felt. Hard to imagine that we believed that Germany and Japan could conquer the world.
Admiral Chester W. Nimitz, Commander-in-Chief, U.S. Pacific Fleet. We have taken a tremendous wallop, but I have no doubt of the ultimate outcome.
Vice Admiral William Bull Halsey, Jr., Commander, Carrier Division 2, U.S. Pacific Fleet. Before we're through with them, the Japanese language will be spoken only in hell.
Eugene Wigner. On December 8, 1941, the very day after the Japanese bombed Pearl Harbor and brought America directly into the war, I heard from Arthur Compton again. He told me that the uranium project was being reorganized.
Norman Hilberry, Associate Director, Chicago Met Lab. I was teaching at NYU, and Anne and I had gone into our first faculty party just before Christmas '41. Our babysitter called and told us a telegram had come. It was from Compton. Have important war job for you. Please report earliest possible moment. I got on the train and went to Chicago, PDQ. He told me what he could. I went to the Physical Society meeting to recruit and reported back to Chicago in January of '42.
Arthur Holly Compton. To make atomic bombs, fissionable material was needed, and this could be either of two kinds. One of these was uranium-235. That must be separated from its much more abundant isotope uranium-238 by a very difficult mechanical process. The other fissionable material was plutonium. This would be produced by a steady nuclear chain reaction with ordinary uranium, as a result of which a small fraction of the uranium-238 would be transmuted into plutonium-239. This plutonium would then be extracted chemically from the uranium. The prime problem was to find a way of producing some hundreds of pounds of uranium-235 or of plutonium.
Norman Hilberry. At that meeting, every reactor type was discussed.
Arthur Holly Compton. We reached the decision to pursue 4 parallel methods, 4 horses in a race. Ernest Lawrence used his radiation laboratory at the University of California as the Center for Development of Magnetic Separation of U-235. Harold Urey coordinated the gaseous diffusion studies at Columbia University. Evie Murphy was put in charge of the development of the centrifuge method, using the facilities of the Standard Oil Development Company's laboratory at Bayway, New Jersey, and cooperating with J.W. Beams at the University of Virginia. I had the task of developing a method for producing plutonium. The method of thermal diffusion was being developed by the Naval Research Laboratory independently of the S-1 committee. Though in one sense competing, these various groups were also cooperating closely.
Leona H. Woods, physics graduate student, University of Chicago. The next problem was to create the central laboratory. Columbia was a possible site, but Harold Urey's diffusion project was there and was expanding fast into the available university space. Instead, Compton decided on Chicago because he had access to laboratory facilities and office space at the University of Chicago, because housing was more available, and because Chicago was safer against military attack than were coastal cities. At that time, the Japanese Navy was unopposed in the Pacific. There was great fear of attacks on the West Coast, and there had been a German submarine landing on the East Coast of the United States.
John H. Manley, physicist. The work toward a chain-reacting pile, which had been going on at Columbia and at Princeton primarily, but at Chicago also, was being consolidated by Arthur Compton at Chicago in this newly named, deliberately to be misleading, metallurgical laboratory.
Eugene Wigner. Just as the sanitarium where I stayed as a child was not chiefly concerned with the sanity of its patients, so this metallurgical laboratory was not designed for metallurgy. The name disguised a laboratory that was trying to create a nuclear chain reaction. And not any nuclear chain reaction, but one of enormous power, which is quite a different thing.
Luis Alvarez. Arthur phoned me in Cambridge and asked me if I would come to Chicago to talk with him about a matter of great urgency. As soon as I could arrange air travel priority, I was there. In the course of my visit, Ernest Lawrence came to Chicago to try to persuade Arthur to move the PILE program to Berkeley. His argument was convincing. His radiation laboratory had support facilities for such a project and experience in the administration of large projects. Ernest and Arthur were scientific peers. I fitted in several rungs below them and felt a strong emotional attachment to each. I remember in particular my surprise at their behavior during a very long and decisive meeting in Arthur's bedroom. He had the flu and felt miserable. Ernest argued in favor of moving everyone to Berkeley. Arthur resisted, sensing that in Berkeley he would be reduced to a cog in Ernest's large machine. In all the years I had been Arthur's student, I had never seen him fight so hard for anything. The discussion between the two men became increasingly acrimonious. Arthur Holly Compton. Lawrence objected. You'll never get the chain reaction going here. The whole tempo of the University of Chicago is too slow. We'll have the chain reaction going here by the end of the year, I predicted. I'll bet you $1,000 you won't, he challenged. I'll take you on that, I answered, and these men are the witnesses. I'll cut the stakes to a 5-cent cigar, countered Lawrence. Agreed. Luis Alvarez. I was shocked. I'd never heard either Ernest or Arthur bet so much as a nickel on anything. Then they both looked at me, obviously embarrassed that I had heard these intemperate remarks and witnessed such uncharacteristic behavior. When they cooled down, they canceled the bet. That was unfortunate for Arthur. He would have won the bet with 3 weeks to spare.
Leona H. Woods. The metallurgical laboratory moved from Columbia University, where it had been initiated, to the University of Chicago in the early spring of 1942, bringing with it Nobel laureate Enrico Fermi and his colleagues Leo Szilard, Walter Zinn, Herbert Anderson, John Marshall, Albert Wattenberg, and several other experimental physicists who participated in the establishment of the first chain reaction, as well as future Nobel laureate Eugene Wigner and other theoreticians, such as Edward Teller and John Wheeler.
Herbert L. Anderson. The metallurgical laboratory acquired a great sense of urgency. It grew rapidly in size and number of personnel, and its work was classified. Fermi's little group of physicists was quickly outnumbered by the influx of many other groups: chemists to work out the chemistry of the fission products and the separation of plutonium, engineers to design the plants, metallurgists to fabricate uranium metal, and even doctors and biologists to study the effects of radiation and to recommend safeguards against such hazards.
Albert Wattenberg. When we went to Chicago, the original New York group was split into two main groups, one under Zinn and another under Anderson, and an appreciable number of additional people were brought in to work with us. Another group under Volney Wilson was in charge of the controls and instrumentation development. Before the war, Wilson understood what nuclear bombs would do, and he had been unwilling to work on the project. However, in the fervor created by the war, he decided he should work on the project.
Alvin M. Weinberg. Fermi's and Wigner's groups got along well. Fermi's aim was to show that a chain reaction was achievable. Wigner's aim was to design a large, high-power reactor to produce plutonium. Fermi's experiments provided the basic data on which Wigner's group based its designs for the big reactors.
Arthur Holly Compton. Typical of the necessary adjustments was that of finding living quarters for the people coming to Chicago. Until a housing office could be put into effective operation, my wife gave what help she could. She found rooms in a friend's home for Laura and Enrico Fermi and their 2 children until more permanent accommodations could be secured. Fermi's 2 assistants, Herbert Anderson and John Marshall, were installed in our older son's room in our home. My wife rallied the help of other ladies who knew Chicago to see that the newcomers would find schools for their children, locate convenience shops, and pick a suitable doctor or dentist. Working with project administrator Joyce Stearns, she arranged some simple parties where the incoming men and women could get acquainted. Rapidly, there developed a spirit of high group morale.
Eugene Wigner. 2 methods of fission were then known. The first was based on uranium-235, the rare isotope of uranium. The second was based on plutonium-239, a new element that could be produced in a nuclear reactor. The chief task of my group was to design a nuclear reactor. We felt sure that a nuclear chain reaction could be made and controlled. We even knew crudely what had to be done. To make a chain reaction producing plutonium, and to understand the separation of the plutonium and the dissipation of heat that the fission process produces.
Arthur Holly Compton. The way was now clear for our main task: to develop a method of producing some hundreds of pounds of plutonium.
Albert Wattenberg. One of the first things that had been established about fission was that several neutrons were emitted during the fundamental fission process. The concept for a self-sustaining chain reaction required that these neutrons be slowed down and made to collide with uranium so that more fission would result with the emission of more neutrons to sustain the reaction. The feasibility hinged on not losing too many of the neutrons and quantitatively understanding the various neutron loss processes.
John H. Manley. The months spent at the Met Lab were thrilling, hectic, and varied. One problem was to find materials to slow down neutrons. The main scheme was to use graphite.
Albert Wattenberg. The exponential piles that we had built at Columbia had given results indicating that even an infinite amount of material would not lead to a self-sustaining structure. This was mainly because of the impurities in the graphite. During the spring, some new graphite arrived, and the exponential piles we built and measured in Chicago indicated that it would be feasible, with a very great deal of material, to build a chain-reacting structure. Thus, it was very worthwhile to continue to get the better quality graphite and also to improve the quality of the uranium oxide that we were obtaining.
Leona H. Woods. If the uranium were in the form of metal, then less total material would be needed and the reactor could be smaller. By the time John Marshall arrived at Chicago, Szilard had obtained some small pieces of solid uranium metal somewhere, and with these pieces, John began to find out how to melt and cast uranium, using furnaces he built in 50-gallon oil drums lined with asbestos insulation. The metal casting work was transferred to John Chapman's laboratory at MIT. John and some other scientists from Chicago went to MIT, and in about 3 months had cast 6 tons of uranium metal in long rods of a few inches diameter, which they then sawed into lumps of a few inches long each, using a machine-driven hacksaw. The sparks that flew from the saw were dramatic.
Herbert L. Anderson. Planning for Chicago Pile No. 1 began early in July, as soon as it became evident that sufficient purified uranium and graphite would be delivered by November. Norman Hilberry had carried through a remarkably successful procurement effort.
Eugene Wigner. By July 1942, MetLab engineer Gail Young and I had rough plans for a great 100,000 kilowatt pile to be made of uranium lumps in a graphite cylinder 12 feet high and 25 feet around. It would be cooled by water. This design was further improved throughout the year and eventually became the basis of the nuclear reactor built in Hanford, Washington. The design that my MetLab group finally adopted for the nuclear reactor was a roughly cubic form, about 6 yards in each direction. We figured how to insert the uranium, how to remove it, and many other such things. It seemed as complex as designing a factory.
Alvin M. Weinberg. We were writing on a tabula rasa. Everything was new and untried. Discoveries came easily.
FDR's OK. Over the spring and summer of 1942, the first concrete plans required to create an atomic bomb began to come together. Or, more accurately, the first plans for future research that would lead to future specific plans that could lead to the necessary production of plutonium and uranium. Work proceeded on an ever-increasing number of parallel tracks as the still-developing team settled on the organizational structure for the work ahead, as well as the physical locations where production facilities would be built, and began to think in earnest about just how to build the bomb itself.
Norman Hilberry. We were told to prove that you could not make a bomb, that you could not get a chain reaction. The first deadline we faced was the May 15th meeting of the S1 committee in Washington when the budgets for the next year had to be put in. The intent had been, at that time, that the whole effort would be concentrated on the most promising project. We got the chemists working like mad on what the impurities were in these materials that Fermi was using, both in the graphite and in the oxide, and then try to estimate what could be done if these impurities could be eliminated. Compton went into that meeting and announced point blank that it would work. He put the numbers down. Here is what we have. This is what we know the impurities are. We know we can remove these thus and so, and we know we can remove these thus and so. There was no question about will it work.
James B. Conant. As news arrived during the early spring of 1942, Bush realized that sometime in May, decisions involving very large expenditures of money would have to be made. The uncertainties had been growing less as the results from various research projects kept coming in. New measurements enabled the theoreticians to estimate that the minimum amount of uranium-235 that would explode, the critical mass, if assembled rapidly, would be between 2.5 and 5 kilograms. Such quantities were quite different from 100 kilograms, which was the upper limit of the range of values estimated by the Committee of the National Academy of Sciences. The three program chiefs and I met with Murphy and Army Corps of Engineers Construction Commander General Wilhelm Steyer on May 23, 1942. After considering all the pros and cons, the group recommended to Bush that he ask the President to authorize a construction program based on the assumption that a start should be made in each of 4 ways to manufacture a bomb. These were 3 separate schemes: the electromagnetic, the gaseous diffusion, and the centrifugal, and the production of plutonium in a pile. We had in effect told Bush that since we could not decide on which of 4 horses to place our bet, all 4 should be kept in the race, though we thought they might be running neck and neck until the final lap.
Vannevar Bush. When I told Mr. Stimson that progress on the bomb had reached the point where a very large amount of money had to be spent for manufacturing facilities and so forth, I suggested to him that the Army take over at that point.
James B. Conant. The total construction cost we estimated at $80 million, and an annual operating cost as $34 million. The project, we believed, would yield a few atomic bombs by July 1st, 1944. I recall vividly the argument about the time schedule. Why nearly 2 years delay, I asked. Why is it not possible to speed up the construction? To which Murphy, speaking as an experienced chemical engineer, replied, I remember clearly the words he used, "Doctor, you can't spend that much money any faster."
Colonel Leslie Groves. Bush's recommendation was very clear that it was now time to put the work of constructing and of building the plants in the hands of the Army engineers.
General George C. Marshall. It fell to me to make the preparations and still do it with secrecy.
Arthur Holly Compton. Bush laid the evidence before the top policy committee of Vice President Wallace, Secretary of War Stimson, and Chief of Staff General Marshall. With their approval, the recommendation of Bush and Conant was brought to President Roosevelt on 17 June. The response was immediate.
Franklin Delano Roosevelt. Note to Vannevar Bush. VB. OK. FDR.
Vannevar Bush. One of the most extraordinary things of the war, of course, was that Stimson and Roosevelt backed atomic energy development without any hesitation, completely and fully. This was a courageous thing to do, because this development was unlike anything ever seen before. Usually, when you are undertaking a development, you can make one part of it and demonstrate that, or you can make a small-scale model and prove that the theory behind it is right. In the case of the atomic bomb, this was impossible. It could be tested only at full scale. Stimson and Roosevelt were backing something which was to them only some figures on a piece of paper calculated by physicists.
General George C. Marshall. I was rather amused at myself because as time wore on, these long statements that would come, that were filled with complicated procedures necessary in these matters and the technical terms involved, I spent so much time with the Encyclopedia Britannica or the dictionary trying to interpret what they said that I finally just gave it up, deciding that I never would quite understand it all. What I must understand was all the procedure concerned with getting this thing done.
James B. Conant. The first Army officer to be brought into the project on a full-time basis was Colonel James C. Marshall.
Colonel James C. Marshall, Army Corps of Engineers. On June 17, 1942, a Wednesday, I received a teletype from the Office of the Chief of Engineers directing me to report to the Chief of Engineers the next morning. On arrival in Washington, I went to General Steyer's office. He came out and said, "Okay, Mrs. Matheson, let me have the S1 file." He handed me, as I recall, about 5 sheets of paper, maybe 6, and I said, "Is this all there is?" He said, "Yes, read this first letter." There was a letter from Vannevar Bush to President Roosevelt dated a few days before. The letter contained 3 or 4 pages and stated the status of the art or science, whichever they wanted to call it, concerning atomic fission, a word which struck me just out of the blue. I had never heard of it before. The letter said that atomic fission was about ready to happen. Steyer says, "The White House has a fund of $200 million to be spent at the discretion of the President." He said, "Tomorrow you go over and tell Eugene Rybold, the Chief of Engineers, that you got a new job and that you need some money. Vannevar Bush's outfit over there at OSRD, Office of Scientific Research and Development, is running both. All of their contracts with the universities, laboratories, and others around the country are about to run out. They will run out June 30th. They must have money." Anyhow, after an hour or 2 of this and being told what my mission was for the next day, he handed me the papers. They were marked secret. He said, "Keep them in your possession." I said, "Is this all I get?" He said, "Yes. I will tell Rybold to issue orders forming a new district, making you district engineer. You report direct to this office."
Colonel Leslie Groves. Somervell and Steyer, without any discussion with General T.M. Robbins or myself, set up the Special Engineer District and selected for it Colonel Marshall. If they had talked to me about it, I would never have recommended Marshall for the job because he was just not fitted for it. He was too nice a fellow. He was too amenable to scientific advice, and he also was very set on building up a neat organization where everything fell into place. All the paperwork was completely handled, and all the rest of it. He did not have the physical strength to carry on such a thing.
Colonel James C. Marshall. I started out on finding the money the next day. Steyer says, "Go to Rybold and tell him you need $15 million and he is not to ask you any questions." So I go into General Rybold, a 3-star general at the moment, and said, "General, I am over here with orders from General Steyer to get a sum of money and you are not to ask any questions." He said, "How much do you want?" I said, "I want $15 million. He immediately reached for the telephone, said, "Get me Steyer on the phone. No, get me Somervell." "Bill, this is Rybold," he said. "I've got a crazy man here sitting at my desk who says he wants me to give him a check for $15 million and he won't tell me what it's for. What should I do?" I heard Somervell say, "Give him the money and quit asking questions." No one in the Chief of Engineers office, regardless of his rank, civilian or military man, could sign a check in excess of $5 million. So we had to get a first lieutenant from the finance department to come over and sign a treasury check for $15 million. I then walked over to 15th Street Northwest, somewhere up there where OSRD was at the time. Dr. Irvin Stewart, who was Bush's right-hand man, said, "I hope you have some money. You are supposed to be the man. We need $15 million in order to preserve the continuity of our contracts with University of Chicago, University of California, Berkeley, and so forth and so on. I handed him the check.
Colonel Leslie Groves. On June 18, immediately after receiving orders to set up his special district, Colonel Marshall had informed General Eugene Rybold, the Chief of Engineers, General Robbins, the Deputy Chief of Engineers and Chief of Construction, and me, the Deputy Chief of Construction, of his new assignment. He did not reveal many of the details of his work, but he did ask that we give him every possible assistance. When he first told us of his carte blanche instructions, Robbins and I were rather skeptical about how long it would be before his priority would be overridden by some other super important project. We had seen this happen before.
Lieutenant Colonel Kenneth D. Nichols. On Friday, June 19, 1942, Colonel Marshall unexpectedly called from Washington. "Come to see me Sunday morning in Syracuse about a very technical project," he said. "I can't tell you any more over the phone." Sunday morning, as I came into his office, he greeted me. "Nick, I am giving you 15 seconds to volunteer for a very important technical project or be drafted." After he had given me a very short description of the nature of the project, I didn't need the 15 seconds. With volunteering settled, Marshall handed me a large envelope that contained most of the top-secret information he knew about the new project. I was to read them in his presence.
Colonel James C. Marshall. I got Nichols transferred to me. He was a Ph.D. Even though it was in hydraulics, I thought I needed somebody who at least had a degree beyond a B.S.
With the work officially in the hands of the military, the scientists and personnel in the new project needed to begin building the infrastructure to support and develop their studies further, as well as what would surely be large production facilities to actually ready the uranium and plutonium for development of a possible bomb.
Arthur Holly Compton. One important question was where the various operations might be carried on. A place was needed, first of all, for setting up the experimental reactor. As my wife and I were horseback riding one Saturday afternoon with our friend George McKibben, a Chicago lawyer, we located a sequestered part of the Cook County recreational area that seemed suitable for the purpose. McKibben, of course, had no idea as to our objective, but when he saw our interest in this well-hidden region only 20 miles from the city of Chicago, he immediately put us in contact with the officials of the Cook County Forest Preserve. On the maps of the area, this site was called Argonne Forest.
Colonel Leslie Groves. The plan then was to concentrate all facilities required for the production of fissionable materials at a single site.
Arthur Holly Compton. Throughout the spring, we had been on the lookout for a site suitable for our plutonium production plant.
General George C. Marshall. We had to construct these huge plants which were going to be required and still try to do it in secrecy.
Arthur Holly Compton. Essential requirements were ample electric power, a good supply of water for cooling, a rugged terrain that would prevent an explosion in one portion of the plant from causing widespread disaster, adequate transportation, available labor supply, a climate that would permit winter construction, and preferably remoteness from the seacoast to make enemy attack more difficult. The Tennessee Valley fitted all these conditions except, surprisingly enough, that just at this time, because of the heavy demands of the new electrical industries that had moved into the area, there was little more power available than that needed to meet existing requirements. Thomas Moore, our chief engineer, Richard Doane, director of the metallurgical laboratory, and Norman Hilberry, associate project director, had gone to Knoxville early in May 1942. A day or two later, my wife and I appeared in Knoxville as if for a holiday at the Great Smoky Mountains. The others had already inspected several sites under guidance of officials of the Tennessee Valley Authority. I spent half a day with them going over the Clinch River territory. We reported to Washington that the Tennessee area was our choice.
Colonel Leslie Groves. That area seemed to meet all the requirements, and beyond that, it gave promise of being a pleasant place for the permanent operating force to live. This was most fortunate because we anticipated that many of the operating personnel would have to be imported, since the specialized skills we would need would be difficult to recruit locally.
Arthur Holly Compton. A month later, when the Army was assigned its responsibility, Colonels K.D. Nichols and J.C. Marshall inspected the sites again and confirmed our recommendation.
Colonel Kenneth D. Nichols. Marshall and I left for Knoxville the evening of June 30th to look at sites. During the 3 days we spent in Tennessee, we looked at 4 locations that met our primary requirements. Apart from having the TVA power and water, the location had the necessary isolation because the Clinch River provided a boundary on 3 sides, and a mountain ridge protected the north side. The area also had the necessary number of valleys and ridges to help isolate the separate plants from each other.
Colonel James C. Marshall. I figured if you're going to have a high-explosive plant in these valleys, they would be separated from each other, and in the case of an explosion, they would naturally go up rather than spreading out.
General George C. Marshall. In all these things, it was exceedingly difficult to keep them secret when you had to get at big money and build these great plants without explanation. I think only the fact that we were building so many of them diverted the public attention from these particular ones.
One of the biggest challenges of the summer of 1942 was imagining how a future atomic bomb, which had been proven on paper only, would actually function as an explosive device. To solve that particular piece of the ever-evolving puzzle, Compton enlisted the help of UC Berkeley's star theoretical physicist, the close colleague of Ernest Lawrence, and the professor who more than anyone in the 1930s had helped to establish the U.S. as a focal point of theoretical physics.
Leona H. Woods. Compton appointed J. Robert Oppenheimer to head a small theoretical group studying the physics of the bomb.
Arthur Holly Compton. I had met Robert Oppenheimer in 1927 when he was a member of the colony of American students of James Franck and Max Born at Göttingen. A specialist in the problems of nuclear physics, he was one of the very best interpreters of the mathematical theories to those of us who were working more directly with the experiments. I had also dealt with Oppie in some rather delicate negotiations involving a professional organization that, in some of its branches, had been infiltrated by communists.
Robbie. Oppenheimer understood the whole structure of physics with extraordinary clarity, and not only the structure, but the interactions between the different elements. Hardly any branch of physics was foreign to him. As well as theoretical physics, he also had a vast knowledge of experimental results and methods at his fingertips, and would continually amaze experimenters by his great knowledge of their own subject, in some respects exceeding their own, especially in fields of great current interest. It is therefore not surprising that he became an almost mythical figure, especially to experimenters.
Robert Serber. Oppenheimer's fascinating personality played a major part in his unique powers as a teacher. Oppenheimer's course in quantum mechanics was well established. Oppie, as he was known to his Berkeley students, was quick, impatient, and had a sharp tongue. Now, after 5 years of experience, he had mellowed, if his earlier students were to be believed. His course was an inspirational as well as an educational achievement. He transmitted to his students a feeling of the beauty of the logical structure of physics, and an excitement in the development of the science. Almost everyone listened to the course more than once, and Oppie occasionally had difficulty in dissuading students from coming a 3rd or 4th time.
James B. Conant. As an outstanding theoretical physicist, he had already helped Lawrence in designing the electromagnetic method of separating U-235. Now it was suggested that Oppenheimer turn his attention to the design of a bomb.
John H. Manley. Oppenheimer wanted help from someone with more experimental experience than he had, and he accepted the position on the condition that an assistant be chosen who would fill in this gap. I may note parenthetically that almost anybody would have had more experimental experience than Oppenheimer. He had essentially 0 laboratory experience. He was an outstanding theorist and did understand the laboratory techniques, but not as an operator. Anyway, I was Compton's choice.
Arthur Holly Compton. After a few weeks spent at Chicago in laying his plans and recruiting his key men, Oppenheimer called together in June 1942 at Berkeley, California, a group of the nation's most competent theoretical physicists. Their task was to figure out how the bomb might be made to explode and what its effect would be.
Hans-Peter. We met in Berkeley for the summer of 1942. We first thought it would be a very simple thing to figure out this problem, and we soon saw how wrong we were.
Emilio Segre. Hans-Peter, Robert Serber, Edward Teller, E.J. Konopinski, and two younger physicists, Stanley Frankel and Eldred Nelson, worked on this project. As they proceeded in their calculations, they needed more and more experimental data that had not been measured, and we tried to help them out as much as possible. At the time, such data were few and unreliable.
J. Robert Oppenheimer. We had an adventurous time. We spent much of the summer of 1942 in Berkeley in a joint study that for the first time really came to grips with the physical problems of atomic bombs, atomic explosions, and the possibility of using fission explosions to initiate thermonuclear reactions. After these studies, there was little doubt that a potentially world-shattering undertaking lay ahead. We also began to see how rough, difficult, challenging, and unpredictable this job might turn out to be.
Luis Alvarez. I remember a most interesting afternoon we spent together, during which time Oppenheimer told me for the first time the possibility of building a thermonuclear weapon. He told me in some detail of the scientific design as he then envisaged it, and pointed out how it would be triggered. As Dr. Oppenheimer pointed out to me, there was no apparent limit to the magnitude of the explosion.
J. Robert Oppenheimer. After our conferences were over, I went and reported to Compton, who was off on a summer holiday, about this aspect of it, as well as others.
Arthur Holly Compton. I'll never forget that morning. I drove Oppenheimer from the railroad station down to the beach, looking out over the peaceful lake. There, I listened to his story. What his team had found was the possibility of nuclear fusion, the principle of the hydrogen bomb. This held what was at the time a tremendous unknown danger. Hydrogen nuclei, protons, are unstable, for they could combine into helium nuclei with a large release of energy. To set off such a reaction would require a very high temperature. But might not the enormously high temperature of an atomic bomb be just what was needed to explode hydrogen? And if hydrogen, what about the hydrogen of seawater? Might the explosion of an atomic bomb set off an explosion of the ocean itself? Nor was this all. The nitrogen in the air is also unstable, though in less degree. Might it not be set off by an atomic explosion in the atmosphere? These questions could not be passed over lightly. We agreed there could be only one answer. Oppenheimer's team must go ahead with their calculations. Unless they came up with a firm and reliable conclusion that our atomic bombs could not explode the air or the sea, these bombs must never be made.
Creating the Manhattan Engineer District. The creation in the summer of 1942 of what was ultimately dubbed the Manhattan Engineer District gave new energy and structure to the sprawling exploration of atomic energy in numerous labs, most of which remained a theoretical exercise more than reality, as well as the official shorthand that history would remember the effort as the Manhattan Project.
Colonel Leslie Groves. The question of a name for the project came up. Toward the end of June, Reibold told us that the new establishment was to be called the Laboratory for the Development of Substitute Materials, or DSM. I demurred on the grounds of security, feeling that the name was bound to arouse curiosity. Reibold decided no change would be made. Before we parted, it was decided definitely to hire the Boston-based construction firm Stone & Webster as the overall architect-engineer managers.
The original contract for Stone & Webster imagined the firm would lead the $80 million construction efforts across the atomic project. But as the scope and complexity of the task ahead became clear, it instead became one partner among many.
Colonel James C. Marshall. Reibold insisted I open up a district headquarters right upstairs over him in the chief's office. I objected and I said, I'll have Nichols down here in Washington. I want to go to New York where I can get office space. You can't get office space here. If you're trying to hide something, you can hide it in New York City a lot easier than you can hide it in Washington. I leased floor by floor 8 or 9 floors in 261 Fifth Avenue down here at 29th Street.
Colonel Leslie Groves. On August 11, Marshall handed me the draft of a general order to be published that day, announcing the formation of the new district. In it, he used the designation DSM. I, again, objected to this term because I felt that it would arouse the curiosity of all who heard it.
Colonel James C. Marshall. I said, why not call it the Manhattan District? I'm in Manhattan. So, that was the Manhattan District.
Colonel Kenneth D. Nichols. Giving the project that name would focus attention away from the actual site of the plants. The Chief of Engineers issued Order Number 33 on August 13, 1942, setting up an engineer district without territorial limits to be known as the Manhattan Engineer District.
General George C. Marshall. The Manhattan Project was the name least liable to arouse some feeling of a mystery. We might have called it Hoboken, but we called it Manhattan.
In project parlance, the Manhattan Engineer District would refer specifically to the Army's atomic effort, while the Manhattan Project referred to the wider umbrella of labs, scientists, factories, and facilities across the nation that supported the effort. Mere weeks after the project was officially named, Colonel Groves found himself, most unwillingly, put in charge of it.
Vannevar Bush. When Steyer first recommended Groves's appointment, I said to Steyer that it wouldn't do at all. I was sure that Groves would get into trouble with the scientists. After some time, Steyer sat down with me again and he said, "Look, there isn't another man in the U.S. Army that can do this job with the skill that Groves would use. We'll have to appoint him. And then you and I'll have to sit on the lid to be sure that he doesn't get into trouble with the scientists."
Colonel Leslie Groves. One day in mid-September, a few minutes after I had finished testifying before a congressional committee on a military housing bill, I met Somerville outside in the hallway. He went on to say, "The Secretary of War has selected you for a very important assignment, and the President has approved the selection." My spirits fell as I realized what he had in mind. I did not know the details of America's atomic development program at that time, but because of the nature of my responsibilities, I knew of its existence and its general purpose. Though a big project, it was not expected to involve as much as $100 million altogether, much less than our total overall spending in a normal week. Magnitude aside, what little I knew of the project had not particularly impressed me. Later that morning, I saw Steyer at his office in the Pentagon. He confirmed my worst premonitions by telling me that I was to be placed in charge of the Army's part of the atomic effort. When I returned home that evening, I told my wife and daughter and wrote to my son, a cadet at West Point, that I had a new job, that it involved secret matters, and for that reason, was never to be mentioned.
Vannevar Bush. Steyer was right when he insisted that Groves was the man for the job.
Colonel Leslie Groves. Before I left, Steyer told me that General Marshall had directed that I be made a brigadier general, and that the list of new promotions would be out in a few days. I decided at once, and Steyer agreed, that I should not take over the project officially until I could do so as a brigadier. I thought that there might be some problems in dealing with the many academic scientists involved in this project, and I felt that my position would be stronger if they thought of me from the first as a general instead of as a promoted colonel. My later experiences convinced me that this was a wise move. Strangely enough, it often seemed to me that the prerogatives of rank were more important in the academic world than they are among soldiers.
Colonel Kenneth D. Nichols. Groves decided to establish his headquarters in Washington, at least initially. He soon found that the capital was the ideal place from which to work. He was able to stay in touch with the War Department and other government agencies, while also readily reaching out into the field.
Colonel Leslie Groves. The office out of which I was to control the Manhattan Project consisted of 2 rooms. As I consider Washington today, it seems incredible that these accommodations were as limited as they were. My secretary, Mrs. O'Leary, who was soon to become my chief administrative assistant, and I occupied 1 room. The only furniture added was one, and later another, heavy safe.
The most significant, and first, move Groves made as the new head of the Manhattan Project was to establish it as the nation's top priority endeavor, upgrading the mid-level war priority status the S-1 Committee's work had been operating under through the spring and summer.
Colonel Leslie Groves. The situation during the summer of 1942 was not promising for any operation that did not hold the very highest priority. Stone and Webster estimated at the time that the construction of a pilot plant for the electromagnetic separation process would take 11 months under an AA3 priority, the highest then available to the MED, yet the same job could be completed in 8 months if an AA1 rating were obtained. I did not see how we could possibly get the job done with nothing better than an AA3 priority, and I did not feel inclined to fail by default. It seemed quite simple to me. If ours was really the most urgent project, it should have the top priority. On September 19, I called upon Donald Nelson, the head of the War Production Board, and stated my views very simply, but most definitely. His reaction was completely negative. However, he quickly reversed himself when I said that I would have to recommend to the President that the project should be abandoned because the War Production Board was unwilling to cooperate with his wishes.
James B. Conant. The thing could have never been built unless Groves had been able to get such top priority.
Colonel Leslie Groves. Up to this time, I had asked no questions about the scientific difficulties and the probability of success in overcoming them because it was not necessary for me to know them in order to carry out my responsibilities, which had involved chiefly assistance, where wanted, to marshal in the site location and the procurement of land, equipment, and materials. Now, I was particularly concerned with determining to what extent our work would be based on real knowledge, on plausible theory, or on the unproven dreams of research scientists. Next, I wanted to know about the available supplies of raw materials.
Colonel Kenneth D. Nichols. Groves was horrified at the information I gave him.
Colonel Leslie Groves. In fact, I was horrified. It seemed as if the whole endeavor was founded on possibilities rather than probabilities. Of theory, there was a great deal. Of proven knowledge, not much. Even if the theories were correct, the engineering difficulties would be unprecedented.
Arthur Holly Compton. In his first review of the situation, Groves realized that the project needed immediate strengthening in its industrial phases. The first task was to get production in hand. Within 24 hours, Groves had made his own personal inspection of the Tennessee Valley area and had approved the selection of a site along the Clinch River. Steps were immediately initiated to take over the area of almost 80 square miles that became Oak Ridge. Here was established the headquarters of the Clinton Engineer Works, named for the neighboring old village of Clinton.
Colonel Kenneth D. Nichols. Receiving his star on the 23rd, Groves officially took charge of the project. That afternoon, he attended a meeting in the Secretary of War's office to decide on the form and makeup of the policy supervision of America's atomic bomb effort.
Vannevar Bush. Part of the plan for the Manhattan District, as I worked it out with Mr. Stimson, was the creation of a military policy committee. This consisted of myself as chairman, with Conant as my deputy, General Steyer, and Deputy Chief of Naval Operations for Materiel, Admiral William R. Purnell. It served as a sort of board of directors for General Groves. It met frequently, had no staff or secretary present, kept no formal records, but provided a point at which every important move could be discussed and closely examined. I know its existence helped Groves. No one who has not been placed in a post of heavy responsibility can realize what a lonesome feeling it is when there is no equivalent of a board present, and one reports to a chief who is rarely accessible.
Arthur Holly Compton. More clearly than the others of us on the S1 committee, Conant saw the magnitude of the operations that must be undertaken if atomic bombs were in fact to be of use in the present war. On a recent visit, he had expressed himself with vigor. "You are after elephants with a pea shooter. We must work on a larger scale if significant production was to come."
Colonel Kenneth D. Nichols. Despite his initial unhappiness with the assignment, once Groves fully took over the reins of the project, I never again heard him voice a single word of regret. Once in charge, he quickly moved to assume de facto control not only of construction, but also control of all research and development, operation of the plants, development of the bomb, and the military aspects of the project.
Eugene Wigner. What an interesting man Groves was. I must admit that many of my physicist colleagues quite disliked him. But I liked Groves. He was a boss in every sense of the word. General Groves had the body of a boss, too, really a quite striking physique. He was more than a little fat, and he must have known that he was. Groves was a dynamic leader who used his great brawn to effect.
Colonel Kenneth D. Nichols. General Groves is the biggest SOB I have ever worked for. He is most demanding. He is most critical. He is always a driver, never a praiser. He is abrasive and sarcastic. He disregards all normal organizational channels. He abounds with energy and expects everyone to work as hard or even harder than he does. Although he gave me great responsibility and adequate authority to carry out his mission-type orders, he constantly meddled with my subordinates. And if I had to do my part of the atomic bomb project over again and had the privilege of picking my boss, I would pick General Groves.
Captain Joseph Volpe, legal advisor, Manhattan Project. He was decisive. As a matter of fact, I learned one thing in my work with the general that I think stood me in good stead over the years, and that was once you decide, move on to something else. Don't worry about it, don't lose any sleep over it. Get on with the next task. And he had a great knack for that. As you know, he made some extraordinary decisions to build things that were not proven scientifically or technically.
Brigadier General Leslie Groves. I think it is important to realize that when I made scientific decisions, in case there are any questions that come in of not knowing all the theories of nuclear physics, which I did not, nobody else knew anything either. We were groping entirely in the dark.
Edward Teller. I heard about a pep talk our general had given when he visited Ernest Lawrence's laboratory in Berkeley. At its conclusion, he turned to Lawrence and said, "Professor, I expect success. Remember, your reputation depends on it." Nobel laureate Lawrence never blinked an eye. But after the meeting, he took the general to his favorite watering spot, Trader Vic's, for dinner. There, after they had enjoyed a few Mai Tais, Lawrence turned to Groves and said, "You know, General, my reputation is made. It is yours that depends on the outcome of the Manhattan Project."
Brigadier General Leslie Groves. On October 5, 1942, I paid my first visit to the metallurgical laboratory at the University of Chicago, where Arthur Compton and I spent the morning inspecting the laboratory facilities and discussing with a number of scientists the work on which they were engaged.
Alvin M. Weinberg. General Groves was introduced to the staff at a large meeting in the Eckert Hall lecture room. After being introduced by Arthur Compton, the general spoke for a few minutes. I cannot remember now what he said, but he made a bad impression on us. Too military in manner, somehow too overbearing. I never quite overcame the first impression, though in retrospect I must concede he did a remarkable job.
Brigadier General Leslie Groves. As the meeting was drawing to a close, I asked the question that is always uppermost in the mind of an engineer. With respect to the amount of fissionable material needed for each bomb, how accurate did they think their estimate was? I was horrified when they quite blandly replied that they thought it was correct within a factor of 10. My position could well be compared with that of a caterer who was told he must be prepared to serve anywhere between 10 and 1,000 guests. But after extensive discussion of this point, I concluded that it was simply not possible then to arrive at a more precise answer.
Colonel Kenneth D. Nichols. As a result of his visiting Chicago, Groves was aware for the first time of the size and difficulty of the project.
Brigadier General Leslie Groves. Up until this time, only infinitesimal quantities of plutonium had been produced, and these by means of the cyclotron, a laboratory method not suitable for production in quantity. And by quantity production of plutonium, I do not mean tons per hour, but rather a few thimblefuls per day. Even by December 1943, only 2 milligrams had been produced.
3 big decisions. Over the course of the fall of 1942, General Groves and the leaders of the now officially named Manhattan Engineer District made 3 foundational decisions that would shape the future arc and success of their project. Choosing the director of the effort to build the bomb, what would be known as Project Y, as well as the site of its main laboratory and its main contractor, a company best known at the time for its recent invention of nylon, the first synthetic polymer which had remade American fashion in the 1930s.
Colonel Kenneth D. Nichols. Some of the key scientists greatly underestimated the time and effort that would be required to develop the weapon. They saw no urgency in starting it because they thought it could be done in a few months with less than 100 men.
John H. Manley. The physics of an explosive chain reaction is really very different from the physics of the chain-reacting pile. In the latter, the pile has to operate on slowed-down or moderated neutrons, but not so in the chain reaction for a bomb. It must go fast and be propagated by fast neutrons. Otherwise, the reaction time would be so long that the material would simply expand, and you'd get a fizzle with no real explosive result.
Joseph O. Hirschfelder, physicist, University of Wisconsin. Their idea was to make the atom bomb in the form of 2 hemispheres of enriched uranium, using a miniature gun to shoot one of these hemispheres as a projectile into the other hemisphere, which served as a target. As long as these hemispheres were apart, the bomb was inert. When they came together, the enriched uranium sphere would exceed the critical mass and the bomb would explode. All of this seemed to them exceedingly simple and would require a staff of the order of 50 scientists and maybe up to 50 additional assistants.
Brigadier General Leslie Groves. Discussions with Arthur Compton, Conant, and Bush made it clear to me that these estimates were dangerously over-optimistic, and that the work should be started at once. A difficult question arose. Who should be the head of it? I had not before been confronted with this special problem, for the directors of the other laboratories connected with the project had been appointed before my arrival upon the scene.
Arthur Holly Compton. A person suited to head the unique task of devising and building atomic bombs needed unusual qualifications. A critical part of the job would be working out an adequate theory of the fission explosion. But experiments also would have to be done, and some of these would be extraordinarily difficult. What is more, this work would necessarily be carried out under conditions of almost unprecedented seclusion. The leader of this enterprise must be a person of such human understanding that he could keep a group of high-strung specialists working smoothly together while largely separated from outside contacts.
Brigadier General Leslie Groves. Although Oppenheimer headed the study group at Berkeley, neither Bush, Conant, nor I felt that we were in any way committed to his appointment as director of Project Y. I did not know Oppenheimer more than casually at that time. Our first meeting had been on October 8 at the University of California, when we had discussed at some length the results of his study and the methods by which he had reached his conclusions. Shortly afterward, I asked him to come to Washington, and together we had explored the problem of exactly what would be needed to develop the actual bomb.
Victor Weisskopf, physics professor, University of Rochester. It was an inspired, but by no means obvious choice. Certainly he was the central figure in nuclear physics. No other man commanded so much respect of his colleagues. But he never was director of a large research operation. He did not have what one calls administrative experience.
Brigadier General Leslie Groves. Oppenheimer had 2 major disadvantages. He had had almost no administrative experience of any kind, and he was not a Nobel Prize winner. Because of the latter lack, he did not then have the prestige among his fellow scientists that I would have liked the project leader to possess. The heads of our 3 major laboratories, Lawrence at Berkeley, Urey at Columbia, and Compton at Chicago, were all Nobel Prize winners, and Compton had several Nobel Prize winners working under him. There was a strong feeling among most of the scientific people with whom I discussed this matter that the head of Project Y should also be one. However, because of the prevailing sentiment at the time, coupled with the feeling of a number of people that Oppenheimer would not succeed, there was considerable opposition to my naming him.
Colonel Kenneth D. Nichols. On October 15th, Groves asked Oppenheimer to join us in Chicago to continue the discussion about the location and organization of the bomb lab. With many issues still remaining as the departure time for the 20th Century Limited approached, Groves invited Oppenheimer to join us on our way back to New York. After dinner on the train, the conversation continued in my small roomette, with Groves, Marshall, Oppenheimer, and myself crowded into the small space with no elbow room. Despite the close quarters and the late hour, the discussion proved most fascinating. It covered all aspects of setting up an organization, building the needed facilities for laboratories and housing, procuring scientific equipment, and dealing with such expected issues as recruiting scientists and confining them in a laboratory in a remote area, and whether the scientists should be commissioned as officers in the Corps of Engineers. When Oppenheimer left the train in Buffalo, there remained no doubts in my mind that he should direct the new lab despite the difficulties we would have in clearing him.
Brigadier General Leslie Groves. In a few weeks it became apparent that we were not going to find a better man, so Oppenheimer was asked to undertake the task. But there was still a snag. His background included much that was not to our liking, by any means. The security organization, which was not yet under my complete control, was unwilling to clear him because of certain of his associations, particularly in the past.
Colonel Kenneth D. Nichols. Before the war, Oppenheimer had become involved with left-wing or communist-leaning groups and had enjoyed friendships with known or suspected communists, including his brother Frank, his girlfriend, and his wife. While he had broken contacts with the questionable organizations once he began work on the bomb project, he retained many of his friendships. Even though the USSR was on our side, these contacts were considered to be security risks.
J. Robert Oppenheimer. I might well have appeared at the time as quite close to the Communist Party, perhaps even to some people as belonging to it. As I have said, some of its declared objectives seemed to me desirable, but I never was a member of the Communist Party. I never accepted communist dogma or theory. In fact, it never made sense to me. I had clearly formulated political views. I hated tyranny and repression, and every form of dictatorial control of thought. In most cases, I did not in those days know who was or who was not a member of the Communist Party. No one ever asked me to join the Communist Party.
Vannevar Bush. Groves took the matter up with Conant and me. We both knew Oppenheimer's history. Groves had looked it up very thoroughly, and we had quite a conference on it. We had the evidence of Oppenheimer's leftist tendencies, the question of whether his wife was inclined to be a commie, and the question of his younger brother, who is still more inclined to be. We also knew that Oppenheimer was highly respected by the scientists. Both Conant and I felt perfectly sure that the man was loyal. We went over all the angles of the thing, and then Groves made the appointment.
Brigadier General Leslie Groves. I have never felt that it was a mistake to have selected and cleared Oppenheimer for his wartime post. He accomplished his assigned mission, and he did it well. We will never know whether anyone else could have done it better, or even as well. I do not think so.
The choice of Oppenheimer to head Project Y would come to define the Manhattan Project in myriad ways, not least of which was Oppenheimer's subsequent influence on both the decision to build a centralized laboratory and, specifically, its location in the Southwest. Oppenheimer and Groves made a seemingly unlikely pair. A wisp-thin 38-year-old scientist, schooled in the Old World's and New World's most elite institutions, from Göttingen to Harvard, deeply rooted in the theoretical and academia. The other, a stout and exacting 42-year-old West Point grad, who had helped lead the construction of the Pentagon, the world's largest office building, and equally deeply rooted in the practicalities and proclivities of bureaucracies. But it would prove to be one of the most fruitful working relationships in the history of the U.S. government.
J. Robert Oppenheimer. We began to notice how very much needed doing, and how much the little laboratories were suffering from their isolation. There was supposed to be security, and the result was that people would not know what was going on anywhere else. Work was duplicated, and there was almost no sense of hope or direction in it. By the fall of 1942, Not only the theoretical people, but anyone who knew the experimental situation realized that this had to be pulled together. These were the considerations that led me to say to General Groves, who had by then been brought into the project as its head, that I thought a bomb laboratory was a good idea.
John H. Manley. The problem of liaison among all the groups was a fantastically difficult one. We couldn't, of course, use long-distance telephone. Our work was classified. Teletype connections that could carry classified messages were limited, and next to hopeless for trying to unsnarl experimental difficulties among these various groups. It didn't take very long for Compton and Oppenheimer and me to realize that we just couldn't run a railroad in this fashion and get anywhere in finding out the necessary properties of the materials from which to build a bomb.
Lieutenant Colonel John Lansdale, Counterintelligence Chief, Manhattan Project. We had originally planned to put this laboratory at Oak Ridge. That was the original purpose of the acquisition of so much of the land down there before we understood how big the project was going to be. Dr. Oppenheimer and various of his associates were quite strong in their feeling that the fastest and best progress could be made if we could find a place where the principle of compartmentalization, which we had adopted generally for the whole project, could be laid to one side. An isolated place where means of egress and ingress could be easily controlled and means of communication monitored. Lieutenant Colonel John H. Dudley, Manhattan Engineer, District Army Corps of Engineers. My first connection with this work was in the very pleasant fall weather of October 1942. I was borrowed from my district to travel around the West to locate a site for a mysterious installation. At that time, and in fact all the way through, I was not supposed to know its purpose. I was simply given a set of criteria to follow.
Colonel Kenneth D. Nichols. The initial criteria included a location more than 200 miles from any border or ocean, in a sparsely settled area with a rather mild climate, in a natural bowl surrounded by hills.
Edwin McMillan, physicist, UC Berkeley. Colonel Dudley said that he visited most of the small towns in the Southwest. He said he traveled thousands of miles on 2-lane roads.
Lieutenant Colonel John H. Dudley. 2-lane roads. 1 lane for the left wheels and 1 lane for the right wheels. When the going got tough, I switched to a Jeep, and when it got even tougher, I rode a horse.
Brigadier General Leslie Groves. Dudley confirmed our preliminary views that there were only 2 general areas that might be satisfactory. One would lie somewhere along the Santa Fe Railroad, in New Mexico or Arizona, while the other would be in California. While shielded by surrounding mountains against the chance of an accidental explosion, the teeming millions of Los Angeles County were too near for us to maintain the security we deemed necessary.
Lieutenant Colonel John H. Dudley. The best place I found that fitted the criteria was Oak City, Utah. It was a delightful little oasis in south-central Utah. The railroad was only 16 miles away over a nice, easy road. The airport was not too distant. The water supply was good. It was surrounded by hills, and beyond, there was mostly desert. However, I noticed one thing. If we took over this area, we would evict several dozen families, and we would also take a large amount of farm acreage out of production. I recommended to Colonel Marshall that we skip over Oak City to avoid these adverse effects. Instead, I suggested the second choice, Jemez Springs, New Mexico.
Colonel Kenneth D. Nichols. To confirm the choice, Dudley arranged for Oppenheimer and Edwin McMillan to meet him and Groves in New Mexico on November 16th.
Edwin McMillan. We were supposed to get horses, and Colonel Dudley was to meet us and ride the boundaries. We went up to Jemez Springs, and we met Dudley there.
Lieutenant Colonel John H. Dudley. Oppenheimer took one look at Jemez Springs and proceeded to change the criteria.
Colonel Kenneth D. Nichols. Despite his earlier enthusiasm, Oppenheimer, seeing the site for himself, found it unacceptable because the surrounding cliffs would give his people claustrophobia, and he refused to ask them to live in a house that had been previously occupied by a Mexican or an Indian.
Edwin McMillan. We were arguing about this when General Groves showed up.
Lieutenant Colonel John H. Dudley. On meeting us at Jemez Springs, Groves was unhappy that we did not have a site picked, so he asked Oppenheimer if there was something else around that had prospects. Oppie proposed Los Alamos as though it was a brand new idea.
Colonel Kenneth D. Nichols. In fact, as early as August 29th, the district engineer's office in Albuquerque had made inquiries about Los Alamos, and Dudley had visited it during his own search. Using the initial set of criteria, however, he had rated it a poor second to Jemez Springs.
Edwin McMillan. Oppenheimer said, well, if you go on up the canyon, it comes out on top of the mesa, and there's a boys' school there, which might be a useful site. We all got in cars. We went up to Los Alamos Ranch School.
Brigadier General Leslie Groves. In the hope of finding something more suitable, we drove over the mountains toward Santa Fe to look at a possibility suggested by Oppenheimer. As we approached Los Alamos, we came upon a boys' boarding school that occupied part of the area.
Edwin McMillan. I remember arriving there, and it was late in the afternoon. There was a slight snow falling, just a tiny drizzly type of snow. It was cold, and there were the boys and their masters out on the playing fields in shorts. This is really a place for hardening up the youth.
Sterling A. Colgate, student, Los Alamos Ranch School. The ranch school was established for boys to learn to ride and be, if not cowboys, at least highly educated cowboys, and have a feeling for the outdoors, and pack trips and riding a lot. And many sports, but not any team sports. The education here was extraordinarily intense. Quite frankly, because of the money that went into this ranch school, it was a rather expensive place, and you had to have reasonably wealthy parents, though there were a few scholarships. The quality of the teachers, the number in classes, and the intensity of the education was just beyond comparison.
Colonel James C. Marshall. It was on a mesa quite high, about 8,000 feet high, several thousand feet higher than Santa Fe.
Edwin McMillan. Soon as Groves saw it, Groves said, "This is it."
Brigadier General Leslie Groves. It was quite evident that this would be an isolated site, with plenty of room for expansion. The fact that there were already a number of buildings at Los Alamos, though nowhere nearly as many as we would ultimately require, meant that we could move in our first people at once and expand on that base. This would save us months in getting started. From the standpoint of security, Los Alamos was quite satisfactory. It was far removed from any large center of population and was reasonably inaccessible from the outside.
Colonel Kenneth D. Nichols. Groves immediately set into motion the process to acquire the school buildings and property.
Colonel James C. Marshall. We bought the whole school, the horses, the canoes, the skis, the tennis ranges, everything.
Sterling A. Colgate. About December that year, 2 men showed up at school, and we were required to say our yes sirs to a Mr. Jones, who was wearing a fedora, and to a Mr. Smith, who was wearing a pork pie hat. The names were obviously pseudonyms. Not only was everybody showing them great deference, but Mr. Jones seemed most uncomfortable every time someone referred to him by that name. The 4 of us who were seniors had studied physics. The pictures in our physics textbook made it easy for us to recognize Mr. Jones as Ernest Lawrence and Mr. Smith as Robert Oppenheimer. Furthermore, the discovery of fission had been big news. In fact, we were even aware of the idea of a chain reaction. Clearly, the school was about to be converted to a laboratory to work on a very secret physics project. Why else would top physicists be visiting a place out at the end of nowhere with no water, no roads, no facilities? What was really going on was obvious. We were secretly amused by the pretense.
Henry Stimson, letter to A.J. Connell, head of the Los Alamos Ranch School, December 1st, 1942. You're advised that it has been determined necessary to the interests of the United States in the prosecution of the war that the property of the Los Alamos Ranch School be acquired for military purposes. It is requested that you refrain from making the reasons for the closing of the school known to the public at large.
A.J. Connell. They did permit us, however, to finish the first half year by canceling the Christmas holidays and working right through until January 21st. Sterling, B., Ted, and Collier all graduated on January 22nd, having qualified for our diplomas and passed special college boards given in Santa Fe a few days before.
Sterling A. Colgate. Oppenheimer gave a superb talk at our commencement. He stood in front of the fireplace in the lodge and graced this project with a set of words that I wish were recorded. I have never seen them, but it was an extraordinary talk that he gave about closing the ranch school. He made us all realize the tremendous importance of what he felt was going to happen here. It was tried to impress on us that we shouldn't talk about what happened here, and certainly I never did.
John H. Manley. It wasn't very long after the Los Alamos site selection that Groves succeeded in getting the University of California to be the contractor to operate the new laboratory. Until 2006, this was the easternmost campus of the University of California, the Los Alamos campus in New Mexico.
Colonel James C. Marshall. Gradually, Nichols and I together got the word across to Vannevar Bush and Conant and all of the Nobel Prize people over there on these committees that this was a big engineering job, and that you could not take test tube experiments and these milli-microsecond things in minute quantities that Harold Urey and John Dunning and these people had been playing with. Nobody had any U-235.
Brigadier General Leslie Groves. I had begun to realize that we were involved in an enormously bigger undertaking than I had previously understood, and that it was unreasonable to expect Stone and Webster to carry the full burden of all the engineering.
Eugene Wigner. General Groves looked for a large industrial firm to perform much of this work.
Arthur Holly Compton. These tasks fit most closely with those of a diversified chemical industry concerned with large-scale production. The prime American industrial organization operating in this field was the E.I. DuPont de Nemours Company of Wilmington, Delaware.
Colonel Kenneth D. Nichols. At a meeting with Vice President Willis Harrington and Dr. Charles Stein, also a company vice president and distinguished chemist, Groves proposed that DuPont take over the entire plutonium project, not just working on the chemical process for separating out the plutonium.
Brigadier General Leslie Groves. During the following week, the top officials of DuPont discussed our proposal, and at their request, 8 of their key employees were permitted to visit the Chicago laboratory, where they went over the status and plans of the project with Compton and his associates, and received all available theoretical and experimental data.
Colonel Kenneth D. Nichols. Representing some of the best engineering and scientific talent in the company, the DuPont investigators, including Stein, Roger Williams, Thomas Gary, and Thomas Chilton, arrived in Chicago on November 4th and spent several days observing every aspect of the activities at the lab. After the group returned to the company's headquarters in Wilmington, DuPont scheduled a meeting to discuss their findings, and on the 10th I accompanied Groves to the conference in Wilmington.
Brigadier General Leslie Groves. On November 10, I went to Wilmington to see DuPont President Walter S. Carpenter. My purpose was to convince him that DuPont must take over the entire plutonium project. When I entered his office, I knew that I had a staggering proposal to put up to him.
Walter S. Carpenter. Our reaction at that time was that we were asked to take on a job about equivalent to perpetual motion. Recovering the power of the atom just seemed to be one of those things at that time which was just beyond all conceivable reach.
Crawford Greenwald, Assistant Director, Chemical Department, DuPont Corporation. There was no assurance that any of these elements would operate. There was no assurance that you could make a reactor run at the high power levels that were required to produce plutonium. There was no assurance that the plutonium, if produced, could be separated. There certainly was no assurance at that time that an atomic bomb could be made, even given the plutonium.
Walter S. Carpenter. Groves told us that President Roosevelt, Secretary of War Stimson, and General Marshall, Chief of Staff, all felt that this was a matter of the utmost urgency. He pointed out that victory in the war would go to the nation that solved the problem first.
Crawford Greenwald. I had my doubts. Like all these people were eminent scientists, but none of them were engineers, and the DuPont Company is being asked to undertake this major undertaking.
Brigadier General Leslie Groves. They pointed out that even in one of their own fields of specialization, they would not attempt to design a large-scale plant without the necessary data that could be accumulated only by a long period of laboratory research, followed by semi-works operation. For example, it had taken them many years to get nylon into mass production, yet the nylon process was simple compared to what we were asking of them.
Eugene Wigner. Resisting General Groves was never easy when he wanted something, and during the war it was nearly impossible.
Walter S. Carpenter. We had really no alternative but to go ahead.
Norman Hilberry. Boy, that bunch? You understood why DuPont was the company it was. They were the hardest-nosed, sharpest bunch of characters you ever ran into. DuPont took absolutely no responsibility for the basic science. That's yours, they said. We will take full responsibility for the engineering development, for the construction, and for the operation. The cut was clean. A straight, clean operation.
Dale Babcock, chemist, DuPont Corporation. In November of '42, Crawford called a few of us together and said, "I am going to describe to you people something that is heresy to chemists. We are going to make a new atom, on a scale of pounds per year. That new element is plutonium." To persons who were chemists all their lives, that was heresy, absolute heresy. In December, I was taken out of nylon and put on this development full-time.
Making the pile. While the Manhattan Engineer District started up, the scientists at the Met Lab in Chicago, under Arthur Holly Compton, worked to ready the first chain-reacting pile of uranium, the landmark step in all the bomb development work to come. The site of their groundbreaking experiments to create exponential piles was about as unlikely a venue for scientific breakthroughs imaginable. Underneath the west stands of the old football stadium at the University of Chicago's Stagg Field in a disused squash court.
Leona H. Woods. Between April and October, in the west stands, 18 stacks of graphite and uranium were built in various arrangements of lump size and distance apart, some including powdered metal and some including cast metal.
Albert Wattenberg. Slowly, our work progressed. The exponential piles built in August were a real turning point. They were the first exponential piles to indicate that one could build a self-sustaining nuclear chain reaction if one had an adequate amount of material.
Leona H. Woods. In late August, the pile experiments in the grimy halls under the west stands showed that, without a doubt, a lattice of graphite and uranium oxide lumps could be put together, which would chain react at a size realizable with the materials on hand. Furthermore, metal was beginning to be delivered from MIT, the inclusion of which would make the critical size of the chain-reacting pile somewhat smaller than if it were built only with oxide lumps in the lattice.
Albert Wattenberg. As experiments gave us information as to which were the best materials and the best geometry, and as the theoretical estimates became more reliable, more definite commitments were made to build an experimental pile which it was hoped would be self-sustaining.
Herbert L. Anderson. To make the best use of the material that would be available, it was decided to build the pile in a spherical shape and to make provision for substituting carbon dioxide for air within the structure. We decided to mount the pile on a cradle of wood timbers and to enclose the whole structure within a halon cloth tent.
Leona H. Woods. Sometimes Herb took me with him on his tour of the lumber yards on Chicago's South Side to buy large numbers of 4-by-6-inch timbers.
Herbert L. Anderson. I spent the summer contracting for an awesome number of 4-by-6-inch timbers. I remember the astonishment with which my inquiry was received at the Sterling Lumber Company, which became a main supplier.
Leona H. Woods. He also ordered a huge square rubber and canvas balloon to enclose the graphite and wood assemblage. The reason for this was that it might have become necessary to replace the air in the cracks between the graphite bricks with some other gas, say helium, in order to allow the chain reaction to occur, because air might absorb too many neutrons.
Herbert L. Anderson. For the balloon cloth enclosure, I went to the Goodyear Rubber Company in Akron, Ohio. The company had a good deal of experience building blimps and rubber rafts, but a square balloon 25 feet on a side seemed a bit odd to them. In wartime, a lot is done with no questions asked. I had good credentials and a high priority rating, and that was good enough for them. They built the balloon in short order to my specifications, suppressing a justifiable curiosity.
Leona H. Woods. There was no heat in the building because it was used for strenuous exercise, and heat was not needed. While the pile experiments of the type begun at Columbia were going on, the lack of heat didn't matter. But after September, when Chicago begins to feel winter set in, there is a penetrating cold under the stands. The boys and staff kept warm by hard work, but the guards had to stand around freezing.
Walter's Inn. To help, we tried charcoal fires and empty oil drums. Too much smoke. Then we secured a number of ornamental imitation log gas-fired fireplaces. These were hooked up to the gas mains, but they gobbled up the oxygen and replaced it with fumes which burn the eyes. The scientists and technicians could use physical activity to keep warm, but the security guards had to stand in one place at the entrance. The University of Chicago came to the rescue. Years before, big league football had been banned from the campus. We found, in an old locker, a supply of raccoon fur coats. Thus, for a time, we had the best-dressed collegiate-style guards in the business.
Herbert L. Anderson. For the construction of the pile, Fermi assigned the responsibility jointly to Zinn and me. Our two groups combined for a concerted effort. 2 special crews were organized. One machined the graphite, the other pressed the uranium oxide powder using specially made dies in a large hydraulic press. Both crews managed to keep their output up to the rate of the deliveries. A separate group under Volney C. Wilson was in charge of control and measuring devices.
Albert Wattenberg. As well as building piles and making neutron measurements, younger physicists such as myself would work with a crew of high school-age kids pressing the uranium oxide pseudospheres and would supervise the drilling of the holes in the graphite bricks. We must have had to drill over 40,000 holes about 3 1/4-inch diameter and with shaped bottoms in order to fit the pseudospheres of uranium oxide. The tough high school kids used for the production work had quit school to earn a little money while waiting to be drafted.
Herbert L. Anderson. In our report for the month ending October 15th, Zinn and I could state that 210 tons of graphite had been machined.
Albert Wattenberg. As well as measuring exponential piles, Zinn took charge of the machining of the graphite and the pressing of the uranium oxide. I feel that Wally Zinn's enormous contribution and cleverness in this project have not been adequately appreciated. Zinn really had a full grasp of the steps and processes needed to build a pile. He was exceptional at devising straightforward, reliable, and efficient solutions to an enormous variety of physics and engineering problems. With about 6 young physicists, 1 millwright, and about 30 kids who had dropped out of high school, he carried a major share of the physics measurements of the exponential pile program, and he machined all the graphite blocks and pressed the uranium oxide briquettes for those exponential piles and for the first self-sustaining pile. Zinn drove people hard. He obtained very high-quality work from them and also gave them a great deal of satisfaction in accomplishment.
Leona H. Woods. Where did the Manhattan District get the uranium that went into CP1, chain-reacting Pile 1? A strange but true tale is that it was thanks to the foresightedness of Edgar Songier, head of Union Minière, Katanga, a Brussels-based firm.
John Gunther. Probably not one American in 100,000 has ever heard the name Edgar Edouard Songier, nor is he well known in Europe outside of a limited circle. So far as I know, no photograph of him has ever appeared in an American newspaper or magazine of wide circulation. Edgar Songier is, in his field, one of the great unknowns of our time. This is all the more remarkable because it was Mr. Songier who made it possible for the United States to make the atomic bomb.
Colonel Kenneth D. Nichols. Initially, the scientists did not even have enough of the element for experimental purposes and had no real idea of how much we would need once the separation plants went into operation.
Brigadier General Leslie Groves. It is sobering to realize that but for a chance meeting between a Belgian and an Englishman a few months before the outbreak of the war, the Allies might not have been first with the atomic bomb. For the most important source of uranium ore during the war years was the Shinkolobwe mine in the Belgian Congo, and the most important man concerned with its operation was M. Edgar Songier.
Colonel Kenneth D. Nichols. The Shinkolobwe mine represented a freak occurrence in nature. It contained a tremendously rich load of uranium pitchblende. Nothing like it has ever again been found. The ore already in the United States contained 65% U3O8, while the pitchblende above ground in the Congo amounted to 1,000 tons of 65% ore, and the waste piles of ore contained 2,000 tons of 20% U3O8. To illustrate the uniqueness of Saint-Gier's stockpile, after the war, the MED and the AEC considered ore containing 0.3% as a good find.
Brigadier General Leslie Groves. In May of 1939, Saint-Gier happened to be in England, in the office of Lord Stonehaven, a fellow director on the Union Miniere Board, when Stonehaven asked him to receive an important scientist. This turned out to be Sir Henry Tizard, the director of the Imperial College of Science and Technology. He asked Saint-Gier to grant the British government an option on every bit of radium-uranium ore that would be extracted from the Shinkolobwe mine. Naturally, Saint-Gier refused. As he was leaving, Sir Henry took him by the arm and said most impressively, "Be careful, and never forget that you have in your hands something which may mean a catastrophe to your country and mine if this material were to fall in the hands of a possible enemy." This remark, coming as it did from a renowned scientist, made a lasting impression on Saint-Gier.
Arthur Holly Compton. Saint-Gier sensed that this uranium ore might be of military value.
Brigadier General Leslie Groves. Saint-Gier left Brussels in October of 1939 for New York, where he remained for the rest of the war. From there, he managed the operations of his company, both inside and outside the Belgian Congo. Toward the end of 1940, fearing a possible German invasion of the Belgian Congo, Saint-Gier directed his representatives in Africa to ship discreetly to New York, under whatever ruse was practicable, the very large supply of previously mined uranium ore, then in storage at the Shinkolobwe mine. In accordance with Saint-Gier's instructions, over 1,250 tons of uranium ore were shipped by way of the nearest port, Lobido, in Portuguese Angola during September and October of 1940.
Arthur Holly Compton. He ordered the ship laden with this ore to proceed to New York. There the ore was stored in a warehouse.
Captain Louis L. Strauss, U.S. Naval Reserve, Office of Naval Research. He had managed to divert to the United States some 2,000 steel drums containing about 1,200 tons of ore. These were stacked in the open at Port Richmond, Staten Island, New York, and plainly marked uranium ore, product of the Belgian Congo. They apparently excited no interest.
Colonel Kenneth D. Nichols. Early in 1942, while in Washington on other matters, he mentioned this stockpile to State Department officials concerned with international economic affairs.
Brigadier General Leslie Groves. As is now well known, the State Department was not informed of the atomic project until shortly before the Yalta Conference in February of 1945. Nevertheless, it is hard to understand why was Saint-Gier so insistent on the value of the uranium ore, and knowing that the ore contained radium, the State Department officials did not make a serious effort to determine the real value of the ores.
Colonel Kenneth D. Nichols. I first learned of Saint-Gier's supply of ore on September 7, 1942. Taken by surprise, I immediately began to ask about the stockpile. I visited Saint-Gier in his New York office on September 18th to discuss purchasing his stockpile. I found the Belgian a courteous gentleman in his 60s. He had a somewhat pallid face, and his light hair was thinning. He was immaculately dressed, and he spoke excellent English in rather curt sentences.
Brigadier General Leslie Groves. When Nichols opened the conversation, Saint-Gier was somewhat guarded in his reply, recalling how the State Department had consistently ignored his repeated proddings.
Edgar Saint-Gier. The colonel confirmed his credentials. I asked him when he would like to have the shipment, and he told me, right now. So I told him, I just happen to have 1,000 tons of ore stored right here in New York City.
Brigadier General Leslie Groves. He said, "Colonel, will you tell me first if you have come here merely to talk or to do business?" Nichols answered diplomatically, as always, that he was there to do business, not to talk.
Colonel Kenneth D. Nichols. Perhaps too flippantly, I answered, "Yes, I have more authority, I'm sure, than you have uranium to sell." After thinking about it for a moment, he demanded to know, will the uranium ore be used for military purposes? I hesitated. I didn't know what I should say to a foreigner about the country's most secret war project. Sanjier rescued me. "You don't need to tell me how you'll use it. I think I know. All I want is your assurance as an Army officer that this uranium ore is definitely going to be used for war purposes." I could, of course, give him that assurance. He replied, "Good. Then let's make a deal, Colonel."
Arthur Holly Compton. When Sanjier was assured on these 2 points, he immediately noted on a sheet of yellow paper the conditions of sale of the ore to the United States government.
Colonel Kenneth D. Nichols. The draft agreement contained only 8 sentences.
Brigadier General Leslie Groves. This was typical of the way in which a great many of our most important transactions were carried out. Once the seller understood the importance of our work, and there was no need to explain it in this case, he was invariably perfectly willing to deliver his goods or his services on our oral assurance that fair terms and conditions would be settled at a later date. We always promised that he would not be out of pocket for any expenses incurred if for some reason final agreement was not reached, and we always kept that promise.
Leona H. Woods. This ore went to the metals production plants and was converted into fuel elements in CP1. The 6 tons of metal arrived in time to be placed at the center of the pile. This more dense material allowed the pile to become chain-reacting at a smaller size than had been previously planned for.
Albert Wattenberg. After exponential pile number 18 was built, there no longer was any doubt for quite a few of us that we were building a chain-reacting pile. However, before we finished building the first self-sustaining pile, several incidents occurred which could have led to serious delays in our getting the job done.
Herbert L. Anderson. Around October 20th, labor difficulties arose.
Albert Wattenberg. We had planned to move the material to a new laboratory at the Argonne Forest near Chicago, but construction of the building was halted due to labor problems.
Herbert L. Anderson. It was clear that we would be ready to assemble the pile before the building was completed. Fermi became concerned about a serious delay.
Albert Wattenberg. The squash court under the west stands at Chicago, where we had been building all of our exponential piles, was just barely large enough to contain the chain-reacting pile.
Arthur Holly Compton. Early in November, Fermi came into my office. "I believe we can make the chain reaction work safely right here in Chicago." We discussed the matter back and forth until we were both satisfied. According to Fermi's calculations, which I carefully checked, we would be working under conditions that it should take some minutes for the reaction to double its power. If this proved correct, there would be ample time for adjustments, and the reaction would be under full control.
Brigadier General Leslie Groves. Several experiments carried out while the pile was under construction indicated that the chances of any untoward happening were very slight.
Arthur Holly Compton. The only reason for doubt was that some new, unforeseen phenomenon might develop under the conditions of release of nuclear energy of such vastly greater power than anyone had previously handled. We would also take whatever other precautions we could think of, even though these might appear superfluous. After all, the experiment would be performed in the midst of a great city. We did not see how a true nuclear explosion, such as that of an atomic bomb, could possibly occur. But the amount of potentially radioactive material present in the pile would be enormous, and anything that would cause excessive ionizing radiation in such a location would be intolerable.
Brigadier General Leslie Groves. If the pile should explode, no one knew just how far the danger would extend. Stagfield lies in the heart of a populous area.
Arthur Holly Compton. As a responsible officer of the University of Chicago, according to every rule of organizational protocol, I should have taken the matter to my superior. But this would have been unfair. University of Chicago President Robert Hutchins was in no position to make an independent judgment of the hazards involved. Based on considerations of the university's welfare, the only answer he could have given would have been no. And this answer would have been wrong. So, I assumed the responsibility myself. I told Fermi to go ahead with the critical experiment.
Brigadier General Leslie Groves. I learned then that nothing is harder for the man carrying the ultimate responsibility, in this case myself, than to sit back and appear calm and confident, while all his hopes can easily be destroyed in a moment by some unexpected event over which he has no direct control.
Herbert L. Anderson. On Monday, November 16th, we opened the rubberized balloon cloth envelope and started erection of the pile inside it. We organized into 2 shifts. Wally Zinn took the day shift. Mine was the night shift.
Leona H. Woods. At the doubles squash court under the West Stands at Chicago on November 14th, the balloon cloth was laid out on the floor, and the first layer of the graphite matrix supported on the 4x6-inch timbers began to be laid down.
Albert Wattenberg. A circle was drawn to indicate where the first graphite bricks should be placed, and the construction of the first chain-reacting pile began.
Leona H. Woods. We proceeded at a rate of somewhat more than 2 layers per day, and by November 20th, the 15th layer of the graphite uranium matrix was being laid.
Arthur Holly Compton. Not nearly enough uranium metal was going to be ready in time. The few tons that would be delivered were reserved for use near the middle of the pile, where their effect would be greatest. For the outer portions of the pile, uranium oxide, purified by Mallinckrodt Chemical Works, and now coming in sufficient quantity, would have to be used. This oxide we had to form, using a hand press, into compact lumps that could be built into the structure. The pile went up as rapidly as the materials arrived.
Herbert L. Anderson. There were no detailed plans or blueprints for the frame or the pile. Each day we would report on the progress of the construction to Fermi, usually in his office in Eckert Hall. There we would present our sketch of the layers we had assembled and indicate what we thought could be added on the following shifts. Since some of the graphite was of better quality than the rest, it was important to arrange its disposition carefully. Fermi spent a good deal of time calculating the most effective location for the various grades of graphite on hand.
Albert Wattenberg. From the middle of October until December 2nd, we were on a regime of about 90 hours of work a week. All we did was to work and sleep, and sometimes we didn't even get to eat meals. Sometimes we thought of why we were doing it. Several times we discussed what we would do if the Nazis won, where we would try to hide in the United States. We were fairly certain we would be killed if we were caught. One morning, very early, Dr. Alvin Graves came in. He was slightly older than the rest of us, and wanted to take over what I was doing, although he wasn't due in until late that afternoon. He said he just couldn't sleep. He felt the Nazis were working, that they were pushing ahead to get there before us. We were in a real race, and he felt he shouldn't be taking a day off.
Herbert L. Anderson. One important detail was the location of the cadmium control strips. These were needed to keep the pile from becoming too reactive once it began to approach the critical size. We wanted a number of control rods distributed widely in the structure. This meant that some had to be installed at a rather early stage. A simple design for a control rod was developed, which could be made on the spot. Cadmium sheet nailed to a flat wood strip was inserted in a slot machined in the graphite for this purpose. The strip had to be inserted and removed by hand. Except when the reactivity of the pile was being measured, they were kept inside the pile and locked using a simple hasp and padlock, the only keys to which were kept by Zinn and myself. One special, particularly simple control rod was built by Zinn. It operated by gravity through weights and a pulley and was called Zip. It was to be pulled out before the pile went into operation and held by hand, Zinn's, with a rope. In case of an emergency, or if Zinn collapsed, the rope would be released and Zip would be drawn into the pile by gravity.
Leona H. Woods. Everything and everybody soon became black with graphite dust, There was a black haze in the air that scattered the beams from the floodlights. Walter Zinn forbade me to help with construction because he said he didn't want to discover he had been cussing out a girl when I took off my dust mask and cap. He was ready and versatile at cussing. It was just as well because there was plenty for me to do.
Meta Newson, project spouse of physicist Henry W. Newson. The first 2 years after we were married, from 1934 until 1936, we were in California with Ernest Lawrence at the cyclotron at Berkeley. When the Manhattan Project started, my husband was at Stagfield. When I went to Stagfield to pick him up in the evenings, I couldn't go in, he would have to come out. He came out one day with little blocks of graphite. I thought, that idiot, he is starting to play with blocks.
Arthur Holly Compton. The graphite dust made the floor more slippery than a dance floor.
Herbert L. Anderson. Once the 15th layer had been reached, we introduced the practice of measuring the neutron activity at a fixed point in the structure. Each day, the measurements of the activity were reported to Fermi, who used it to improve his estimate of how much bigger the pile would have to be.
Alvin M. Weinberg. Fermi was able to accurately predict how many layers were needed for criticality.
Herbert L. Anderson. As the pile grew, the estimate of its critical size became increasingly accurate. Thus, we could tell that on the night between December 1st and 2nd, during my shift, the 57th layer would be completed and the pile could be made critical.
Albert Wattenberg. About 8 weeks prior, Fermi had started a series of weekly lectures which continued until November 20th.
Luis Alvarez. His brilliance as a lecturer was astonishing. I had never heard such lucid lectures, delivered without notes but as polished as if Fermi had been reading them from a book. My friends and I attributed his flawless performances to careful rehearsal. Later, when I worked with him, I understood that he simply knew his subject so well that he could improvise a finished presentation only minutes before he walked into the room.
Herbert L. Anderson. That night, the construction proceeded as usual with all cadmium rods in place. When the 57th layer was completed, I called a halt to the work in accordance with the agreement we had reached in the meeting with Fermi that afternoon. All the cadmium rods but one were then removed, and the neutron count taken, following the standard procedure which had been followed on the previous days. It was clear from the count that once the only remaining cadmium rod was removed, the pile would go critical. It was a great temptation for me to pull the final cadmium strip and be the first to make a pile chain react, but Fermi had anticipated this possibility. He had made me promise that I would make the measurement, record the result, insert all cadmium rods, lock them all in place, go to bed, and nothing more.
Chain reaction. In early December 1942, the World War still appeared that it could go either way. Far from Chicago, some of the war's fiercest moments flashed, including battles in North Africa and Guadalcanal, and warnings were just beginning to come about how brutal the conflict's cost was turning out to be. The State Department had recently warned that approximately half the estimated 4 million Jews in Nazi-occupied Europe had been slain in an extermination campaign, leading Jewish communities across the Allied nations to hold vigils and declare Wednesday, December 2nd, 1942, an International Day of Mourning. Underneath the old stadium at the University of Chicago, the day would be remembered for other historic reasons. There, the Chicago Met Lab believed it was ready to start up the world's first artificial nuclear reactor. The final pile was a massive undertaking, costing about $1 million and involving some 45,000 graphite blocks, totaling more than 300 tons, alongside more than 5 tons of uranium metal and 40 tons of uranium oxide.
Arthur Holly Compton. Wednesday, 2 December, was a cold day in Chicago, about 10 degrees with a raw wind. The L and the streetcars were jammed, for it was the second day of gas rationing. Motor traffic was down 40%.
Walter Zinn. It was a very cold day. To those of us who worked in the West stands, cold was not a new experience. That gloomy structure with its high stacks of graphite bar filling all corridors, stairwells, and wherever 500 tons of the black stuff would be stored was completely unheated. Perhaps the importance of our jobs had something to do with it, but we really worked fast to keep warm.
Arthur Holly Compton. That morning, on schedule, W.K. Lewis brought his reviewing committee back to Chicago, returning from Lawrence's laboratory in California. They were stopping over between trains. We met the committee in a comfortable conference room of Eckert Hall. "Where is Fermi?" Lewis inquired. "We would like to talk over these questions with him." "I'm sorry," I replied, "but Fermi has an important experiment in hand in the laboratory and has asked to be excused. Here are others of us who will be glad to discuss your questions." The members of the committee surely guessed what Fermi was doing, but in not telling them, the code of secrecy was being observed.
Albert Wattenberg. On December 2nd, we began by checking that the neutron intensity was the same as Herb Anderson had measured the previous night, when all except one of the cadmium rods in that pile had been removed. The rates on some of the other instruments were checked, and some adjustments were made in anticipation of the neutron intensities increasing as we proceeded in the morning.
Arthur Holly Compton. Tests showed that the pile, only about 3/4 of the size that had been thought necessary, was ready to give a chain reaction. This reaction was held down by control rods coated with cadmium that swallowed up all neutrons within reach. To make the reaction work, it should now only be necessary to pull these control rods out of the pile.
Herbert L. Anderson. Fermi had prepared a routine for the approach to criticality. The last cadmium rod, attended by George Weil, was pulled out step by step. At each step, a measurement was made of the increase in the neutron activity, and Fermi checked the result with his prediction based on the previous step.
Albert Wattenberg. The rest of us gathered on the narrow balcony at the other end of the squash court. At one end of the balcony were the electronics, scalers, and a pen recorder attached to detectors on the pile. Some of the younger physicists would read and plot the readings from the scalers. Fermi could look at their data or at the pen recorder. They were independent measurements of the neutron intensity.
Leona H. Woods. Fermi and I repeated Herb's flux measurement with the standard boron trifluoride counter.
Albert Wattenberg. The most important thing was to establish the position of the control rod at which the pile would become self-sustaining, that is, the critical point. The next thing was to establish how fast the intensity would rise if he moved the rod beyond that point. From the first couple of measurements, he obtained the value of the constant, which was what he had hoped it would be.
Leona H. Woods. The new point fell exactly on Fermi's extrapolated line. It intercepted 0 at half a layer less than number 57.
Albert Wattenberg. Fermi periodically read some numbers and did a quick calculation on his little slide rule of the exponential rate of rise of the neutron intensity in the pile. After the intensity had leveled off, he then told Weil to move the cadmium rod another 6 inches. The neutron intensity in the pile rose further and then again leveled off. The pile was still subcritical. Fermi had been busy noting the values on the back of his slide rule and calculating the rate of rise. After it had stabilized, Fermi told Weil to move the rod out another 6 inches. Again, the neutron intensity increased and leveled off. The pile was still subcritical.
Norman Hilberry. Clearly, if there were any new law of physics, it would begin to show up in an actual deviation of the observed graphs from those Fermi had computed. And each time, it hit absolutely right on the nose. I am sure that long before Fermi finally said, "George, pull it out another 10 inches," the question had long since been settled in his mind. It was long since settled in mine, too.
Alan Wattenberg. It was 11:30 a.m., and Fermi said, "I'm hungry. Let's go to lunch."
Leona H. Woods. We agreed to meet again at 2 o'clock. Herb, Fermi, and I went over to the apartment I shared with my sister. It was close to the stands, for something to eat. I made pancakes, mixing the batter so fast that there were bubbles of dry flour in it. When fried, these were somewhat crunchy between the teeth, and Herb thought I'd put nuts in the batter.
Arthur Holly Compton. About middle of the morning, the telephone rang. It was Volney Wilson's voice. "I thought you would want to know that Fermi is ready to start the critical experiment. Wilson explained that space in the laboratory was at a premium, but told me that if I wanted to bring with me one other person, it should not too greatly disturb the experiment. I picked rather the youngest member of the group, Crawford H. Greenwald, then at the age of 40, the director of research of one of the important divisions of the DuPont Company.
Crawford H. Greenwald, Chief Liaison to the Manhattan Project, DuPont Corporation. Why he picked me out of the three, I do not know, but he did.
Arthur Holly Compton. I reasoned that he would probably remember longer than the others what he would see, and it should be something worth remembering.
Crawford H. Greenwald. Of course, it was an exciting thing because, actually, I never regard this particular experiment as really critical. That is, there are many first experiments that do not work, and this does not mean that it cannot be made to work. This is just the first try, and it was interesting. But I did not consider it as critical in determining whether or not the project fell flat or whether it went on. I am quite sure that if it had not worked, if the experiment had failed for some reason or other, they would have found some way of trying again.
Leona H. Woods. We put on the usual gray, now black with graphite, laboratory coats, and entered the double squash court containing the looming pile enclosed in the dirty, grayish-black balloon cloth, and then went up on the spectators' balcony. The balcony was originally meant for people to watch squash players, but now it was filled with control equipment and readout circuits glowing and winking and radiating some gratefully received heat.
Arthur Holly Compton. We entered onto a balcony at one end of the squash court laboratory. At the opposite end of the room was the massive pile of graphite blocks, within which the uranium was embedded. On the balcony with us were 20 others, including Fermi.
Eugene Wigner. Leo Szilard was able to bring himself to attend the event. His sense of history was apparently greater than his jealousy of Fermi.
Albert Wattenberg. Herb Anderson, Bill Sturm, and Leona Woods were recording the readings from instruments. Somehow we got a public address system, and Bill Overbeck was set up to call out the neutron counts. Fermi was set up to watch the pen on the recording chart, which was attached to a neutron detector.
Herbert L. Anderson. Then back from lunch, Fermi called for another increase in activity. Again, predicted it on the nose, you see. And then finally he says, now we will make a chain reaction for the first time in the history of man. We will pull the rod out.
Crawford H. Greenwald. They had on the platform buckets of strong cadmium nitrate solution. The idea was that if the reaction could not be controlled by the control rods and seemed to be getting away, they were to run out on top of the structure and pour the buckets of cadmium nitrate physically, by hand. This was supposed to stop the reaction, but this was simply the remote precaution.
Albert Wattenberg. We had several different types of safety rods. One of them, called Zip, which was designed by Zinn, operated by gravity. Wilson's group had built a series of safety rods which could be activated remotely by pushing a button. An additional gravitational safety rod was tied out with just a rope on the railing of the balcony where we stood. Norman Hilberry had an axe to cut that rope if human intervention were required to shut the pile down in a hurry.
Leona H. Woods. Each person had a job. I read the counts of the standard boron trifluoride counter in a loud voice. 2, 2, 3, 1. These being the counts in 10-second intervals with the control rod still inside the pile.
Albert Wattenberg. The trace on the paper on which the neutron intensity was being recorded showed the intensity rising slowly, at the rate that Fermi expected.
Arthur Holly Compton. The data fitted his calculated line with remarkable precision.
Herbert L. Anderson. At first you could hear the sound of the neutron counter. Clickety-clack, clickety-clack.
Leona H. Woods. The last control rod, manned by George Weil, was pulled out foot by foot at the voiced instruction of Fermi on the balcony above him. After each foot, there was a halt to measure the increased neutron flux shown by the pen recorder, which Fermi checked with his slide rule against his predicted flux increase. When the cadmium control rod was pulled out to each new position he asked for, you could hear the sound of the clicking boron trifluoride counter increase. I called, 8, 16, 28, 64. Then the clicks merged into a roar too fast to read.
Herbert L. Anderson. The clicks began to merge into a roar. The counter couldn't follow anymore.
Leona H. Woods. Fermi switched on the chart recorder attached to the ion chamber, and everyone watched the pen rise rapidly and level off. Another foot, George! The pen rose rapidly and leveled off. Another foot, George!
Crawford H. Greenwald. The thing that I remember best is Enrico Fermi's complete calmness. He was walking around as if he was simply waiting for the barber to say, "Mr. Fermi, come have your hair cut." It was just as casual and calm as that. Every so often he would pull a little 3-inch slide rule out of his pocket and make a few stabs with it.
Herbert L. Anderson. The pile has gone critical, he announced. No one present had any doubt about it.
Leona H. Woods. Everyone could see that the pen line was rising without leveling off. Up and up.
Herbert L. Anderson. Then, everyone began to wonder why he didn't shut the pile off. But Fermi was completely calm. He waited another minute. Then another.
Leona H. Woods. What happened was that Fermi waited, and waited, to test Volney-Wilson's control circuits. Suddenly bells rang, startling everybody. The ion chamber flux had passed the level preset for safety. Wilson reached over and tore the connecting wires out of the wall to stop the bells. Electric motors drove in the safety rods. Like the control rods and the zip, the safety rods were coated with cadmium foil, and this metal absorbed so many neutrons that the chain reaction was stopped. Volney-Wilson called these scram rods. He said that the pile had scrammed. The rods had scrammed into the pile. This word has entered the vocabulary of power plant operation, and also of nuclear submarines, so that any shutdown of the reactors is called a scram.
Albert Wattenberg. The radiation and the neutron intensity and the counting rates all decreased almost instantaneously. We had built the pile, and Fermi had established that we could get a self-sustaining nuclear reaction that we could control in a very predictable manner.
Crawford H. Greenwald. It worked. We all heaved a sigh of relief.
Leona H. Woods. At the instant that the safeties went in, the pile had achieved a power of only about 1/2 watt, barely enough to light a flashlight, but the chain reaction had been demonstrated.
Herbert L. Anderson. No cheer went up, but everyone had a sense of excitement. They had been witness to a great moment in history. Only 43 persons were present at the experiment, mostly the scientists who had done the work.
Leona H. Woods. We began to lock in all the control and safety rods, and to turn off the power supplies. We were nearly ready to leave, taking off our dirty gray laboratory coats and putting on our outdoor coats, when in came Eugene Wigner, alone, with one small bottle of Chianti. We were only about 20 people, the visitors and the high brass all having long since left. Eugene had, miraculously, not only the tiny bottle of Chianti, but also some paper cups. These he filled with a few drips each, and passed them around in the midst of that dingy, gray-black surrounding, without any word whatsoever. No toast, nothing, and everyone had a few memorable sips. No toast? Why not? There was a greater drama in the silence than if words had been spoken. Everyone was thinking, if we did it, haven't the Germans already achieved the chain reaction?
Albert Wattenberg. After all the others had left, I stood there just looking at the pile. I had a tremendous feeling of accomplishment. Then my mind wandered in the wrong direction. I started thinking about the work that lay ahead. So I went around and checked that all of the rods were locked in place, that all the power supplies were turned off. I hung up the Chianti bottle on the wall. I then went home to my room to sleep for 12 hours.
Arthur Holly Compton. When the committee had left, I picked up the phone and called Conant.
James B. Conant. The way the story is usually told, I was in my office in Cambridge. Actually, I was in Washington, in my quarters in the dormitory attached to the Dumbarton Oaks Library and Collection of Harvard University, where I had been staying several days each week since Pearl Harbor. I was waiting for news. Therefore, I was not surprised when I heard Arthur say, "Our Italian navigator has just landed in the New World."
Arthur Holly Compton. Then, half apologetically, because I had led the S1 committee to believe that it would be another week or more before the pile could be completed, I added, the Earth was not as large as he had estimated, and he arrived at the New World sooner than he had expected.
James B. Conant. My apprehension influenced my immediate question. Were the natives friendly? There was no prearranged code, but Arthur knew that I was asking whether everything had proceeded according to prediction. Everyone landed safe and happy, he replied.
Leona H. Woods. Enrico and I trudged back toward home through the blue-shadowed snow, the temperature well below zero. Herb had already disappeared, doubtlessly to clean up for a party that Laura was giving that night. Enrico and I didn't say a word. I don't know what he was thinking, but I was thinking, of course the Germans have already made a chain reaction because we have, and they have been ahead until now. When do we get as scared as we ought to and work harder? Seeking to probe his thoughts, I asked Fermi, when do we get scared? Could our work go faster?
Laura Fermi. In December 1942, I gave a large party for the metallurgists who worked with Enrico and for their wives.
Leona H. Woods. Laura's party had been scheduled for weeks before. That it happened to fall on the same day as the chain reaction demonstration was pure coincidence. Laura was so little aware of the major events of the day that after the tired and exultant Enrico got home, she asked him to go out and buy cigarettes for the party. And it was snowing.
Laura Fermi. As the first bell rang shortly after 8 in the evening, Enrico went to open the door, and I kept a few steps behind him in the hall. Walter Zinn and his wife Jean walked in, bringing along the icy cold air that clung to their clothes. Walter extended his hand to Enrico and said, "Congratulations." "Congratulations?" I asked, puzzled. "What for?" Nobody took any notice of me.
Leona H. Woods. I got there on time, about 8 o'clock, and almost instantly people began to arrive in large numbers. As each couple came through the door, stamping off snow and pulling off overshoes, they had congratulations for Enrico.
Laura Fermi. Every single man congratulated Enrico. He accepted the congratulations readily, with no embarrassment or show of modesty, with no words, but with a steady grin on his face.
Leona H. Woods. Laura was mystified. What was going on?
Laura Fermi. My inquiries received either no answer at all, or such evasive replies as, "Ask your husband," or "Nothing special, he is a smart guy, that's all," or "Don't get excited, you'll find out sometime." I had nothing to help me guess. Enrico had mentioned nothing worthy of notice, and nothing unusual had happened, except, of course, the preparations for the party. And those did not involve Enrico, and provided no ground for congratulating.
Leona H. Woods. She came to me and begged me to tell her what Enrico had done. I was struck dumb by her question and became a silent statue. How could I, the youngest member of a totally secret project, say one word that would inform her, this beautiful lady who I admired so intensely and would not disappoint for anything? My mind gradually unthawing, I decided to use an analogy. I said that Enrico had done something equivalent to sinking a Japanese admiral's ship. This at a time when the American fleet in the Pacific had been totally wiped out, and we were at the mercy of the Japanese. Even the capture of Hawaii and the invasion of the west coast of the United States were possible. So I replied, "He sank a Japanese admiral." This was perhaps the most embarrassing moment of my life, quite unknown to anyone else.
Laura Fermi. 2 years and a half elapsed. One evening, shortly after the end of the war in Japan, Enrico brought home a mimeographed, paper-bound volume. "It may interest you to see the Smith report," he said. "It contains all declassified information on atomic energy. It was just released for publication, and this is an advanced copy." It was not easy reading. I struggled with its technical language and its difficult content, until, slowly, painfully, I worked my way through it. When I reached the middle of the book, I found the reason for the congratulations Enrico had received at our party.
Herbert L. Anderson. The original pile in the west stands, dubbed CP1, had a short life. It lived for 3 months, but those were 3 very active months for the first chain reactor. It turned out to be a marvelous experimental tool. Its sensitivity for neutron absorption and production was beyond the wildest dreams of those of us who had struggled so hard to make such measurements before. The pile became an indispensable device for the design of its successors. The building at the Argonne site was now complete, and we had a whole group of young and eager engineers from DuPont to help us. We did not hesitate to disassemble and rebuild the pile at the Argonne site.
Albert Wattenberg. I had sentimental feelings about CP1. I remembered the circle which had been drawn on the floor of the balloon cloth to indicate where we should lay the first bricks. As we got close to the bottom layers, I dug down and made sure to get out what I thought was the first graphite brick that had been laid, namely the cornerstone of CP1. I moved these out to our laboratory at Site A, and the Chianti bottle hung on the wall of that laboratory until the straw string began to look rather weak.
Arthur Holly Compton. The atmosphere was now one of confidence. The nuclear reaction was an accomplished fact.
Colonel Kenneth D. Nichols. Franklin Matthias and I went to Wilmington on December 14th to discuss with DuPont officials the site requirements for the relocated plutonium process. Given the needs for a much larger area than the Tennessee site and a great deal of electric power and water, relatively few suitable locations existed. The area in central Washington state near the Grand Coulee Dam seemed to offer the most promising site, and on the 15th, Matthias and AES Hall and GP Church of DuPont left to survey that area and other locations in California and Nevada.
Colonel Franklin T. Matthias, Officer in Charge, Hanford Engineer Works. I thought the Hanford site was perfect the first time I saw it. We flew over the Rattlesnake Hills up to the river, so I saw the whole site on that flight. We were sure we had it. I called General Groves from Portland and told him I thought we had found the only place in the country that could match the requirements for a desirable site. It had so much in favor of it. An area with almost no people, very undeveloped. It was obvious it had been built by the Columbia River in early times, working across the valley, leaving gravel behind it, and there's nothing better than gravel, deep gravel for foundations, for earthquake protection, anything you want. It had all the advantages.
Brigadier General Leslie Groves. The Hanford site was one of the largest procurements of land handled during the war or at any other time. The total acreage taken was something less than 500,000 acres.
Arthur Holly Compton. This decision to develop another vast area for carrying on the atomic project added very substantially to its total cost. It was about a similar occasion that General George C. Marshall was speaking when, years later, he told me the following story. General Groves came to see him at his office in Washington. Marshall kept him waiting for some minutes while he finished an item on his desk. Then he turned to examine Groves' memorandum. It was a statement that added facilities would require an additional $100 million. He read the memo and, as was his custom, handed it back with only a kind comment to indicate his approval. As Groves was about to leave, Marshall called him back. "General," he said, "you may be interested to know why I kept you waiting when you came in. I was writing this check for $3.52 for grass seed for my lawn."
Eugene Wigner. Just 2 weeks later, the plans for the reactor plant in Hanford, Washington were passed out. They reflected the will of the Army to build production-scale nuclear reactors. What confidence all of us had in Enrico Fermi's team. He inspired it. He deserved every bit of it.
Alvin M. Weinberg. By the end of 1942, Wigner had completed the design of a 500-megawatt water-cooled reactor that would produce 500 grams of plutonium per day. The report CE-407, Preliminary Process Design of Liquid-Cooled Power Plant Producing 5 times 105 kW, was dated January 9, 1943. As I think back on Wigner's design of the Hanford plutonium-producing reactors, I can think of only one analogy. Mozart, who would compose a piano concerto in a few days. The whole thing was accomplished in about 4 months.
Colonel Kenneth D. Nichols. With the selection of Los Alamos for the bomb development laboratory and the Hanford site for the plutonium production plants, and with the acquisition of the CEW site, the Manhattan Project had the locations for its major facilities. Thus, by the end of the year, work was underway on 3 methods of producing fissionable material, with the goal of producing at the earliest possible date an atomic bomb that could fit into the bomb bay of a B-29.
Arthur Holly Compton. After December 1942, what determined when the bombs were ready was simply the time required to design and build the plants, to produce the materials, and to fabricate the materials into bombs.
Colonel Kenneth D. Nichols. The December 1942 progress report for President Roosevelt provided estimates for beginning bomb production as possibly June 1, 1944, a better chance before January 1, 1945, and a good chance during the first half of 1945. The total cost was estimated as about $400 million.
General George C. Marshall. I obtained the first money for the Manhattan Project by taking 20% of the appropriations concerning such matters in the development of bombs, artillery, and kindred matters, which was legal. You could divert 20% away from an appropriation to a somewhat similar matter, one connected with defense, for example, and this bomb was certainly connected with defense.
Vannevar Bush. The way in which the money was raised was interesting. Each year, after the Manhattan District had been established, Secretary Stimson and I went up on Capitol Hill and met first with the leaders of the House and then with their counterparts in the Senate. This included, of course, the chairman of the Appropriations Committee of the House, the senior minority member, and the majority leader of the House, about 5 or 6 men. I told them of the difficulties of development, the enormous cost, the probable timetable, the size of the bomb when it was developed. We included also estimates of where we thought the Germans stood. Now this was an excellent way to do it, because then the item for the money on the Manhattan District was buried in Army appropriations. When it came up, for example, in the House Appropriations Committee, the chairman would say, "Well now, don't inquire into that item, gentlemen. I've inquired into it very thoroughly, and I can assure you that it's all right." There never was the slightest leak from that source.
Part 3. Making the Bomb. 1942 to 1944. From late 1942 through the winter of 1945, the work of the Manhattan Project unfolded at numerous sites around the country simultaneously. From the RAD Lab in Berkeley, to the Met Lab and Argonne Lab around Chicago, to Columbia University in New York. The project's 3 major facilities, at Oak Ridge, Tennessee, Los Alamos, New Mexico, and Hanford, Washington, each had to be built from scratch, creating some of the most advanced scientific facilities in the world in remote, isolated locales, amid wartime labor and materials shortages, to focus on industrial processes based on novel and largely untested methods, all under a heavy cloak of secrecy and misdirection. At nearly every turn, project planners, engineers, and scientists realized they had underestimated the complexity and scale of the work ahead. The division of labor, for the most part, fell into 3 distinct lanes of effort. Oak Ridge was the center of the Manhattan Project's uranium refinement. Hanford focused on plutonium, and Los Alamos brought together the world's top scientists on a remote mesa to design and build the working bombs themselves. For organizational and comprehensibility purposes, I have mostly organized the narrative in this part by geographic location rather than strictly chronologically, telling the stories of Oak Ridge, Los Alamos, and Hanford distinctly, even though time-wise they all overlapped from 1942 through 1945. The order ahead follows roughly when each location's primary work unfolded. In the roughest chronological terms, the Oak Ridge Y-12 calutrons begin uranium production first in November 1943, while the bomb design work peaks in 1944 at Los Alamos, and the Hanford plutonium facilities begin production last in September 1944, when their B reactor comes online. Oak Ridge, creating the Clinton Engineer Works. When Leslie Groves and the U.S. government requisitioned a vast expanse of land in Tennessee, the Manhattan Project still had little idea what precisely would be built there. The site, known first as the Clinton Engineer Works and later Oak Ridge, would ultimately host the first of the mega facilities built to ready uranium for the bomb. The region around the Clinch River was mountainous and still quite rural. The dams of the Tennessee Valley Authority were just beginning to bring electrification to many of the small communities around Black Oak Ridge. As families, many of whom had lived in the Tennessee hills for generations and even centuries, were moved out, engineers and scientists drew on the work of Ernest Lawrence's Berkeley Calutrons and other Manhattan Project labs to build some of the largest industrial facilities in the U.S.
Alvin M. Weinberg. Almost immediately after the Army took over the project in September 1942, Tennessee was chosen as Site X for all the production plants, the 3 isotope separation plants, K25 gaseous diffusion, Y12 electromagnetic separation, and later S50 liquid thermal diffusion, and the plutonium-producing piles.
Brigadier General Leslie Groves. Here would be located all our uranium separation plants, the plants designed to separate the easily fissionable uranium-235 from the more abundant but much less fissionable isotope, uranium-238.
Paul Elza, engineer, Tennessee Valley Authority. In very late 42, there were rumblings throughout the countryside about something big going on out near Clinton. Most people were quite busily engaged in many other things and paid relatively little attention to it. Word and rumor began to spread that it was going to be a great artillery range or a bombing practice location. That caused some concern in the population. It was natural, for one of those things about which we all speculated was that it would be some great new secret weapon. And of course, that wasn't too far from the mark.
Horace V. Wells, Jr., publisher, The Clinton Courier-News. The takeover. This was a rather difficult period for the country. The U.S. Army sent in people to handle the acquisition of the property for the then-called Clinton Engineer Works.
J. Nash Copeland, owner, General Store, Robertsville. They just came down, looked around, issued an order of taking, and told us to get out of the property. November the 15th they told us to move. We moved out December the 1st of 1942. I'd built a 4-room house with running water in it, and I had improved our house by adding a bathroom and putting in running water and electricity. I'd improved the store building, and I had a warehouse building, and I still only was offered the same price when the government came in to take it over that I had paid for in 1935. We had one little lady lived on the hill, Mrs. Dicey. She had an acre and a little house and a little barn thing. They only gave her $75 for her total property there, believe it or not. Wasn't enough to move the woman.
Horace V. Wells, Jr. Here were people who had land that had been in their family from the original grant from the state of North Carolina for service in the Revolutionary War. The land had never been sold, and it was the only home they had. They had been making a living there. They were satisfied. The government came in and offered prices that felt too low, and in fact were too low, to go and buy comparable land anywhere else.
J. Nash Copeland. We had a mass meeting at the Scarborough School at that time, and the building was just about full. I don't believe there was hardly a family here that wasn't represented, and they were unanimous in telling the government that they weren't treated right in purchasing the property. The only reason people here gave up their homes as easy as they did is because they thought it was wartime, and they thought they were doing their part in helping the war effort.
Paul Elza. We were at war. We were in rather desperate circumstances up until that time. Remember, things hadn't gone entirely well for us, and people were in the mood of sacrifice. They were in the mood of being cooperative. You could stop a man on the street and tell him, persuasively, that you needed the coat off his back for the war effort, and chances are, at that moment, he'd shuck his coat off and hand it to you and never look back.
Arthur Holly Compton. The speed with which the construction went ahead at Oak Ridge was phenomenal. In December 1942, ground was broken for the administration building. During the following winter, work started on the electromagnetic separation plant, the plutonium semi-works, and the residential areas. In June 1943, a steam power plant of 250,000 kilowatts was begun to supply the electricity for the plants that were being erected.
Colonel James C. Marshall. We had a contest in the district there and offered a $25 bond to anybody that would name the place down there. We got 94%, I think, of the several hundred replies to the contest were all Shangri-La, so I vetoed that.
Charles E. Norman, Project Staff, Y-12 Plan, Tennessee Eastman Corps. We were told that we were going out to the site, which was now referred to a little more specifically as Clinton Engineer Works, though we still didn't know where it was. As a matter of fact, when we got on the train to come out, the senior member of our party had all our tickets in a sealed envelope, and we weren't allowed to open it until we were out of town on the way.
Colonel James C. Marshall. One day O'Meara came in and he said, if we're going to open up a town down there, I've got to have a name for it. We called it the Clinton Engineer Works to disguise it, like the such-and-such Ordnance Works, Badger Ordnance Works, and Twin Cities Ordnance Works, and things like that. O'Meara said, the post office won't stand for that many words in the name. I said, well, we can't call it Clinton because there is a town, Clinton. We thought of several names, and I remember sitting in the office down here with Virginia Olson. She sat in the same office I did. Nichols was here, and Blair was here in separate rooms. I asked Ms. Olson to bring me a map. I saw the principal ridge there was marked Black Oak Ridge. I said, okay, call it Black Oak Ridge. And he rubbed his hands and he said, I told you we could not have 3 names in the town like that. The post office department doesn't like it. I said, well, call it Oak Ridge and get the hell out of here. And so it was named.
With the land cleared and in government hands, work began on the uranium plants. Just as Groves had enlisted DuPont as the main contractor for the plutonium project, he turned to a local powerhouse industrial firm to handle the construction and management of the new uranium plants. The construction project alone would employ about 15,000 people, and training was soon underway for 5,000 more personnel to operate and maintain the plants. The original plans for the Clinton Engineer Works envisioned housing and facilities to support about 13,000 people. But population estimates quickly leapt to 30,000, then 45,000, and ultimately there were 75,000 people working in and around Oak Ridge by the end of World War II, making the secret community the 5th largest city in Tennessee.
Brigadier General Leslie Groves. Long before the essential research was well started and before the equipment could be designed, we had to start designing and constructing the building to house it. Stone and Webster was in charge of this operation. The research on which all design was based was carried out in the radiation laboratory of the University of California under the direction of Dr. Lawrence, and to operate the plant, we selected Eastman Kodak, whose subsidiary, Tennessee Eastman, was an extremely competent organization with much experience in chemical processes.
Colonel Kenneth D. Nichols. Tennessee Eastman already was involved in war work and was responsible for the Holston Ordnance Works, an explosives plant near Kingston, Tennessee. They knew industrial chemical operations, the labor situation in Tennessee, and had the full technical, managerial, and financial backing of Eastman Kodak. Tennessee Eastman worked closely with Stone and Webster and took full responsibility for developing the chemical process based on work done at Berkeley.
Horace V. Wells, Jr. We had a tremendous influx of people during the early days. People were living in barns and chicken houses. Automobile firms went out of business during the war, so some of the garages were converted into dormitory arrangements. People just placed anywhere.
Edward S. Bettis, Nuclear Engineer, Y-12 Plant, Tennessee Eastman Corporation. I was told absolutely nothing. Absolutely nothing. As a matter of fact, my interview for the job took place on the fire escape on the old Empire Building in Knoxville. I remember asking the man who interviewed me, "What are we going to do?" He said, "I can't tell you." I said, "When will you be able to tell me?" He said, "We won't tell you. Ever."
John Schachter, Chemical Engineer, K-25 Plant, Union Carbide.
Through World War II, the company that helped run the Oak Ridge facility was known as the Carbide and Carbon Chemicals Company, which later evolved into the modern-day Union Carbide. Since the company is referred to in oral histories and memories as both, I've changed all references to Union Carbide for simplicity.
They had a big hall with the interviewers. Mine was named Kleintop. He said, "I can't tell you anything about the work. It's wartime stuff. But it's got a lot of math and engineering, and it's interesting. and it's fast-moving, and if you want the job, you're going to have to stay right here and go to work.
Paul Elza. I looked up from my desk at the Tennessee Valley Authority, and there appeared in the door Leo Warren. He was a brusque sort of rough-talking character, and I heard him call out, "Where in the hell's Elza?" And I stood up at my desk and held up my hand to wave to him, and he came back. He loomed over my desk and says, "I want you to go with me." I says, "All right, when?" And he says, "Now." He says, "I can't tell you anything about it. I can't tell you what you'll be doing." And he says, "I can't tell you anything except you won't be paid any less money than you are here." It turned out that that man had gone throughout TVA and had picked and selected people that he wanted to come to Oak Ridge. I came with him. He stopped by an employment office, and there were signs around saying Tennessee Eastman Corporation, and he said, "These are the people who are going to put you on the payroll." We then came through Clinton, and through what was even then known as Elza Gate, and we were taken up to a building that looked like a huge army barracks.
Waldo E. Cohn, biochemist, metallurgical laboratory. A lot of my recruiting took place by phone calls from my old colleagues at Berkeley and whatnot. They hedged around. It would be something in line with my expertise and that I would find it very exciting, so forth and so on. Anyway, there were enough hints dropped to make me interested.
Brigadier General Leslie Groves. There were only 3 electrical suppliers in the country whom we considered suitable for the manufacture of the type of equipment in the quantities needed for the electromagnetic project. To avoid overloading them, we divided our requirements among them. General Electric produced power supply equipment, Alice Chalmers the magnets, and Westinghouse the process bins and allied parts. Building and operating such a plant as this presented many new industrial problems as laboratory experiments using raw materials measured in grams were expanded to handle tons. More than 50 key specialists were transferred from Berkeley to Tennessee Eastman.
Edward S. Bettis. Eastman had only a very few of their employees that they put here. They had to recruit all the others. Some of us they called key personnel were given training in the policies of the company and how the company was run, and we in turn had to indoctrinate others. Although my job was a day job, I've gone out many times at 2 o'clock in the morning to conduct these training classes in Eastman policy. I was just one of many.
Brigadier General Leslie Groves. To wring out the utmost in the way of support for the electromagnetic project, we invited the presidents of Westinghouse, General Electric, and Alice Chalmers to visit Oak Ridge. The speed with which the plant could be completed depended largely on how quickly their companies could deliver the key parts, and we wanted these men to see for themselves just how their equipment was to be used and to gain a first-hand realization of the complexity and magnitude of the project. The results of the visits were quite noticeable.
Meyer Silverman, chemical engineer. The job offer in Oak Ridge looked attractive. Just as the interview was ending, they asked me, "By the way, what does Mrs. Silverman do?" I said, "Well, recently she has been working as secretary to a couple of patent attorneys at RCA." My interviewer said, "You hear that? Grab them immediately." They were short of competent professional secretarial help.
Obi Amaker, Labor Relations X-10 plant. I was not able to learn anything about the project until I reported to Oak Ridge. There I became reacquainted with some chemists whom I had worked with in Alabama. These chemists had disappeared to Oak Ridge and the University of Chicago, and I did not know what they were doing after they disappeared.
Marjorie Cattell, project spouse. I was very anxious to get down here. I remember the day that the great, big, burly man came to move our small amount of furniture. We didn't have very much. He was putting ours in the same van as several other people's that were coming here. He came in and said, "Well, so you are going down to Hell, Tennessee." It was a terribly bad thing to have someone tell you.
Oak Ridge, Y12. The centerpiece of the Oak Ridge complex was known as the Y12 plant, which used giant magnets to separate uranium isotopes. The scale boggled the imagination, given how tiny the finished output was. By the time they were at full operation, The 10 buildings that ultimately made up the Y-12 electromagnetic separation facility housed some 2,000 cyclotrons, modeled on Ernest Lawrence's work in Berkeley. Together they separated about 100 grams, equal to about a half cup, of uranium-235 each day. Construction work on Y-12 began long before the radiation laboratory had finished designing the machines that would go inside it, or, for that matter, before they'd even proved the design would work at all. Groundbreaking for the Y-12 plant occurred on February 18, 1943.
Luis Alvarez. It was Ernest's idea to build 1,000 enormous mass spectrometers, dubbed calutrons, to separate U-235 from U-238. The scale of his proposal led everyone to question his sanity at first. But with a series of increasingly large test devices, he demonstrated that he was on the right track. Understanding that the 184-inch cyclotron could be converted to a large-scale calutron, everyone pitched in to complete construction ahead of schedule. The big magnet went up first, and its building around it. When I visited the new laboratory on the Hill in March 1943, I found all this activity amazing. My old love for magnets, vacuum plumbing, and cyclotron electronics was rekindled.
Christopher Kime, project staff, Y-12 plant. The name calutron is a condensation of cyclotron and California, where the cyclotron was developed.
Brigadier General Leslie Groves. We would never have attempted it if it had not been for the great confidence that we, particularly Bush, Conant, and I, had in the ability and drive of Dr. Ernest O. Lawrence of the University of California. Rather early in the American effort, Lawrence had proved to his own satisfaction that electromagnetic separation was feasible, but he stood almost alone in this optimism.
Colonel Kenneth D. Nichols. Ernest Lawrence provided outstanding scientific leadership for the design, construction, and operation of the electromagnetics plant, Y-12. In my opinion, Lawrence probably was the most dynamic of all the physicists involved in producing the atomic bomb.
Brigadier General Leslie Groves. The method called for a large number of extremely complicated and as yet undesigned and undeveloped devices involving high vacuums, high voltages, and intense magnetic fields. As a large-scale method of separating uranium-235, it seemed almost impossible. Dr. George T. Felbeck, who was in charge of the gaseous diffusion process for Union Carbide, once said it was like trying to find needles in a haystack while wearing boxing gloves.
Paul Elza. When these calutrons are set up, they're set up inside a huge magnet. These magnets are laid out in the shape of a racetrack, in elliptical shape. They are quite large. All of us who worked on it referred to them as racetracks. All of the units are operating to separate the uranium-235, the fissionable isotope of uranium that you want in order to get fission and get the weapon.
Brigadier General Leslie Groves. In every way, this process was one of the major efforts of the MED, Manhattan Engineer District. Its purpose was to separate uranium-235 from uranium as it occurs in nature, and to do so in sufficient quantity and of the concentration necessary for use in atomic weapons. Basically, electromagnetic separation of isotopes is based on the principle that an ion describes a curved path as it passes through a magnetic field. If the magnetic field is of constant strength, the heavier ions will describe curves of longer radii. The various isotopes of an element, since they differ in mass, can be isolated and collected by such an arrangement.
Colonel Kenneth D. Nichols. By the middle of March 1943, the scope of the Y-12 plant was determined. There would be 5 racetracks of 96 tanks each for the alpha stage. Lawrence finally had acknowledged that a second, or beta, stage would be needed. The beta tanks were smaller, arranged in the form of a rectangle, with the plant consisting of 2 units of 36 tanks, 2 sources each. For the beta plant, everything had to be more precise because this plant would be handling 10 to 36% U-235 enriched material as compared to only 0.7% U-235 material in the alpha stage, and losses could not be tolerated.
Brigadier General Leslie Groves. The electromagnetic plant was built in a restricted area of about 825 acres in the central southeastern part of the reservation, approximately 5 miles from the commercial district of Oak Ridge, which was the town site of the overall development. From the standpoint of employment, this plant was the largest in the Clinton Works.
Colonel Kenneth D. Nichols. Lawrence toured the entire electromagnetics project in May 1943 and was amazed at the scope and magnitude of the effort. As a result of designing and building cyclotrons, Lawrence had far more experience with large equipment than most scientists. But even so, he had difficulty comprehending what was involved in building 552 calutrons and accompanying magnets and controls. However, his amazement at the progress increased his enthusiasm and his dedication to final success. Moreover, his enthusiasm permeated the entire project.
The enormous scale and material needs of the Y-12 plant proved especially challenging amid wartime shortages and the competing priorities for industrial manufacturing across the country and the war effort. One of the major early hurdles proved to be a shortage of copper for the wiring of the magnets, causing the Manhattan Engineer District to locate and source a creative alternative.
John Schachter. The gigantic scale of everything. You know, we had bicycles riding up and down the plant. I was impressed as heck.
Brigadier General Leslie Groves. Substances that had previously had very limited application were needed in staggering quantities. For example, each Alpha Track used 4,000 gallons of liquid nitrogen every week.
Colonel Kenneth D. Nichols. Copper was required for electric windings to form the large electromagnets. The pilot unit, originally planned for the Berkeley campus, would need 120 tons of copper, while the full-scale plant to be built in Tennessee would need 5,000 tons or more of the metal. Copper was in desperately short supply because of the demands of the war industries.
Colonel James C. Marshall. They said we can't have copper to build the magnets in the Y-12 plant. I heard from somebody that you could use silver. I remember calling up on the phone to Gus Klein at Stone and Webster. I said, "Will you compare over the phone the conductive qualities of pure silver and pure copper and disregard the cost? What is the resistance, the electrical properties, and the thermal properties?" Then I could figure out with all the stages and all the magnets needed in that Y-12 plant.
Colonel Kenneth D. Nichols. For the electromagnetic process, silver could substitute at the ratio of 11 to 10.
Colonel James C. Marshall. I then said to somebody, "Where can we get silver?" Somebody said, "Well, how about getting all this stuff from Treasury Secretary Mr. Henry Morgenthau? He's got, I don't know how many hundreds of millions of dollars worth of silver up there at West Point."
Colonel Kenneth D. Nichols. Since the government would own the plants and the silver could be returned after the war, we decided we should approach the U.S. Treasury to borrow the needed metal from the silver repository. As a result, I visited Assistant Secretary of the Treasury Daniel Bell. He explained the procedure for transferring the silver and asked, "How much do you need?" I replied, 6,000 tons. "How many troy ounces is that?" he asked. In fact, I did not know how to convert tons to troy ounces, and neither did he. A little impatient, I responded, "I don't know how many troy ounces we need, but I know I need 6,000 tons. That is a definite quantity. What difference does it make how we express the quantity?" He replied rather indignantly, "Young man, you may think of silver in tons, but the Treasury will always think of silver in troy ounces." With our contrasting perspectives expressed, we then settled on a form of agreement that was ultimately used to transfer some 14,700 tons of silver from its storage place at West Point to New Jersey, where it was melted down and cast into large ingots for shipment to Alice Chalmers in Milwaukee for further processing.
Brigadier General Leslie Groves. Under the terms of the final agreement, 6 months after the end of the war, an equal amount of silver would be returned to the Treasury. It was further agreed that no information would be given to the press on the removal of the silver, and that the Treasury would continue to carry it on their daily balance sheets.
Colonel Kenneth D. Nichols. Each month during the war, I signed an inventory for the Treasury stating that we had in our possession over 400 million troy ounces of silver, expressed 1/100th of an ounce.
Colonel James C. Marshall. Alice Chalmers wound it on the magnets, and those magnets were big enough to require 2 long freight cars, and they were shipped to Oak Ridge. That was a major operation in itself.
Colonel Kenneth D. Nichols. We established very strict procedures to avoid loss, and when the silver was returned to the Treasury after the war, less than 1/36,000th of 1% of the more than 14,700 tons of silver was missing.
Oak Ridge. Living inside the gates. The tens of thousands of newly arrived transplants found almost everything lacking in Oak Ridge, from entertainment to roads. Few of them, and even fewer of the local residents, understood exactly what was taking place inside the gates of the Clinton Engineer Works, and even many plant workers wondered at the goal of the vast industrial processes around them. The only Manhattan Project facility located in the Jim Crow South, Oak Ridge was also the only site to encounter legal segregation against black workers.
Colonel Kenneth D. Nichols. From the spring of 1943 to the end of 1944, a tremendous construction effort ensued at all the Manhattan Project sites. At the CEW, the construction of the central facilities, family housing, schools, commercial facilities, dormitories, and barracks or hutments for construction workers became an ever-expanding program. For temporary housing, we rounded up every trailer we could locate from every part of the United States. A separate construction camp, which we hoped would live up to its name, Happy Valley, was located near the gaseous diffusion plant to lessen travel time for the 17,000 construction men working there.
James Reagan Justice, cafeteria manager, Clinton Engineer Works. The locals hadn't the slightest idea what was going on. They'd see these trains loaded with something going into Oak Ridge and nothing coming out. They couldn't figure it. They didn't have any manufacturing or anything over there. There wouldn't be anything coming out. That's the thing I heard, more than anything else. What in the world could they be making when they weren't shipping anything out of there?
Colleen Black, leak detector, K-25 plant. Everything came in, and nothing came out.
Colonel Kenneth D. Nichols. During the month of May, we finished 1,288 family units, which brought the total to 7,041 residences, exclusive of 113 efficiency apartments. 18 dormitories were finished during the month. Every time we expanded the plant, we had to authorize more houses and town facilities of all kinds to provide for the welfare of the new influx of workers. We even built a jail, but then had to face the jurisdictional question of whether we had the authority to lock the door.
Charles E. Norman. One of the things that impressed me upon arriving was the size of the operation. A little bare, rocky hill had stacked, crated bathtubs covering that whole hilltop, waiting to be put into houses, none of which were built yet. A whole hilltop covered with bathtubs stacked 3 layers deep was an impressive introduction to the place.
Colonel Kenneth D. Nichols. Marshall argued for exception to the cost limits placed on expenditures for housing. Groves, however, expressed the belief that houses should be quite small and extremely simple in the interests of economy. In turn, Marshall argued that primitive housing could not be expected to meet family requirements of the class of personnel contemplated for the project, and that comfortable and modern quarters would have to be provided, at least to the maximum extent that could be reached under the money limitations expected.
Colonel James C. Marshall. For instance, I wanted to put a fireplace in every house we built in Oak Ridge. We started out, I built 1,000. He said, "You're crazy. You don't need that many." Well, then we had 3,000 going in a matter of 2 or 3 months, all on my say-so. All of the first 3,000 had fireplaces. Groves said that's silly. People like the pioneer experience. I said, you can build army barracks if you want to out in Los Alamos. I don't care what you build out in Richland. You can't have fireplaces there because there's no wood to burn in them. But I said at Oak Ridge, there is going to be a screened-in porch and there's going to be a fireplace in each house. I had to say so for Oak Ridge.
Arthur Holly Compton. Our house at Oak Ridge was like 3,000 others. It was across the road from a similar house occupied by Colonel Nichols, the commanding officer of the area. This little knoll where we lived accordingly became known as Snob Knob. The widespread community spirit made the best of the difficulty of living in this construction area. When my wife and I arrived to occupy our just-completed house, our car was filled with odds and ends. As we were sweeping the floors and clearing away the rubbish, across the road came a neighbor bearing a bucket and a broom. She introduced herself as Jackie Nichols. She was the wife of the commanding officer. What could she do to help put our house in order? A few weeks later, President Conant came to Oak Ridge. As he stepped in the door of our house, he exclaimed, "Why, Betty, you have made a home of this." "That's the idea, Jim," was her reply.
Carl Z. Morgan, health physicist, University of Chicago. I came to Oak Ridge in September of 1943, and my family joined me here a few months after that. I stayed at what was called the guest house. It was just a big barn in those days, and we slept in one big room that had about 30 cots.
John Michel, project staff, K-25 plant. When I first came down here, I went on shift work, rotating shift. So 2/3 of the time I was trying to sleep when other people weren't there, but still a lot of noise around the dorm. Thin walls and minimal structures.
Bonnie Hicks, chef. There were these huge trailer parks here. This is something that the people in Knoxville didn't seem to realize at that time. Some of the highest educated people in the world were living in trailers. That's all they had to live in. As far as my friends and relatives in Knoxville, they just didn't live in trailers. If you did, you were a very lower-class person as a rule.
Hetty Horton, teacher. This was a segregated town when we came, and they went by the Southern rules. Black employees had their own school. They didn't have a high school for a while. They used to have to take the bus and go to Knoxville.
Hal Williams, construction worker, K-25 plant. I would be working with a white fella all day beside him. Well, when quitting time come, they went to their shack, and I went to mine. That's a different world. We didn't even clock out on the same clock.
R.L. Ayers, cafeteria worker, K-25 plant. White people had barracks and dormitories, but black people had huts to live in, and that was it for the black people. The huts were something like a box, made like a box. It had 4 beds in it, and if they needed more space, they would put 8 beds in it, double beds. It had a big potbelly stove in the center of the floor, and that was the heat. So we had no running water, no place to cook, and no bathrooms in this place. They had a big, long place. They called it the latrine. That's where you had to go to do your washing, do your cooking if you wanted to cook anything, take a bath, and use the bathroom. If you were black, even if you had a master's degree, it made no difference. All you could do was sweep up, clean up. In 43, that's all that you could do. So I wasn't making but $1.47 an hour, but it was better than where I came from. This place was owned and operated by the federal government, and it was sad the way that the black people were treated.
Hal Williams. They had a Skyway theater for folks to drive in their cars. It was a long time before a black could drive his car there to it. He could come out there and sit up in the ground and listen to the movies. Sure, look at it. But he couldn't drive up there like the white did.
Colonel Kenneth D. Nichols. We ultimately completed more than 300 miles of paved roads throughout the reservation, including a 4-lane highway down the center of the main valley connecting the town of Oak Ridge with the gaseous diffusion plant, K-25, within the town site, and branch roads to the electromagnetic plant, Y-12, the plutonium semi-works, X-10, and to each of the 5 security entrance gates. We also had to build a complete water purification plant and 2 sewage treatment plants. The electric distribution system, telephone, water, and sewage systems had to be expanded continually to meet the exploding population of Oak Ridge. The railroad connections to the L&N and the Southern Railroad were faced with hauling the millions of tons of supplies needed for the 3 plants, the central facilities, and the town.
Charles E. Norman. Things were moving very fast. No sidewalks, no pavement. The streets had rock put on them. In fact, they followed a general pattern. They would bulldoze the streets out, place crushed stone on them, and then come along with a big de-ditching machine and dig a trench right down the middle to lay the water main, and then it would all have to be done over again.
Carl Z. Morgan. One day, I heard a plaintive call from a young lady who was ahead of us crossing the road. Looked up, and she was stuck in the mud. At that time, they issued boots to everybody that worked at the laboratory, women and men. And it was up to the top of her boots, and she wasn't able to move. Some of us got out to her and pulled her out. But her boots are still there. They're buried under the highway, I guess, today.
James Reagan Justice. Oh, the mud. I never saw so much mud as that in my life. That was the worst mud ever. And they had thousands and thousands of loads of gravel in there, and it'd just sink out of sight.
Hetty Horton. Your shoes just got wrecked.
Carl Z. Morgan. Each of us had 3 or 4 pairs of shoes we would have to clean in the evening because of the mud, and pick up the pair of shoes that had been worn the farthest back, and then get on the bus and go to work.
Paul Elza. All back in the woods behind the houses, there had been boardwalks built throughout the townsite, so that very few people used the roads when they were walking. They went everywhere they needed to go on the boardwalks.
James Reagan Justice. In Knoxville, they could tell an Oak Ridger by his shoes. He'd have mud all over them.
Ernest M. Lees, maintenance worker. I always felt that Knoxvillians resented all of us foreigners.
Carl Z. Morgan. Although many of us came from the South, I'm a Southerner, they thought all of us were Yankees.
Paul Elza. With this enormous influx of population, there were shortages of anything and everything. Not only was it wartime, but here was a concentration of one of the biggest activities going on, and in a small area, and in an area that was not heavily populated theretofore. Accordingly, everything was short. You never could find enough of anything. The people outside tended to blame that on Oak Ridge. The schools were all overcrowded, the movie theaters were overcrowded, the places to eat were overcrowded, and it was always them damned Oak Ridgers that were creating the clutter and the bother.
Colonel Kenneth D. Nichols. We decided that the district should not try to staff and manage all the required facilities in the town. Consequently, we contracted with Turner Construction Company to take on town management and operations. George Hoare, a vice president of Turner, had been the project manager for construction of the Rome Air Depot, so Marshall and I were well acquainted with both him and the company. Turner organized a special company called Rowan Anderson, named for the 2 counties involved in the CEW site. They organized and operated the bus lines, garbage collection, the school system, the hospital, management of all the housing, the hotel, the fire department, central eating facilities, and practically everything else pertaining to town operation, including delivering coal to individual houses.
James Reagan Justice. We brought meat by the carload, we brought produce by the truckload, and we brought potatoes by the carload. At that time, there were 700 employees in the cafeteria alone.
Charles E. Norman. One wing of the cafeteria was a recreation room where we would meet and play ping pong. One of the big events for about once a week. They would get in a shipment of beer. It would come to the cafeteria, and after dinner, the group from the recreation room would be served beer.
Colonel Kenneth D. Nichols. The school system posed a special problem. The school population increased every day. Additional teachers and school buildings had to be made available as needed for children arriving at Oak Ridge from all parts of the United States and all having different backgrounds and educational needs.
Hetty Horton. The first newspaper that the school put out only put the first names of the children. They couldn't use any last names because some were famous scientists' children.
Paul Elza. I suppose most people here had 98% of their existence inside the gates.
Letta Orison, project spouse. People were so hungry for friendship. Everybody was a stranger. So you may have met your best friend sitting at the bus stop.
Mary Michelle, teletypist, K-25 plant. Security was pretty strict. I know that I belonged to a group for a while that called themselves the St. Stephen's Episcopal Choir, but we always had great parties afterward, and one of the guys started talking too much. The people kept saying, "Oh, this guy's going to say the wrong thing sometime to the wrong person." And sure enough, one day he vanished. I never knew what happened to him. He was definitely removed. I often wondered what happened to him.
Ernest M. Lees. I was amused on some occasions how well some of us were oriented on security. We'd get to talking with someone. Well, where do you work? Clinton Engineer Works. Yeah, I know Oak Ridge, but where? Who do you work for out there? Clinton Engineer Works. They couldn't even tell us Stone and Webster or whoever the other companies. They wouldn't say. Just Clinton Engineer Works.
Paul Elza. It was always taken for granted that no one was from here. One evening at a gathering, one of these dowager types from Cambridge, Massachusetts came up to me and said, "Mr. Elza, where are you from?" I said, "Well, ma'am, I'm from right here." She said, "You mean you were born here?" I said, "Yes, ma'am." And she said, "And you grew up here?" And I said, "Yes, ma'am, right here." And she turned to her husband across the room, and she says, "Oh, dear, come here. They're training some of the natives to work on the project." It was a thing of surprise if you found someone that happened to be born and grew up right here.
Colonel Kenneth D. Nichols. For all town problems, the residents were advised to call Roan Anderson. I really caught hell one day when Jackie phoned my office. Miss Olson told me that Mrs. Nichols was stuck in the mud and wanted to know what to do about it. Busy with the problem, I adhered to my own orders and simply said, "Tell her to call Roan Anderson, like everyone else has to do." That was the last I heard about it until I returned home for dinner. Then I heard plenty.
Oak Ridge, making U-235. By November 1943, the Y-12 plant was starting to show real progress. But gremlins in the production process bedeviled engineers for months. Although by February 1944, the plant had refined enough uranium to deliver some samples to Los Alamos, ultimately in July 1944, Lawrence and Groves decided to completely redesign the complex racetracks that refined the uranium to fix numerous problems and speed production.
Colonel Kenneth D. Nichols. Work on the plants themselves provided an ongoing challenge. Construction of the electromagnetic plant generated unexpected and difficult problems. The first Alpha building with the equipment for the first racetrack was completed and placed in operation on November 13, 1943, my 36th birthday. However, as a birthday present, it proved to be a real dud, as its operation ran into difficulties immediately. Operators could not sustain a beam in the calutrons. Vacuum could not be maintained because of leaks. However, the worst problem was that the magnets shorted out, causing us to stop operations completely to locate the cause. Groves was at his best or worst, depending on one's point of view, in pinning down the cause of the trouble. He was extremely disturbed about the situation, and his caustic comments and persistent inquiries irritated practically everyone. Even Ernest Lawrence received some sarcastic comments when he recalled that he had experienced a similar problem with his cyclotron. The stress, long hours of work, frequent meetings, major but honest differences of opinion, and flaring tempers generated hard feelings.
Graydon Whitman, mechanical engineer, Y-12 plant, special engineer detachment. They had had a lot of trouble with their startup. I was assigned to 92012, an Alpha building, in major repair. There was a shortage of people who knew a screwdriver from a pair of pliers. There were a lot of tough problems they were having.
Brigadier General Leslie Groves. One difficulty, which was unforeseen because we lacked experience with magnets of such enormous power, was that the magnetic forces moved the intervening tanks, which weighed some 14 tons each, out of position by as much as 3 inches. This put a great strain on all the piping connected to them. The problem was solved by securely welding the tanks into place using heavy steel tie straps. Once that was done, the tanks stayed where they belonged.
Arthur Holly Compton. Runs were made testing the chemical extraction process. Each test worked more successfully than the one before.
Graydon Whitman. At the end of 30 days of normal operation, a calutron was taken down and the U-235 recovered from the pockets. The thing was sent to a wash area where it was washed in dilute nitric acid, everything cleaned up, and all the parts brought back, and then reassembled. It's complicated. There was just a continuous line of calutrons to reassemble. It was like a production line. The drive to get this work done? I've never seen anything like it.
Colonel Kenneth D. Nichols. There was considerable question concerning operators. Would it take hundreds or even thousands of PhDs to operate the plant?
Connie Bowling, Staff Supervisor, Y-12 Plant. They sent some of us to Livermore, California to learn from E.O. Lawrence, who built the first Calutron. They didn't tell us where we were going, and Oak Ridge wasn't named. We didn't know any of the scientists that were training us. They didn't even have name cards, and there wasn't any writing down of anything. They trained us, and then we came back to the Y-12 plant. We had to teach for a whole year the operators how to work those Calutron machines. And for 1 whole year, that is all I did.
Colonel Kenneth D. Nichols. Tennessee Eastman started plans for training personnel and decided not to use PhDs to operate the control units. Instead, they planned to use girls from Tennessee having only a high school education or less. In Berkeley, many of the scientists were skeptical about this decision.
Louise Keaton, Control Panel Operator, Y-12 Plant. I graduated high school and then went to Oak Ridge to work. I just went directly to work. We called Calutrons cubicles. I was a cubicle operator. They were big on each side of a long aisle.
Marjorie Wells, Control Panel Operator, Y-12 Plant. They had a row of Calutrons that way and a row back this way. We were busy watching numbers on those things. We had to keep a certain ratio in order to get a better grade of separation of uranium. At first I looked at those and I thought, I'll never be able to keep up with this. But you do.
Louise Keaton. I operated 4, 2 on each aisle. I remember my badge number, 18157. When we went to work, we changed clothes into a blue uniform. Then, when we came out, we left that uniform, and it was laundered and ready for us for the next shift. It was fun. The cubicles sometimes would have flurries, what we called flurries, and you had to keep operating and adjusting knobs so that you could make good readings. If they got out of control, when they could get into flurries, we operated a knob between them and got them back, and they would make terrible noises. In the back of each one of the cubicles or Calutrons, there was a small window, and we were told never to look in that window.
Colonel Kenneth D. Nichols. Tennessee Eastman's proposal to train operators with only a high school education was working remarkably well. As each new unit was turned over to Tennessee Eastman by Stone and Webster, Ernest Lawrence, with a team of scientists from Berkeley, took over operations to eliminate the bugs in the unit. When they achieved a reasonable operating rate, they transferred the unit to Tennessee Eastman. As a result of my comparing production data for the various units, I pointed out to Lawrence that the young hillbilly girl operators were outproducing his scientists. He claimed that this was because his men were experimenting on ways to improve operations. Thereupon, I challenged him to make a production race between his PhDs and the young local girls. He agreed, and he lost. The girls won because they were trained like soldiers to do or not to do, not to reason why. In contrast, the scientists could not refrain from time-consuming investigation of the cause of even minor fluctuations of the dials. This little contest provided a big boost in morale for the Tennessee Eastman workers and supervisors.
Marjorie Wells. Most of the operators were women. The young men were gone.
Colonel Kenneth D. Nichols. We had difficulty finding sufficient technical talent. Fortunately, we seized the opportunity to select qualified men to form a Special Engineer Detachment, SED. The largest SED units were at the CEW and Los Alamos. At a Military Policy Committee meeting with James C. White, president of Tennessee Eastman, about the difficulties of finding sufficient operators, White commented on how helpful the Army had been. He turned to Admiral Purnell and asked, "What can the Navy do to help us?" In response, Purnell arranged for about 60 young commissioned officers with technical education to be assigned to the MED. They would be assigned to a separate dormitory they called Good Ship Never Sink.
The other major effort at Oak Ridge to refine uranium was known as the K-25 plant, a name derived from the plant's contractor, the Kellex Corporation, and uranium-235, which is often shortened in scientific speak to just 25. It relied on what was known as the gaseous diffusion method to separate U-235 from U-238, a process that had been the primary recommendation of the British scientists working alongside the Maud Committee and the Tube Alloys Project as early as 1941. The work had been expanded upon by Columbia University's John R. Dunning and others who designed a process to turn uranium metal into uranium hexafluoride gas that would be pumped through a barrier filled with tiny microscopic holes. Like Y-12, work began on K-25 long before scientists at Union Carbide, Kellex, and other labs had even figured out how to make such a porous barrier. The finished plant was housed in a mile-long, U-shaped building, the largest roofed building in the world at that time.
Hubert Barnett, Maintenance Supervisor, K-25 plant. Columbia University did the theoretical design of the plant. There had never been a diffusion plant before. I spent all my time working with Kellex on getting information, getting the proper drawings that we needed to train our people, because not only did we have to get qualified people, but we had to train them in maintenance activities that they've never been exposed to before. It was all special.
Mike Linden. I was actually working in Philadelphia for the General Electric Company when the War Manpower Commission said, "Get your tail to New York on Monday morning." Arrived in New York and went to work for the Kellex Company at Columbia University at the Nash Building doing vacuum testing. From there, the entire group eventually, except for a few of us, moved to Oak Ridge with Union Carbide.
Brigadier General Leslie Groves. The gaseous diffusion method was completely novel. It was based on the theory that if uranium gas was pumped against a porous barrier, the lighter molecules of the gas, containing U-235, would pass through more rapidly than the heavier U-238 molecules. The heart of the process was the barrier, a porous, thin metal sheet or membrane with millions of submicroscopic openings per square inch. These sheets were formed into tubes, which were enclosed in an airtight vessel, the diffuser. As the gas, uranium hexafluoride, was pumped through a long series or cascade of these tubes, it tended to separate, the enriched gas moving up the cascade while the depleted gas moved down. However, there is so little difference in mass between the hexafluorides of U-238 and U-235 that it was impossible to gain much separation in a single diffusion step.
Donald Trauger, Columbia University physicist, K-25 plant. To make weapons-grade material, we required many stages, many repetitions of the gas passing through barriers, and a little bit of separation with each pass.
Brigadier General Leslie Groves. This was why there had to be several thousand successive stages.
Donald Trauger. The barrier was tiny pieces that were an inch. An inch square was a fairly large piece at that time, but they envisioned that for a plant of K-25 size would require a large area of barrier in many little pieces that somehow fit together that you could measure it in acres. To go from these little pieces that were an inch square, about as large as they would make at the time, was a daunting undertaking.
Brigadier General Leslie Groves. The basic piece of equipment was the isotope separation column, 102 of which were arranged to form an operating unit, which we termed a rack. The column was a vertical pipe, 48 feet long, of nickel pipes surrounded by a copper pipe. The copper pipe was encased in a water jacket contained in a 4-inch galvanized iron pipe. The copper pipe was cooled with water at a moderate temperature. The columns were arranged in 3 groups, each of 7 racks, making a total of 2,142 columns.
Mike Linden. The entire system at K-25, success depended on being leak-tight, so far as possible. The helium mass spectrometer was a tool at the University of Minnesota that we used in doing our vacuum testing.
Brigadier General Leslie Groves. At first, the operation was not too satisfactory. We were badly handicapped by the complete lack of pilot plant experience, the lack of trained people, and, as it turned out, by an insufficient supply of steam. We were also plagued by leaks of the process material and by high-pressure steam leaks.
Colleen Black. My father worked for Midwest Pipe, and we were in the same building. It was huge, and the pipes would come down and would go on the machines, and our mass spectrometer machine would take all this air out of them, and then we would try to find where the leak was. We'd mark the pipe with glyptal paint, and they would take it back and fix the leak.
Brigadier General Leslie Groves. By October, it was evident that too much steam was leaking out at the screwed unions at the bottom and top of the columns. We decided, therefore, to replace all of them with new welded connections. By January, all the 21 racks were again ready except for a few small piping changes found to be necessary on the basis of our operating experience.
Colleen Black. I had no idea what was going in the pipes. They were great big pipes, little bitty pipes.
Hubert Barnett. I would say that we had 7,000 employees in the plant when the war ended. I'd say not over 50 people knew what the hell was going on.
Brigadier General Leslie Groves. It was not until January 1945 that these difficulties were entirely ironed out. Peak production was reached the following June.
William Wilcox, chemist, Y12 plant. K25 was so much more efficient. Less than 10% of the cost of what it was costing at Y12.
Late in 1944, engineers rushed to build a third plant, S50, that focused on another uranium refinement process known as thermal diffusion, developed by Philip Abelson. It became fully operational in March 1945, helping to feed slightly more refined uranium into the Y12 calutrons and speed up the refinement process there. Ultimately, it sped up uranium production by about a week.
Brigadier General Leslie Groves. If I had appreciated the possibilities of thermal diffusion, we would have gone ahead with it much sooner, taken a bit more time on the design of the plant, and made it much bigger and better. Its effect on our production of U-235 in June and July 1945 would have been appreciable. Whether it would have ended the war sooner, I do not know.
Los Alamos, Project Y. Even with the construction of vast production facilities and factories underway, scientists were only beginning in 1943 to design the bomb itself. That would be the task of the team Oppenheimer assembled on a remote mesa in New Mexico, part of the ultimately 54,000-acre site purchased by the government for about $440,000, known colloquially as Los Alamos. It would be a task, like many on the Manhattan Project, far larger and more complex than first imagined.
J. Robert Oppenheimer. The last months of 1942 and early 1943 had hardly hours enough to get Los Alamos established.
Brigadier General Leslie Groves. The task for which Project Y, as the bomb development was called, was brought into being, was without precedent. It would require the utmost in collaboration among civilian engineers, metallurgists, chemists, and physicists, as well as military officers, some of whom would have to use the final weapons in combat. Many of the most difficult problems encountered at Los Alamos could not even be anticipated until work was well underway throughout the entire project. For this reason, scheduling at the Y site was both definite and indefinite. The bomb had to be ready as soon as sufficient quantities of atomic explosives were available, yet no one could say when this would be.
J. Robert Oppenheimer. Even though we then underestimated the ultimate size of the laboratory, which was to have almost 4,000 members by the spring of 1945, and even though we did not at that time see clearly some of the difficulties which were to bedevil and threaten the enterprise, we knew that it was a big, complex, and diverse job. Even the initial plan of the laboratory called for a start with more than 100 highly qualified and trained scientists, to say nothing of the technicians, staff, and mechanics who would be required for their support, and of the equipment that we would have to beg and borrow, since there would be no time to build it from scratch.
Brigadier General Leslie Groves. The big problem in getting good people arose from the fact that the scientific resources of the country, particularly in this general area, were already fully engaged on important war work.
J. Robert Oppenheimer. The primary burden of this fell on me. To recruit staff, I traveled all over the country, talking with people who had been working on one or another aspect of the atomic energy enterprise, and people in radar work, for example, and underwater sound, telling them about the job, the place that we were going to, and enlisting their enthusiasm.
Arthur Holly Compton. Oppie drew to Los Alamos a group of exceedingly able and resourceful men. From Princeton, the University of California, the University of Chicago, the University of Minnesota, the University of Wisconsin, and many other institutions, they rallied to join him.
Robert R. Wilson, physicist, Princeton University. My God! I exclaimed to my wife as I hung up the phone. Robert Oppenheimer is coming to visit. We were then in Princeton, where I had been working at the university on a project to separate the rare bomb-making isotope of uranium. Oppie explained that he had been chosen to head up a new laboratory in the West, the purpose of which was to work out just how to assemble a nuclear bomb out of the fissionable material that would, as we then believed, be available in another year. Oppie asked me to join his new laboratory. I agreed on the spot. Then he suggested that we go on to convince my colleagues to come as well. To a man, almost, they did.
Bernice Broad, project spouse of physicist Robert Broad. It was wartime Washington, early in March of 1943, when our friend, J. Robert Oppenheimer, came to see us in our chilly living room. Heat was rationed, and our rented house in Chevy Chase was cheerless and damp. But Oppie did not notice. I could see he was burning with an inner fire as he told us about his new war project, to be situated in the desert of New Mexico. I remembered how he once had said that his two loves, physics and desert country, never existed together. Had he joined them at last? He was vague about everything, but his eyes had that special intensity, peculiar to him, when he said to me, "I think you will like that life up there, Bernice. It will be quite nice, even in wartime." He made it seem like high adventure rather than patriotic duty, and I felt it was not to be missed.
Edward Teller. During the winter, Oppie had asked me to help him with recruitment. As part of that task, I wrote a description for a prospectus without having seen the laboratory grounds. I mentioned, among other things, that the school was built around a small lake. When I arrived, I came face to face with that body of water. It was, and is, in the best of times, a pond. Fortunately, those whom I unintentionally led astray preferred teasing me to being angry. Brigadier General Leslie Groves. One other major handicap was that we could not hold out any financial inducement to the people we wanted. It had been decided, after consultation with the Military Policy Committee, that, in keeping with the general policies of the OSRD, Office of Scientific Research and Development, we should not offer any increase in pay to people recruited for the Manhattan Project. However, academic personnel who had formerly been paid on the basis of a 9-month work year were given increases whereby they were paid for the full 12 months of work at the original monthly rate.
Colonel Kenneth D. Nichols. Dr. Conant had suggested that in view of the secrecy and the military nature of the work, we commission the scientists as officers in the Corps of Engineers and operate Los Alamos as a military laboratory. Oppenheimer was amenable to this type of organization, and he actually took initial steps toward becoming a commissioned officer.
J. Robert Oppenheimer. For a time, there was support for making it a military establishment, in which key personnel would be commissioned as officers, and in preparation for this course, I once went to the Presidio to take the initial steps toward obtaining a commission.
Colonel Kenneth D. Nichols. Oppenheimer ran into difficulties with the military concept when he tried to recruit Robert F. Bacher and Isidore I. Robbie. They both refused to accept commissions.
Robert R. Wilson. Robbie and Bacher, and perhaps others, managed to talk Oppie out of his determination to have everyone in the new lab inducted into the Army. Before that, as Oppie and I had traveled about the country on various missions connected with the Los Alamos Project, we had argued fiercely about his suggestion of our becoming soldiers in uniform. I argued the impracticality of scientists taking arbitrary orders from above. All the orders from above that I had seen for the past year had seemed a bit nonsensical. Nor are scientists at their best in unquestioningly following orders. I wondered if we could function at all in those circumstances.
Luis Alvarez. It wouldn't have worked. Bob Wilson and Joe Kennedy, for example, who were under 30 but led the experimental nuclear physics and chemistry divisions, would have been unable to argue with more senior but less knowledgeable officers. I don't think science can be done under authoritarian arrangements. Young people very often know better than their elders.
J. Robert Oppenheimer. We had a long hassle about that. In a letter which reached me early in 1943, signed by Groves and Conant, it was agreed that initially the workers in the laboratory would be civilians. It was contemplated that later, at the more critical phases, the key people would be commissioned. That plan was dropped, essentially because the numbers got so big and there was no need for it, and it became impractical.
Lieutenant Colonel John H. Dudley. We set up an office in Santa Fe on the 4th of January 1943. A few days later, we set up an office for Oppenheimer in another building. The initial construction contract looked like $300,000. Within a year, that first contract had gone to $7.5 million, a 25-fold increase, and it was only the first contract. There were many others because there were major difficulties in the construction and major expansions.
Brigadier General Leslie Groves. From the beginning, the procurement of equipment and materials was difficult, not only because our needs were unusual, but because some all-important equipment could be obtained only by negotiation or borrowing from universities.
Hugh T. Richards, physicist, Rice University. The Manhattan Project requisitioned most of our lab equipment and tools. An Army inspector came to sign for and supervise the packing. He was, of course, completely baffled by most of the items and could only write down what we told him, but when it came to small hand tools, he beamed and insisted on more details. For example, pliers had to be identified as slip-joint gas pliers.
J. Robert Oppenheimer. It took from perhaps October or November 1942 until March of 1943 to get the rudiments of a laboratory. We stole a cyclotron from Harvard, some Van de Graaff accelerators from Wisconsin.
Edwin McMillan. Los Alamos had to get equipment, nuclear equipment. And I went to several laboratories that had cyclotrons of the right size, and the one that was best suited, in the best condition, portable, or as close to portable as a cyclotron gets, was the Harvard cyclotron. On my recommendation, it was taken, and for many years after that, some people at Harvard were very angry with me. Of course, in the meantime, construction was going on, housing, laboratories, and so on. Oppenheimer and his immediate staff arrived on March 15, 1943. So from the middle of March, perhaps 20 research people were there. I followed very shortly after that. Mrs. McMillan came on April 1st, and from then on, the laboratory grew rapidly.
McMillan was an early pioneer of the Berkeley Rad Lab with Lawrence, where he is credited with discovering beryllium-10. Even before the U.S. entered World War II, he decamped to MIT to work on the secret effort to develop radar before ultimately joining the Manhattan Project. He and Glenn Seaborg shared the 1951 Nobel Prize in Chemistry for their discoveries of beryllium-10 and plutonium.
Leona H. Woods. All the equipment, the cyclotrons, the Van de Graaff, the Betatron, the machine shop equipment and construction material, had to travel up the original amusement park ascent to the Mesa. Surprisingly, little of it fell over the edge. A dramatic story was that Sam Allison, who had driven to Santa Fe with everyone's ration coupons to buy liquor, was washed into the drain that comes through Espanola by a flash flood on his way back. Sam and the liquor were rescued safely, but the car suffered a few dents.
Stanislav Ulam. I received an official invitation to join an unidentified project that was doing important work, the physics having something to do with the interior of stars. The letter inviting me was signed by the famous physicist Hans Bethe. A student of mine, Joan Hinton, had left for an unknown destination a few weeks before. Soon after, other people I knew well began to vanish, one after the other, without saying where. Cafeteria acquaintances, young physics professors, and graduate students like David Frisch and his wife Rose, who was a graduate student in my calculus class, Joseph McKibben, Dick Tashik, and others. Finally, I learned that we were going to New Mexico, to a place not far from Santa Fe. Never having heard about New Mexico, I went to the library and borrowed the Federal Writers' Project Guide to New Mexico. At the back of the book, on the slip of paper on which borrowers signed their names, I read the names of John Hinton, David Frisch, Joseph McKibben, and all the other people who had been mysteriously disappearing to hush-hush war jobs without saying where.
Ensign Donald F. Mastick, U.S. Naval Reserve. I traveled to Los Alamos in early 1943 under rigorous security, being the second technical person in residence there. Those were very active times. The pressure to move ahead was intense and exhilarating.
Robert Bacher. Nobody was supposed to know where we were going. I just disappeared into thin air.
Dorothy McKibben, Director, Los Alamos Lab Project Office, Santa Fe. 109 East Palace was the Los Alamos Santa Fe office, which served as a reception desk, information center, and travel bureau. Scientists arrived there breathless, sleepless, and haggard, tired from riding on trains that were slow and crowded. Often the traveler arrived days after he had been expected, and settled down with a sigh into a chair at 109 East Palace as if he could never move again. Most of the new arrivals were tense with expectancy and curiosity. They had left physics, chemistry, and metallurgical laboratories, had sold their homes or rented them, had deceived their friends, and then had launched forth into an unpredictable world. They walked into the thick-walled quietness of the old Spanish dwelling at 109 East Palace, expecting anything and everything, the best and the worst. The scientists often arrived in a frantic hurry. One dashed in hatless and breathless after a hectic rush from Johns Hopkins University and panted in dismay. "What, no ride-up for an hour and a half? Why, I cut short a seminar in order to get here now."
John H. Manley. In April of 1943, people started coming into Santa Fe, reporting to Dottie McKibben at 109 East Palace, asking for further instructions. Where did they go from there? She'd tell them how to cover the last leg, which was that 35-mile trip. I had to stay a few days when I arrived in Santa Fe, just about April Fool's Day, in order to get the accelerator from Illinois unpacked. It was in the freight yard, in a boxcar, and I had to make arrangements to get it on a truck and up to Los Alamos. I remember it was April 4th when I drove off with a man and his truck and the accelerator in the back end of the truck to my unseen destination of Los Alamos. I was quite concerned most of that 35-mile drive for the cargo in the back of the truck. It was a steep old country gravel road full of turns and sharp bends as it climbed the last 12 miles from the Rio Grande crossing at 5,500 feet above sea level to the 7,200-foot altitude of Los Alamos. We managed to make it and pulled up in the laboratory area.
L.D.P. King, physicist, water boiler reactor team. The first ride to the hill was memorable. Wandering through the several little Spanish villages past San Ildefonso Pueblo and then climbing an incredible series of switchbacks to get to the top of Los Alamos Mesa, all on a rough gravel road, is not easily forgotten.
Charlotte Serber, project spouse. When the first 100 or so scientists and their wives arrived, they met endless, unexpected situations and hardships. Everything was makeshift. Los Alamos was in no way ready to receive them. The housing had not been completed. The fence around the post was half finished. The tech area was an empty shell without power, gas, telephone, furniture, or equipment, and it was separated from the post proper only by fence posts.
J. Robert Oppenheimer. We started out the job with a large meeting. This would have been April 1943. That I called, all the people there, and a number of others whom I hoped to lure there, and many of whom were in fact later to come, to discuss the technical.
L.D.P. King. Oppenheimer's first step following the creation of Project Y was to hold a series of conferences at Los Alamos on April 15th to 24th, 1943. These meetings were to brief the initial staff on the present state of knowledge and chart a course for theoretical and experimental work at Los Alamos.
John H. Manley. If there were any groundbreaking ceremonies at Los Alamos, like champagne or cutting ribbons, I was unaware of them. Most of us who were there felt that the conference in April 1943 was really the groundbreaking ceremony.
Emilio Segre. Oppenheimer had invited some 30 scientists to the gathering. including the future leaders of the project and consultants like Fermi and Rabi. In the conference's 5 sessions, Robert Serber systematically described all that was known concerning a possible bomb. Serber's lectures were followed by discussion of what to do, as well as by animated debates on the laboratory's organization.
John H. Manley. There were long discussions of all problems which could be foreseen and decisions on assignment of responsibilities.
Robert Bacher. It was mostly devoted to elaborating the unknown physics information that was needed for knowing whether an atomic bomb would work or not. There were fundamental things where the information just wasn't known. For example, nobody knew how fast the neutrons came out. Some of them were known to be delayed, but even the ones that came quite promptly, you could say, well, they probably come right away. But they had to get out of there in a time like 10 raised to the 8th power seconds. That's 100th of a millionth of a second. And nobody had any idea of whether that was it at all. Any measurements made up to that time only went down to about 100th of a second.
Edward U. Condon. Notes on opening lecture by Robert Serber, Los Alamos, April 1943. The object of the project is to produce a practical military weapon in the form of a bomb in which the energy is released by a fast neutron chain reaction in one or more materials known to show nuclear fission.
Viktor Weisskopf. Not much more was known than the fundamental ideas of a chain reaction.
J. Robert Oppenheimer. My directive was to lose no day in preparing an atomic bomb. The definition of an atomic bomb was that it should be at least equal to 1,000 tons of TNT in explosive force. This sense of pressure started at the beginning and never let up.
Charlotte Serber. Everyone was put to work, usually at unfamiliar jobs such as rigging, teamstering, chauffeuring, and clerking. I had been hired on the project as the scientific librarian, but since no books or reports had arrived yet, I also did another job. For the first month or 2, I worked in the director's office, helping Priscilla Green, the executive secretary.
John H. Manley. It is hard to recreate the atmosphere of those days. Let me try with an illustration. Just before Los Alamos really got going, the last measurements on how much uranium-235 might be needed for a weapon had increased over the previous low estimate by almost a factor of 2. It was about 5 kilograms in absolute amounts. These 5 kilograms meant nearly 2 months extra production for each weapon. Maybe, if we were really clever and got an extremely good material that could reflect back neutrons and behave properly, we could get back most of that factor of 2 that we had just lost. We were playing that kind of a game almost continually. You get experimental results which say things are worse than expected. Then you try to be smart and get some better material or a new device or do things another way.
J. Robert Oppenheimer. We were building a town at the same time that we were building the laboratory.
Robert R. Wilson. We were small enough in numbers to be put up at Fuller Lodge, the elegant central log building of the Los Alamos School. There the grocer, the plumber, the schoolmaster were also housed. There we all took our meals, under the baleful eye of the spinster dietitian of the school, who was now watching in stern disapproval our food habits, our conversations, our moral convictions, our politics. We failed on all counts. Since then, I have also had occasions to try to set up an eating facility and am more sympathetic. At the time, the possibility that she was a Nazi agent trying to starve us to death did not seem all that far-fetched.
Emilio Segre. Fermi, Rossi, I, and perhaps some other Italian-speaking physicists were lunching one day during this period at Fuller Lodge, and, as usual, we slipped into Dante's language. As usual, talking loudly. General Groves was nearby, and he let us know that he did not like us speaking Hungarian in public. He delicately hinted that if we wanted to speak foreign languages, we had better go into the woods.
Robert R. Wilson. For a time, was it weeks, or was it only a few days, we happy few ran the project. We were the project. Then other people, rank outsiders, began to arrive.
John H. Manley. I think we really must have made some sort of a record, and I'm still moderately proud of the little part I had in it. All 4 of these accelerators, the cyclotron, 2 Van de Graffs, and a Cockcroft-Walton, were operating and giving data on experiments within 2 or 3 months after they were trucked up to Los Alamos. This would have been a feat on any university campus, but at Los Alamos, the buildings weren't even finished. The workmen were still in there. Special wiring and plumbing had to be installed for all of these machines, and shops and stocks and everything else were just getting organized. I can add to the picture of our early complications by reminding you that the only telephone line to Los Alamos from the outside world was a Forest Service line. If you manipulated the crank on the side of the box with enough vigor, sometimes you got a response from the outside world.
Franklin D. Roosevelt, letter to J. Robert Oppenheimer, June 29, 1943. The successful solution of the problem is of the utmost importance to the national safety, and I am confident that the work will be completed in as short a time as possible as the result of the wholehearted cooperation of all concerned. I know that you and your colleagues are working on a hazardous matter under unusual circumstances.
Arthur Holly Compton. By early July, experiments with the cyclotron were underway.
Hugh T. Richards. For a couple of weeks in July, our group had the world's supply of plutonium, a barely visible speck, a few hundred micrograms prepared by cyclotron bombardment at Washington U, St. Louis. We compared the neutrons emitted from our small plutonium sample to a known U-235 sample. This was in fact the first experiment completed at Los Alamos, and everyone in the group had devoted all 3 hours to the project.
J. Robert Oppenheimer. We were finding out things that nobody knew before.
Los Alamos. Working on the Mesa. The earliest estimates for the Los Alamos laboratory imagined just a few hundred personnel, but the population jumped by more than that effectively every month through the end of the war. Los Alamos' population stood at 3,500 by the end of 1943, about 5,700 by the end of 1944, and more than 8,000 by the end of 1945. All of their supplies to support the new community and laboratory complex and all of the new personnel would have to be trekked over a small, treacherous 25-mile road.
Brigadier General Leslie Groves. As the work got underway, some amazing rumors began to circulate through Santa Fe, some 30 miles away. Typical of these was that old standby that we were building a home for pregnant WACs, soldiers from the Women's Army Corps. The nearby local population followed the construction of the enclosure's fence with great interest to see whether it was designed to keep people in or to keep them out.
Dorothy McKibben. Santa Feans soon became accustomed to the queer ways of the scientists. They claimed they could spot these people from a great distance. Frequently, a clerk in a shop, prompted more by Western hospitality than by curiosity, automatically inquired, "Where are you from?" The answer was always a stammered, "Box 1663," as the speaker faded into the background. Security allowed them to say no more. Santa Feans knew what Box 1663 meant and felt smug about it.
While P.O. Box 1663, the mail drop for the scientists atop the Mesa, is the most famous mailing address of the Los Alamos lab and Project WWII site, the military utilized more than a half-dozen specific P.O. boxes for the site, including number 180 for military and technical staff and number 1539 for medical staff.
Brigadier General Leslie Groves. After a number of Navy officers had been assigned to the project and were seen on the streets of Santa Fe, rumors burgeoned about the new type of submarine that was being perfected on the hill, as Los Alamos came to be known locally. Although the nearest navigable body of water was many hundreds of miles away, this rumor sounded entirely plausible to a number of people.
Edward Teller. The newly established laboratory procedures were as strange as our setting. Almost all of us were accustomed to an academic atmosphere, to having time to sit and think quietly by ourselves, to nurturing a novel idea slowly, and to casual chats with colleagues. But at Los Alamos, almost constant collaboration was necessary. All the work was done at a feverish pace, and one's new good idea, once hatched, could be taken away and given to others to develop, which, for many scientists, felt a little like giving one's child to someone else to raise. Stanislav Ulam. It is difficult to describe for the general reader the intellectual flavor, the feeling of a scientific atmosphere. There is no specific English word for this impression. It was on the first or second day in Los Alamos that I met Richard Feynman and remarked to him about my surprise that E equals mc square, which I of course believed in theoretically, but somehow did not really feel, was in fact the basis of the whole thing and would bring about a bomb. What the whole project was working on depended on those few little signs on paper. Einstein himself, when he was first told before the war about radioactive phenomena showing the equivalence of mass and energy, allegedly replied, "Ist das wirklich so? Is that really so?"
Paul Numeroff, chemist, Special Engineer Detachment, Los Alamos. The laboratory was quite a surprise. To find such a superb facility on the plateau of a mountain in the wilds of New Mexico had to be the last thing anyone would expect. Nothing was lacking. It had everything that any chemist could want. There were 5 civilians and another soldier working there already. I was the 6th chemist. These men, and another who joined us later, were to be my scientific colleagues for 22 months.
Frederick de Hoffmann, physicist. Meetings on subjects under consideration occurred spontaneously. It took me many years to realize that all the instant problem-solving I had seen was not the rule of how physics got done, but the rare exception. At Los Alamos, one really expected it to be the rule.
Rudolf Piles. In return for the isolation of the place, Oppenheimer had wrung from Groves the concession that there was to be no compartmentalization within the laboratory. Every scientific member was allowed to know everything that went on in a laboratory, except for a few strictly military matters. This helped greatly to make the work efficient.
Brigadier General Leslie Groves. Compartmentalization of knowledge, to me, was the very heart of security. My rule was simple and not capable of misinterpretation. Each man should know everything he needed to know to do his job, and nothing else.
Colonel Kenneth D. Nichols. Groves ardently supported compartmentalization of the atomic bomb project. The scientists did not favor the idea, as it directly contradicted the belief that science thrives on the free exchange of all information. At Los Alamos, they insisted on complete, open discussion of all aspects of bomb design and won the support of Oppenheimer. Groves reluctantly approved it.
Leona H. Woods. The internal policy at Los Alamos was that everyone there with sufficient technical background had complete access to all information.
J. Robert Oppenheimer. It turned out over and over again this was a wise policy. Good ideas came from places that you would not have expected. Enthusiasm and understanding could be generated because people knew what it was all about.
Paul Numeroff. Every Monday night in the smaller of the 2 theaters at Los Alamos, there were reviews of the status of the project. What was going well, what was not going well, what was being done to solve problems. Often there were guest speakers from other laboratories around the country. It was exciting, stimulating, and even awe-inspiring to be in the presence of these luminaries, men of whom I had heard and whose publications I had read.
Luis Alvarez. Any properly cleared technical person could attend, and anything and everything about the secret work of Los Alamos could be discussed.
Rudolf Piles. One of the groups would present a report on its work. He would also announce any interesting news, such as the results of some crucial tests or the arrival of some samples of uranium-235 or plutonium. The meetings were held in the closely guarded cinema.
Lieutenant Dr. Henry L. Barnett, pediatrician, Army Medical Section, Los Alamos. I went to the colloquia and I didn't understand very much. Louis Hempelman at one point left a lecture and said there was only one word he understood, and that was Fermi.
Joseph O. Hirschfelder. As each new problem developed, experts were recruited to solve that problem. For example, I was brought in to prescribe the characteristics of the gun and gunpowder to be used in the enriched uranium atom bomb. In 3 weeks, I completed the final specifications for the internal ballistics of the gun and the charge of gunpowder. My situation at the end of the first 3 weeks represented a typical personnel problem at Los Alamos. After the expert had solved his problem, what did you do with him? Generally, the expert was transferred to some other problem area where he might or might not be knowledgeable. By the time the atom bomb was tested, Los Alamos was 3 deep in experts.
Edward Teller. Project Y, as Los Alamos was codenamed, was perennially short-handed. By the time Los Alamos was organized, most American scientists were already involved in war work. The several talented British physicists, among them James Tuck and Rudolf Peierls, were particularly appreciated because no one needed to orient these newcomers to the work. The British were firmly convinced, then and afterwards, that they had started the atomic bomb project with their tube alloy program. The following summer, another member of the British contingent, Klaus Fuchs, arrived after having spent some months working at Columbia.
Paul Numeroff. Fuller Lodge's upper floor was used for visitors, and the ground floor was a large open auditorium. A piano stood at one end. On the evening of my memory, on my way back to the lab, I heard someone at the instrument. I stopped to listen. I recognized the pianist as Otto Frisch, who, with his aunt, Lisa Meitner, first estimated the energy release in nuclear fission. I waited until he had finished the magnificent Mozart sonata he was playing, and then applauded. He stood up, smiled, and waved. I waved in return, and continued on my way. The experience was surreal.
Victor Weisskopf. The great world of international physics was assembled inside the fence. Eugene Wigner. The Hungarian scientists working on the Manhattan Project, principally Szilard, Teller, von Neumann, and Wigner, were thought to be queer by the Americans. They often called us the Martians. The label was unreasonable. We Hungarians had no more contact with Mars than they did. But we had imagination, and some far-reaching desires. A spur to our success was probably the fact of our forced emigration. Emigration can certainly be painful, but a young man with talent finds it stimulating. Outside your own nation, you lack a ready place. You need great ingenuity and effort just to find a niche. Hard work and ingenuity become a habit. Otto A. Frisch. Niels Bohr also came to Los Alamos. He arrived with his son, Owe. In the autumn of 1943, Niels Bohr had escaped from Denmark when he and his family crossed the Sound to Sweden in small boats on a dark night. Word had gone round that the Germans were about to pick up and imprison all the Jews in Denmark, and Bohr had a Jewish mother.
Margrethe Bohr, spouse. We had to get away the same day.
Oh, a Bohr. The stay in Stockholm lasted only a short time. A telegram was received from Lord Cherwell with an invitation to come to England. My father immediately accepted, and requested that I should be permitted to accompany him.
Otto A. Frisch. He was taken in a mosquito bomber, seated in the bomb bay, where he became unconscious because the headphones didn't fit his very large head, and so he didn't hear when the pilot told him to turn on the oxygen.
J. Robert Oppenheimer. The Royal Air Force was not used to such great heads as Bohr's.
Oh, a Bohr. The pilot realized that something was wrong when he received no answer to his inquiries, and as soon as they had passed over Norway, he came down and flew low over the North Sea. When the plane landed in Scotland, my father was conscious again.
J. Robert Oppenheimer. Once in England and recovered, he learned from Chadwick what had been going on with the atomic bomb. To Bohr, the enterprises in the United States seemed completely fantastic.
Edward Teller. When I heard that Bohr was coming, I began looking forward to reminding him that he had said it was impossible to build a fission weapon. But Bohr spotted me at the end of a long corridor, came running, and immediately squelched my chance of having been right. "Teller," he said, "didn't I tell you that you could not make a nuclear explosive without turning the whole country into a huge factory? Now you have gone ahead and done it.
J. Robert Oppenheimer. Letter to Brigadier General Leslie Groves, November 2nd, 1943. After you gave me the list during your last visit of the men whom we may expect from the United Kingdom, it occurred to me that it might be wise, before they arrive here, to give them new names. This refers especially to Niels Bohr. I am thinking of the fact that mail will be addressed to them, that they may on occasion originate or receive long-distance calls, that they will be making some local purchases, and that for all these routine matters it would be preferable if such well-known names were not put in circulation. It has, in fact, troubled us some that we are forced to place calls for Dr. Conant, Fermi, Lawrence, etc. This does not happen very often, but in view of the fact that we try not to use these names over the telephone, the placing of the calls themselves seems to us rather unwise. I doubt whether at this late date it would be practicable to assign new names to those who have been associated with the project in the past. In the case of Bohr and Chadwick, I think it would be advisable to do so before they get here. Sincerely yours, J.R. Oppenheimer.
Edward Teller. One of the more futile security measures was to change distinctive famous names into common ones. Those of us who were not so famous suffered only a minor deprivation of identity. Our driver's licenses were made out with a number instead of a name, and Post Office Box 1663, Santa Fe, New Mexico, instead of an address. But Niels Bohr was famous, so he was transformed into Nicholas Baker. The group of us who had known him at his institute in Copenhagen soon modified that alias to Uncle Nick. Stanislav Ulam. It was well known throughout Los Alamos that Nicholas Baker was Niels Bohr. Nevertheless, his true name was never supposed to be mentioned in public. At one colloquium, Weisskopf referred to the well-known Bohr principle. "Oh, excuse me," he fumbled, "the Nicholas Baker principle." General laughter greeted this security breach.
Arthur Holly Compton. At the order of General Groves, some of us who were known to be associated with work in atomic physics were given fictitious names to be used when away from our home bases. This precaution led into a variety of amusing and sometimes embarrassing incidents. I well recall an experience at Cheyenne, Wyoming. Trouble had developed at the Hanford plant. General Groves requested me to fly out at once. For the first time in nearly 3 years, I was permitted to travel by air. I was handed tickets in the name of Black. It was late at night, and I had been sleeping on the plane. After a pause at the Cheyenne airport, the stewardess was checking over the names as we returned on board. "Name, please?" I was puzzled. I remembered that I had been given the name of some dark color. Was it black or brown? Fortunately, I guessed right, and the stewardess let me pass.
Bernice Brode. The strangest feature of all to us was the security. We were quite literally fenced in by a tall barbed wire barricade surrounding the entire site, and patrolled along the outside by armed MPs. We felt cozy and safe, free from robbers and mountain bears. We never locked our doors. In our second year, extra MPs were sent to guard the homes of the Oppenheimers and Captain William Deke Parsons, making round-the-clock patrols. Some of the practical housewives cooked up a scheme to use these MPs as babysitters in the immediate neighborhood. What could be safer than a man with a gun guarding the precious small fry? The children were sure to be impressed and behave accordingly. Martha Parsons never hired a babysitter as long as the MPs remained around her house. And Kitty Oppenheimer once got real service when the guard came to the front door of the house she was visiting to tell her that little Peter was crying. Soon after, the sergeant in charge put his foot down. No more babysitting for his crack MPs.
Ralph C. Sparks, Special Engineer Detachment. At one of our regular Wednesday evening security lectures, this one on loose talk in the barracks, Major De Silva announced that last Monday night, about 10:30, there were 5 soldiers holding a discussion about their work in the tech area. It occurred in Barracks C at the West End. Then came the usual stern warning: if this ever happens again, there will be a court-martial and a firing squad will be summoned to carry out the punishment. The 5 who were discussing our problems in the tech area were Sandy Simons, Bob Aldridge, Louis Tricot, Jim Maxim, and me. All 5 of us knew there was a G2, intelligence, agent in that group, but we didn't know who he was. As a result, none of us would speak to each other for several months. After the war was over, I visited Jim Maxim at his home in Maine, and he finally admitted he was a G2 agent and had turned us in to Major De Silva. He was very apologetic and sad as he related what his duties were while he was in the Army.
Brigadier General Leslie Groves. By the end of the war, the Meds force of creeps, as they became known, numbered 485.
Jane S. Wilson, project spouse. Because any representative listing of project personnel would have revealed a suspicious concentration of nuclear physicists, such lists were forbidden. For this reason, we were prohibited from depositing money in Santa Fe, and all our banking was done by mail. Automobile licenses and New Mexico state income taxes were made out to numbers rather than to names. Driver's licenses were also anonymous. As far as the New Mexico records were concerned, one was driver 66 or driver 23.
Lieutenant Colonel John Lansdale. We established a system of monitoring telephone calls and mail. We established a post office, you might say, down in Santa Fe in an office. We censored all mail on a spot-check basis, and the mail of the more important scientists and those upon whom we had derogatory information 100%.
Jane S. Wilson. Our mail was censored. Furthermore, our correspondents were not supposed to know that it was censored. The method was simple. Mail went into the box unsealed, the censor read it, sealed it, and sent it on its way. Or, if he didn't approve of the letter, he sent it back. Sometimes the system proved useful. If one of us intended to send a letter with an enclosure, such as a check, and then forgot to enclose it, the letter would come back with a note from the censor, politely chiding the sender for his absent-mindedness.
Emilio Segre. The British mission, headed by Sir James Chadwick, included among others my old friends Rudolf Peels, Otto Frisch, and P.B. Moon. The British mission unfortunately also included Klaus Fuchs, a German refugee who became a Russian spy. I had exchanged only a few words of introduction with him, but he passed under our window every day at noon, presumably going to lunch. Elfrida noted his sad aspect, and not knowing who he was, nicknamed him Il Poverino, the poor soul. She was dismayed later in hearing that the Poverino was a spy.
Brigadier General Leslie Groves. The most disastrous break in security was that resulting from the treasonable actions of the English scientist, Klaus Fuchs. Our acceptance of Fuchs into the project was a mistake. But I am at a loss when I try to determine just how we could have avoided that mistake without insulting our principal war ally, Great Britain, by insisting on controlling their security measures.
Ralph C. Sparks. It was ironic that there were only about 100 scientists who had white badges that entitled them to know everything that went on in the tech area. One such white badge man was Klaus Fuchs, one of the physicists who came to Los Alamos with the British mission.
Edward Teller. Fuchs, a polite and gracious bachelor, was generous with his time. He was willing to help with any project, whether it was to discuss a colleague's problem and suggest possible new approaches, or to act as a chauffeur for wives whose husbands had no time for that. His services earned him a fond spot in many hearts.
Luis Alvarez. When there were parties at Los Alamos, he would take care of the children of the people who went to the parties, so he had an excuse not to go. He was not a particularly social person. I recognized him and nodded to him in the halls.
Robert Bacher. He was a very quiet, very retiring person.
Luis Alvarez. A very retiring person.
Commander Norris Bradbury, U.S. Navy, head of E5, the Implosion Experimentation Group, Los Alamos Lab. I think it must be said in fairness to Fuchs that he worked extremely hard and effectively for Los Alamos and this country. He appears to have a divided or double loyalty. I think his accomplishments at Los Alamos, it must be said, were very effective.
Much of the unique flavor of Los Alamos flowed from the personality and intensity of the lab director, J. Robert Oppenheimer, whose role ranged from chief administrator to recruiter to something of a scientific mascot.
Joseph O. Hirschfelder. Oppie was a frail, sensitive, lonely man whose life was tragic. When he was 13 years old, he had tuberculosis, and his parents took him to New Mexico, where they bought a ranch in a mountain valley far from any habitation. There, Oppie whiled away the time while recuperating by studying Sanskrit. He was absolutely brilliant. However, in spite of Oppie's eminence as a physicist, he published very few articles. Indeed, he set such high standards for his own research that he could seldom satisfy his own standards. This made him unhappy. Oppie had a wonderfully clear understanding of the basic principles of physics and had a genius for finding other people's mistakes. Thus, physicists from all over the world came to him for advice and help.
Otto R. Frisch. Oppenheimer used to greet newcomers with the words, "Welcome to Los Alamos, and who the devil are you?" His slight figure with the broad-brimmed pork pie hat was unmistakable.
Rudolph Piles. On our first evening there, the Oppenheimers asked Genia and me for dinner. This started with dry martinis, and we each had 2. We did not then realize that the altitude substantially reduces one's tolerance for alcohol until one gets acclimatized in a week or so. After dinner, we found we had great trouble getting up from the table and walking home. This was only slightly aggravated by the fierceness of Robert's martinis. He had strong views on questions of style in food and drink. Martinis had to be strong. Coffee had to be black. When coffee was served in their house, there was never any cream or sugar on the table. They would be provided on request. But the hosts started from the assumption that the guests would want to have their coffee the proper way. Steak had to be rare.
Luis Alvarez. Remembering the unworldly and long-haired pre-war Robert, I was surprised to see the extent to which he had developed into an excellent laboratory director and a marvelous leader of men.
Brigadier General Leslie Groves. Naturally, I am prejudiced, because I selected him for the job. But I think he did a magnificent job as far as the war effort was concerned. In other words, while he was under my control, and you must remember that he left my control shortly after the war was over.
Hans Bethe. He knew and understood everything that went on in the laboratory, whether it was chemistry or theoretical physics or machine shop. He could keep it all in his head and coordinate it. He understood immediately when he heard anything, and fitted it into the general scheme of things and drew the right conclusions. There was just nobody else in that laboratory who came even close to him in his knowledge. There was human warmth as well. Everybody certainly had the impression that Oppenheimer cared what each particular person was doing. In talking to someone, he made it clear that that person's work was important for the success of the whole project.
Joseph O. Hirschfelder. Every Sunday, Oppenheimer would ride his beautiful chestnut horse from the cavalry stable at the east side of town to the mountain trails on the west side of town, greeting each of the people he passed with a wave of his pork pie hat and a friendly remark. He knew everyone who lived in Los Alamos, from the top scientists to the children of the Spanish-American janitors. They were all Oppenheimer's family. His office door was always open, and each of us could walk in, sit on his desk, and tell him how we thought that something could be improved. Oppie would listen attentively, argue with us, and sometimes dress us down with clever, cutting sarcasm. At all times, he knew exactly what each one of us was working on, sometimes having a better grasp of what we were doing than we did ourselves.
Edward Teller. I consider Dr. Oppenheimer's direction of the Los Alamos Laboratory a very outstanding achievement, due mainly to the fact that, with his very quick mind, he found out very promptly what was going on in every part of the laboratory, made right judgments about things, supported work when work had to be supported, and also, I think, with his very remarkable insight in psychological matters, made just a most wonderful and excellent director.
J. Robert Oppenheimer. I have never known a group more understanding and more devoted to a common purpose, more willing to lay aside personal convenience and prestige, more understanding of the role that they were playing in their country's history. Time and again, we had in the technical work almost paralyzing crises. Time and again, the laboratory drew itself together and faced the new problems and got on with the work. We worked by night and by day, and in the end, the many jobs were done.
Colonel Kenneth D. Nichols. Success remained about a 50-50 proposition. Faint hearts and pessimists had no place in the Manhattan Project. I always had the gut feeling that we would succeed.
Viktor Weisskopf. One of the most important factors that kept us at work was the common awareness of the great danger of the bomb in the hands of an irresponsible dictator.
Edward Teller. It was hard not to feel that we were far from our goal. Earlier, Bohr had told us that Heisenberg was working on the German atomic bomb. For those of us who knew Heisenberg and the many other talented German physicists, the idea of their work was deeply disturbing. The thought of how far the Germans might have come in the years since the discovery of fission was enough to give us all nightmares.
George B. Kistyakovsky. That was the driving force of Los Alamos.
J. Robert Oppenheimer. The deadline never changed. It was as soon as possible.
Life on Bathtub Row. Los Alamos, known as Site Y to the government and the Hill to most of its residents, provided odd living arrangements. A romantic desert mountain community, richly infused with Native American culture and history, hurriedly thrown together with government-issue furniture and bureaucracy mixed with some of the most advanced technology in the world.
Otto R. Frisch. I was given a room in one of the original school buildings, a magnificent blockhouse which was traditionally built from big tree trunks and generally known as the Big House. Here, on the whole, were the quarters for the bachelor scientists. Married ones were given individual houses, which were going up at a great rate.
Ruth Marshak, teacher. The housing office was in one of the ranch school buildings, and it was the housing office which we new, confused arrivals sought on our first morning. Locating any place on the mesa was difficult. The sprawling town had grown rapidly and haphazardly, without order or plan. Roughly in the center of town was Ashley Pond, a shallow little pool, with the laboratories on the one side and the hospital on the other. To the west stretched a section of 4 and 8 family dwellings, identical in appearance, hunter green in hue. This section terminated in tight rows of barracks, housing for the enlisted military personnel, which overlooked the horse pasture. East of the pond was the oldest housing, consisting of green duplexes for childless couples, 4-family houses for larger families, and Bathtub Row.
Rudolph Piles. The old log houses had the distinction of containing bathtubs as opposed to mere showers, and the street on which they stood was known as Bathtub Row.
Luis Alvarez. The Army built apartments in barracks style with 10 showers. The apartments came in various sizes, the commonest being 4 family units, with 2 families above and 2 below.
Rudolph Piles. We were told apologetically that no room was left for us in Bathtub Row or in any of the houses nearby in the more desirable part of town. There was only a flat on the other side of town. We said, never mind, when we live there it will become respectable. Sure enough, when the Fermis arrived a little after us, they moved into the flat above us.
Jane S. Wilson. The military administration, with what struck me as typical perversity, had given each apartment a splendid modern electric refrigerator with one hand and a hideous, curvaceous, very bleak wood and coal-burning range with the other. One frightened look at this item, familiarly known as the Black Beauty, and I was in tears.
Robert R. Wilson. Worst of all was the cook stove, an old-fashioned wood range. My wife had never seen such an object. Then, too, at an altitude of 7,200 feet, it did take an unconscionably long time to hard-boil an egg. When Oppie brought General Groves on an inspection tour, my wife felt that the time had come to make a strike, not only for herself, but for every housewife on the hill. "Yes, General," she simpered. "Everything is fine, just fine. One little thing. The stove. I can't get it to work, and we are growing tired of cold meals." "Nonsense," said the General briskly. "These stoves are wonderful devices. I was raised on them. I'm an old farm boy. Let me show you how it's done." The General marched into the kitchen and fiddled with the obdurate black beauty. The General's hands grew smudgy. Black spots dappled his tan uniform. Time passed. He was not able to light a fire. "There," said the General, wiping his hands against his pants. "You see how it's done?" He marched out of the kitchen, head very high. The next day, GI electric hot plates were distributed to every household on the site.
Jane S. Wilson. I did all my cooking on 2 hot plates plus my own electric broiler and electric roaster. With such implements, I would nonchalantly whip up dinner, occasionally for as many as 35. This was difficult, but not impossible, except when the power was shut off. There were periods when this happened frequently, sometimes for hours at a time. If dinner happened to be ready, we ate by candlelight. If our meal was not yet cooked, occasionally we did not eat at all.
Bernice Broad. All the kitchens faced on the road, so that the fronts of the houses were really the backs. Callers came in via the back or kitchen, doors from the steps that were just off the road.
Rudolph Piles. The houses were heated by hot air from a coal-burning furnace, and one thermostat served the upstairs and downstairs flats. Our living room contained the thermostat that controlled both our flat and that of the Fermis. We had to remember to set the thermostat to a higher temperature when we had a party and perhaps a log fire, to prevent the Fermis from getting too cold, and to set it down when we opened our windows, or the Fermis would get roasted. Not all ground floor tenants remembered these finer points, and there was a good deal of friction.
Kathleen Mark, project spouse. Perhaps the most surprising thing about living in a Los Alamos house was the service we received. When the coal bin was empty, or often before, men appeared in a large truck to fill it up again. When the wood box was empty, it was promptly refilled.
Alice Kimball Smith, project spouse. The mushroom-like growth was a constant source of jokes. One might be picking tall white yuccas and fiery paintbrush in a quiet mountain meadow one Sunday and come back 2 weeks later to find it covered with government trailers or Nissen huts.
Phyllis K. Fisher, project spouse. Nameless dirt streets and roads were located in reference to the water tower. One lived north of the tower or east of the tower. The growing town quickly outstripped its limited water supply and also put a strain on an inadequate power supply. Housing continually lagged behind the population increase. There were clearly too many of us for our meager resources. And so the weathered and worn water tower represented our point of reference, as well as our forlorn hopes for survival on our bleak mesa.
Ralph C. Sparks. The mess hall was still Army, and we had all come to call the West Mess Hall by a more appropriate name, Worst Mess Hall. One day at the noonday meal, the coffee, a huge stainless steel monster, failed to give coffee. The mess sergeant removed the lid and peered into the pot. He reached in and pulled out a large mop. The mop looked as though it had seen duty in World War I and had been in the pot since then. Somehow, we all lost our desire for coffee for some time.
T3 Eleanor Jerry Stone. Los Alamos was small and compact. A main road connected East Gate at one end with West Gate at the other.
Bernice Broad. The technical area, called Tech Area, T Area, or simply T, where the main work of the project was done, resembled a small factory. A 2-story clapboard building painted, of course, green. The windows were large and pleasant, like those in our houses, although innocent of any washing since the original putty was smeared on. Originally, the one building, designed as a laboratory only, was built along West Road, but we soon grew in all directions, adding wings wherever possible. The tech area had its own fence around it, and a special badge was required to enter the gate guarded by MPs. The badges came in assorted colors, indicating the areas to which the bearer had access. White was the highest form, also admitting the wearer to the testing area in the canyons. Mine was orange. Though one of the lower forms, it allowed me to roam at will inside T.
Charlotte Serber. The tech area originally contained a group of buildings named T to Z, respectively, which housed the administrative offices, laboratories, library, warehouse, and shop. From this modest beginning, the place mushroomed into so many buildings that to name them, we quickly ran through the English alphabet, moved into Greek and Hebrew, and finally into mathematical symbols. The first buildings were drab and badly planned, with soft, unvarnished floors, small windows, and poor incandescent lighting. Later, buildings varied from the elegant structure built for the chemists, which sported glass partitions, battleship linoleum, and an overabundance of fluorescent lighting, to the beaver-board chicken coop built for the theoretical physicists.
T3 Eleanor Jerry Stone. All activity in those days centered around the tech area and overflowed twice a day to the tech PX for coffee breaks. On my second day in Los Alamos, I was assigned to work in the tech PX. Although my Army job was classified communications, my tech area clearance had not been completed, and Army personnel did not remain idle. I reported for duty to Sergeant White, a dour-faced Arkansas boy, and was introduced to my first Spanish-speaking people, Ramon and Linda, both teenagers. They taught me the intricacies of putting together milkshakes. Soon it was coffee time, and the mob was upon us. Hardly could we recover from one rush when another came. I never had a chance to look at the clock until I was excused at 6 p.m. Then I headed dog-tired down the side of the road, straight from my bunk.
Charlotte Serber. When the public address system was installed, our favorite PBX operator happened to be on, and she christened the machine in dulcet tones. At the sound of the gong, it will be 5:30. Everyone, please go home. In about its second week of infancy, we still treated the PA as a fancy toy, serenading one of the senior scientists with happy birthday. Such frivolous behavior was officially discouraged, but nevertheless, practical jokes on the PA continued to crop up at times. An operator, by request, insistently paged Werner Heisenberg at intervals for 2 days. Finally, a sympathetic soul took pity on her and explained that if she really wanted him, she had better cable Berlin.
Bernice Brode. Every room in T had a loudspeaker over which came diverting messages. Attention, please. Will the person who took the Sears Roebuck catalog from Harold Agnew's room please return it immediately? Repeat. Immediately. Attention, please. Will the owner of the lady's blue bicycle with the outsized basket please remove it? The bulldozer is coming and the bicycle is in danger. I dashed out, for it sounded like mine. It was.
T3 Eleanor Jerry Stone. The paging system, however, was in almost constant use. Chanting for Kistyakovsky, Beta, Fermi, Teller, Mitchell, Serduk, Segre, Perlman, Lynchitz, as well as for hastily needed, little-known technicians, and 2 popular characters, J.J. Gutierrez and John Marsh, maintenance men. These last 2 must have been the busiest men in town. We paged them consistently 20 times a day.
Hugh T. Richards. The name most commonly heard over the loudspeaker paging system in the tech area was J.J. Gutierrez, a Hispanic in charge of the janitorial staff.
Otto A. Frisch. Most scientists worked in groups of about 12 people, headed by a group leader, but there were some exceptions. For instance, I was not put into any group, but worked for a while as a sort of visiting plumber, going round to see what various groups were doing and offering advice when required, particularly on questions of instrumentation.
Laura Fermi. Enrico was the leader of the F division, in which F stood for Fermi. When he arrived at Los Alamos, he managed to gather a group of very brilliant men. One of them was his imaginative friend Edward Teller, another was Herbert Anderson, Enrico's inseparable collaborator.
Herbert L. Anderson. 4 groups were placed in the F division. 1, under Edward Teller, pursued the theoretical study of the super, the hydrogen bomb, in which Teller had been engaged for some time. Egon Brecher headed another group on the Super, which was the experimental counterpart of Teller's. Fermi's greatest personal participation was in the other two groups, the water boiler group under LDP King and the group under me called F4. The water boiler Per King was building was an extremely simple nuclear reactor, and though small in size, only 1 foot in diameter, it could serve as a strong source of neutrons. It used enriched uranium in water solution, a novel product of the new atomic technology, undreamed of only 6 years earlier. My group, Darren Nagel, Julius Tabin, and I, was available for other problems that might come up.
Eugene Wigner. When people discuss the Manhattan Project, they often linger too long on the physicists. We had some wonderful chemists, too, whose work was essential to our success. Glenn Seaborg was my favorite, a tall, friendly, brown-haired real American. The nuclear chain reaction made plutonium, which had to be separated from the uranium in the reactor. With talented men assisting him, Seaborg did much of this separation work. After the war, Seaborg shared the 1951 Chemistry Nobel with Edwin Macmillan for related work with transuranic elements.
Ralph C. Sparks. Some of the scientists who came to my shop with their sketches of equipment to be made drew them on scraps of paper or an old brown paper bag. The scientist would proceed to enhance the sketch with a verbal description of what was wanted, which seldom concurred with the sketch. I would jot down the verbal description below the sketch, then sit at my desk and draw a conventional, three-dimensional machine shop drawing.
Bernice Broad. These SED boys were quite different from the regular post soldiers. They looked, in spite of the uniforms, like budding professors instead of combat troops. Shortly after they came up to the hill, some high brass from Washington came for a formal military review in the baseball field in front of the big house. All of us came with our children to see the show. The MPs, the post soldiers, the WACs, and even the doctors made a fine showing as they marched across the field. But the newly arrived SED boys were terrible. They couldn't keep in step.
Ralph C. Sparks. The 9812th Special Engineer Detachment in the Manhattan Corps of Engineers, otherwise known as SED, was indeed a very well-educated and skilled group of men. The information about our detachment published in 1946 said more than 35% of the men had college degrees, some with master and doctoral degrees. Most of the others had skilled training, and many had 10 years' experience. Many developments and patents were the work of this group of SED soldiers in the technical area. When I arrived on the Hill in 1943, there were about 188 men who had arrived.
George B. Kistchakowski. The Special Engineer Detachment was very important. General Groves insisted that, in distinction to technical staff civilians, most of whom lived quite comfortably in a highly hierarchically organized society, the enlisted personnel be given only what the Army regulations stipulated as the minimum comforts. Minimum housing, minimum recreation, minimum food facilities. And this meant 40 square feet per man in the barracks, including part of the recreation area. Try to recreate yourself in that area. The poor SEDs, of whom we had more than 1,000 at the end of the war, really felt themselves the pariahs of Los Alamos.
Val L. Fitch. At Los Alamos, I was assigned to an upper bunk in a recently completed barracks, a spot that was to be home for another year and 9 months. I quickly learned the Army's situation from the SEDs already there. We lived in single-floor barracks, roughly 60 men to a unit. As the summer and fall of 1944 progressed, the size of the SED contingent continued to increase as fast as new barracks were built. The fundamental dichotomy in the Army existence and the work alongside civilians troubled some of the SEDs. They considered themselves miserably exploited by the system. On the other hand, many of us found our work in the laboratory intellectually stimulating, and we spent long hours there working on and learning new things. We considered this Army assignment extraordinarily fortuitous.
Emilio Segre. On average, the members of this group were young, about 32 years old. Some who were a little older had barely passed 40 and were already quite famous. Several who would become famous later were about 20 years old at the time. There were 8 future Nobel Prize winners: Alvarez, Bethe, Bloch, Chamberlain, Feynman, Macmillan, Rabi, Segre. Oppenheimer was 39.
Bernice Brode. There were almost no old people. So those of us in our early 40s were the senior citizens. We had no invalids, no in-laws, no unemployed, no idle rich, and no poor.
Elsie Macmillan, project spouse. Los Alamos had a small hospital with only 2 bedrooms, a waiting room, a pharmacy, and an operating room, which at first could not be used because we didn't have the proper anesthetic for the altitude. We had only 2 doctors, James Nolan, who had been a cancer specialist and was the physician for the people who were there, and Louis Hempelman, who was the radiologist for the technical area. We had 3 nurses, Pete and Sarah and Peggy. Food had to be brought over from the lodge, and it got cold.
Dr. Louis Hempelman. I was supposed to be the medical director for the laboratory with specific emphasis on radiation. I didn't even know that there was such a thing as occupational medicine. We operated in the most primitive way, really. Then Oppie called me and asked me if I could get someone to take care of the health of the town, of the total population. I got a classmate of mine named Jim Nolan, who had gone into gynecology. He was trained as a surgeon and then went into obstetrics and gynecology. He was a very good obstetrician, fortunately, which was the main thing we had to deal with. Also, he was a good surgeon, so he could set bones and things like that.
Lieutenant Dr. Henry L. Barnett. Louis Hempelman, who had been in medical school with me, was a radiologist in Rochester. He always ranked first in the class, and I ran second. Louis asked me whether I'd be interested in a job where I would be doing pediatrics. I got an order I should report to 109 Palace Street in Santa Fe, New Mexico. There was a surgeon there that Louis had gotten, Jim Nolan, who was also in our class. The next one they wanted was a pediatrician, so they got me.
Shirley B. Barnett, project spouse. Since the hospital was centrally located, no operation or emergency went unnoticed by the local gentry. I remember waiting one night outside the hospital with Anne, Jim Nolan's wife, while Jim and Henry were in the operating room taking care of an emergency. Anne was expecting a baby within a week or 2. When a car drove up and the occupants spotted us standing in the shadows, they asked why the operating room lights were on. They wondered audibly if Anne's baby was being born. Anne stepped out from the shadows and reassured them. As the car drove off, Anne made a fervent wish that her baby be born during the day, so as to assure her some chance of a head start on knowing whether her baby was a boy or a girl. Her wish was not granted, but her child was born during a night of comparative quiet on the mesa. The announcement was made next morning to a proud community, who felt that the birth of its first child was something in the way of a major event, and a matter for loud huzzas. Our birth rate after this, Anne's baby was born in August 1943, was fairly high.
Ruth Marshak. The general was reputed to have complained to Dr. Oppenheimer about the number of children being born on the hill. Couldn't something be done about it? The general wanted to know. A jingle celebrating this remark went in part, "The general's in a stew. He trusted you and you. He thought you'd be scientific. Instead, you're just prolific. And what is he to do?"
Shirley B. Barnett. 80 babies were born during the first year, and about 10 a month thereafter. Rural free delivery, people said jokingly. Henry's pediatric practice increased steadily.
Elsie Macmillan. The birth certificates of all babies born there said, place of birth, box 1663, Sandoval County, rural. My God, was that box ever full of babies?
Bernice Brode. Our school at Los Alamos was the most exclusive in the country, and our worst problem. In the beginning, everyone was completely unrealistic about the school, and we all had to learn the hard way. The earliest organizers seemed to proceed on the assumption that the school would be the least of their troubles. With all those thoroughly educated people to be hired, why wouldn't it be a cinch to set up and run a fine school for their kids?
Rudolf Piles. The science teaching was weak. This paradox was explained by the fact that most of the teachers were wives of scientists and included some first-rate scholars. However, those with scientific qualifications preferred work in the laboratory, so teachers with poor science backgrounds had to teach science also.
Ruth Marshak. We teachers worked under difficulties. When an experimental blast in a nearby canyon would rock the school to its expensive foundation, there would be a frightened silence in the classroom, and then we would begin again on Henry Wadsworth Longfellow.
Phyllis K. Fisher. Our quiet was punctuated from time to time by explosions down in the canyons. These explosions were often enough to shake our flimsy houses and set all the pictures on the walls askew.
T3 Eleanor Jerry Stone. There were many loud blasts. When the ground shook and the air smelled of firecrackers, we knew the scientists were testing explosives. When I washed my hair, I could smell that firecracker smell, but it was combined with the smell of the pines.
Charlotte Serber. Until we had a formal personnel office in full swing, most housewives were transformed into working wives by the grapevine. Working conditions included 48 hours to the work week, 2 weeks of vacation with pay, sick leave, 1 day off a month for a shopping trip to Santa Fe, maids available through the housing office, and a nursery school for her children. The working wife's salary, which was set very arbitrarily, was influenced less by her previous work history than by the fact that she really had no bargaining power.
Bernice Brode. I worked for some months as a computer, as we computing machine operators were called then, in the theoretical wing at T. After 3 months of computer training, we were moved to the theoretical wing of T to work under mathematician Moll Flanders. After hours, Professor Flanders and his family contributed greatly to our musical life. All the family sang and played instruments, and Moll himself conducted our chorus and orchestra. He wore an unusual but becoming full beard, and when we asked why, he replied in his New England accent, "If you had 3 women in the family and only 1 bathroom, would you not do likewise?"
Edward Teller. A further source of unhappiness was the limited availability of domestic help. Michi, like most of the wives, eventually went to work at the laboratory in the computations division because of the terrible shortage of personnel. With Paul a baby, she had to have help to do so. At that time, household helpers were in such short supply that they were rationed.
Charlotte Serber. Within about 15 miles of Los Alamos, there are 3 Indian pueblos, 2 towns, and a number of small farms, the closest being San Ildefonso Pueblo. In May 1943, the security office granted us permission to bring San Ildefonso women up to do housework for the working women. An Army carryall was to transport the original 8 or 10 Indians up to the hill at 8:30 and down again at 5:30 each day. Most of us got from 3 to 6 half-days of work a week and were delighted at this unexpected relief from housework. As more and more people arrived on the hill, and because the press of work in the tech area never eased up, the demand for Indian maids grew tremendously.
Phyllis K. Fisher. It was always a thrill to visit the different Indian pueblos scattered throughout the valley, to get to know some of the local people, to begin to appreciate their art and philosophy, as well as their festivals. We came to realize that we were surrounded by a rich, intriguing, and very special world. Around us was a lovely area that invited exploration.
Bernice Brode. The Indian dances, whatever else they meant to the Indians, provided good fun and a show for everyone. Los Alamos people provided an enthusiastic audience, and the Indians liked it. Some of the dances were held on weekdays, but when it was understood that our men could come only on Sunday, their 1 day off, some of the dances were switched. The dances also increased in variety, we noticed, and we suspected the Indians were making up new non-traditional ones, since we were enthusiastic but uncritical and would not know the difference.
Paul Numeroff. One of the civilian men in the lab had his own car, and he would often arrange trips to several of the Indian pueblos in the area. One of them, San Ildefonso, was the home of a woman named Maria Martinez, who became famous for her black-on-black pottery. We would drive up to the central square of the pueblo and wait. Eventually, doors to the homes that faced the square would open, and Indian women would appear with their pottery carried in their large, billowing skirts. They would form a semicircle, place blankets on the ground, and put their pottery on them. Not a word was said. Buyers would walk up and down, pick up the pieces, and ask questions. It wasn't until much later in life that I appreciated fully what an opportunity I had missed. A 12-inch Maria Martinez plate, black on black, that I could have bought for $12 in 1944, now could be worth about $12,000 if it were even available from a collection. My problem was that $12 was almost half of my monthly paycheck.
Charlie Masters, teacher, Los Alamos School. A phenomenal amount of blackware was produced, for the Los Alamos folk had an insatiable appetite for these plain, rich bowls, plates, vases, plaques, and candlesticks. It became almost impossible to buy a new piece not sanctioned by the taste of the hill, or to find a potter with the time to make one. It cost me 4 Sunday visits to San Ildefonso, I recall, to buy a bowl of two-toned brown, or red, as the Indians prefer to call it, which I had rashly promised as a birthday gift.
Emilio Segre. The mess hall in Fuller Lodge had a porch opening onto a lawn, and from it we had a spectacular view on the Sangre de Cristo Mountains, dominated by the Truchas Peak, across the Rio Grande Valley. The view from Fuller Lodge could not fail to impress whoever saw it for the first time. The view from Fuller Lodge became even more dramatic in late spring and summer at 4 p.m., when every day a big thunderstorm started illuminating the horizon toward the Sangre de Cristo Mountains, with brilliant lightning crisscrossing the sky. The storm lasted a few hours, and by 8 o'clock it was over, giving way to a serene night. The phenomenon was perfectly regular. At noon, big cumulus clouds started forming in a sky that early in the morning had been perfectly clear. The clouds grew and rose in the sky until they climaxed in the afternoon's thunderstorm. These summer storms cooled the days which otherwise would have been hot in spite of the altitude. Thus the climate was most pleasant, with moderately cold winters that permitted skiing.
Edward Teller. In retrospect, it is hard to imagine where we found the energy to go hiking and horseback riding, visit the nearby Indian pueblos for festivals, explore the ancient Indian ruins a few miles away at Bandelier, give and attend parties, and manage routine chores while working long hours on the atomic bomb as well. But we did.
Rudolph Piles. The scope for leisure activities was limited. There was a cinema, but not much else. People with musical talents arranged music groups, barn dancing was popular, and there was a horsey set. There were also many parties, large and small. Being an army base, Los Alamos did not have a wine store, and drink had to be bought in Santa Fe. Whiskey and gin were in short supply, but there was plenty of Mexican vodka. As most Americans like martinis, a mixture was made with vodka in place of gin, and nicknamed Martinovich. John von Neumann consumed 15 of these one evening in our house. Next day he said, "I know my stomach has a cast-iron lining, but it must have developed a crack."
Edward Teller. Many activities took place on the mesa itself. I helped at the radio station, played chamber music, and had my only experience as a thespian when I played the part of a corpse in a production of Arsenic and Old Lace.
Bernice Brode. Little publicity was needed for a forthcoming play. Nearly everyone on the mesa had been part of the rehearsal, been approached for props, or been asked to help out in some way. So every performance was assured of an appreciative and capacity audience. After the play, it was the custom for players to come out in grease paint and be congratulated by their public. Then we pushed back the chairs and benches and danced until midnight to music often provided by Mr. Olmsted's jazz band. One of our biggest hits was Arsenic and Old Lace, with Betty Brixner as the old lady. Betty was a pretty blonde of 25, so she had a good deal of acting to do, but carried it off very well. The high spot of the show was the end of the last act, when the dead bodies were brought up from the cellar. It was kept top secret so well that the audience was unprepared to see Oppenheimer brought up stiff as a corpse and laid on the floor. Then Deke Parsons, then Bob Bacher, Cyril Smith, Harold Agnew, and others. Cyril Smith remarked on the way home that it was the most restful occupation he had on the mesa.
Val L. Fitch. Those of us who immediately got involved in the hiking, skiing, skating, and folk dancing activities came to love dearly that part of the country. Most of the noted physicists at Los Alamos hiked and skied, and I came to know more of them on the ski slopes than I did at work. Niels Bohr skiing, albeit modestly, was a memorable sight. Being gently chastised by Enrico Fermi for inadequately, in his opinion, filling in the sitz mark from a skiing spill was more an honor for me than a rebuke. Mrs. Rudolph Pyerls, directing traffic over all the ski slopes from the stoop of the warming hut at the bottom, is not to be forgotten. Where else in the Army could one on a moonlit night go skiing a few hundred yards from his barracks, as I did?
Shirley B. Barnett. The natural hazards of transplanting a large group of urban dwellers into a country where vigorous outdoor exercise is very much the thing took its toll. There were horseback riding accidents, skiing accidents, and even one ping-pong accident. Touch football provided its share of dislocations and sprains, with tennis trailing along behind. By the time the community had reached its top population, around 7,000, our vital statistics in relation to accidents were on par with any.
Otto R. Frisch. Teller had lost a leg in a traffic accident while young, but he never let on. His artificial leg merely gave him a slight limp, and he didn't mind going for long walks. He even often joined us when we went skiing, but then wore snowshoes rather than skis.
Stanislav Ulam. Enrico was fond of walking. Several times we walked all the way from Los Alamos down the walls of a canyon and along a stream to the Bandelier National Monument. It was a walk of 7 or 8 miles, during which we had to cross the stream more than 30 times. The walk lasted several hours, and we discussed many subjects.
Leona H. Woods. Enrico took me on the usual hikes around Los Alamos, such as climbing Lake Peak across the valley of the Rio Grande, one of the high peaks in the Sangre de Cristo range. We found arrowheads and marveled at the patience it took to chip out these weapons so carefully. Obviously, the Department of Defense was a cottage industry in those days, circa AD 1300. Pot shards were everywhere. It is puzzling how so many pots could have been broken along every trail.
Otto R. Frisch. On the long walks, which were his recreation, he liked to talk physics to his guard. One day he said pensively, he had acquired a good command of English but had never lost his Italian accent, "My bodyguard, now he knows so much physics, he will soon need the bodyguard himself."
Oak Ridge. Glimpsing plutonium. The work to refine plutonium at the Hanford Engineer Works in the dry desert of eastern Washington state really began across the country at Oak Ridge's Clinton Engineer Works, where the Manhattan Project first designed and built a pilot semi-works graphite reactor known as X-10, under the leadership of the University of Chicago's Met Lab and DuPont. That reactor, the first built after the Met Lab's December 1942 success with CP-1, produced the first meaningful amounts of plutonium the world had ever seen. Constructed on a crash schedule beginning in February 1943, the reactor was online by November, and the first plutonium emerged later that month.
Arthur Holly Compton. By mid-October, the pattern for the first experimental reactor at Chicago had been agreed upon. It was of prime importance that the pilot plant at Oak Ridge be of the greatest possible value to DuPont in building and operating the Hanford plant. Accordingly, Whitaker spent a considerable part of several months at Wilmington working with the DuPont men on the plans for the plant's construction and operation. A design was agreed upon that had considerable similarity to the Wigner plans for the Hanford production plant.
Alvin M. Weinberg. Wigner likes to say, I designed by myself the X-10 reactor at Oak Ridge in early 1943, but it really wasn't much of a thing. There really wasn't much design that had to be done there. I was responsible for deciding what the lattice spacing was, the geometry of the nuclear pile. The X-10 reactor was built in 9 months. Perhaps the most serious problem was the canning of the metallic uranium slugs. Each slug was 4 inches long and about 1 inch in diameter. It was placed in a thin aluminum can that was then welded shut. Unfortunately, the welded end caps sometimes leaked, and many slugs had to be rejected. But eventually, enough non-leakers were accumulated to load the pile. On November 4th, 1943, the X-10 reactor went critical for the first time. Fermi had come from Chicago to supervise, and though I was not there, I was told that all went pretty much as planned.
Charlie W.M. Mathis, Project Staff, X-10 Reactor. In this reactor, we transmuted uranium into small quantities of plutonium that were used for extraction process development and testing to evaluate its properties. We discharged the irradiated uranium fuel down the back of the reactor into a pit. On the other side of the wall were the handlers, dissolvers, dipping down to pick up the fuel elements.
Alvin M. Weinberg. The significance of the X-10 to Hanford was that nobody had ever extracted plutonium on a large scale. Separation had always been done on a micro scale. This was the first time in human history that mankind was handling radioactivity on this enormous scale. X-10 was the first reactor that produced significant amounts of heat, 1,000 kilowatts. Secondly, it was the first reactor in which sizable amounts, meaning gram quantities of plutonium, were produced, about 1 gram a day. The Hanford reactors, each one initially produced about 250 grams a day.
Colonel Kenneth D. Nichols. The pile operated beautifully and eventually reached a power level equivalent to 1,800 kilowatts, about twice the design capacity. We were jubilant. In December, 1.54 milligrams of plutonium were separated and shipped to the Met Lab for experimentation. In March, there was great excitement when the first gram of plutonium was produced. I felt elated. We were now on the road to success. Compton and Whitaker invited Groves and me down to the semi-works to see it. Compton opened the glass door and reached in under the ventilation hood to pick up a small glass vial containing a single gram of green liquid. He handed it to me. Whitaker hurriedly picked up a stainless steel pan and held it under my hand, saying, "For God's sake, don't drop it on the floor." As Groves reached for it, Whitaker grabbed it and replaced it safely under the hood.
Alvin M. Weinberg. I was awestruck when Sam Allison, who was then director of the metallurgical laboratory, showed a few of us a small vial filled with a green solution of a dissolved salt of plutonium, probably plutonium nitrate. So the crazy idea of manufacturing a new element on a large scale was not so crazy after all. It really worked.
Los Alamos. Designing the bomb. The main day-in, day-out work of the Manhattan Project scientists at Los Alamos was designing not one, but 2 different nuclear devices, using plutonium and uranium. They are competing, but not necessarily mutually exclusive, stories about the origins of the Thin Man and Fat Man names for the project's bomb designs. One story holds that the names were deliberately chosen to honor Franklin Roosevelt and Winston Churchill, or perhaps used by the military to confuse enemy surveillance, who had imagined the B-29s being modified to carry Thin Man and Fat Man were meant for VIP transport. By contrast, Robert Serber says the names instead were an homage to detective novelist Dashiell Hammett, with Thin Man, which featured a long, thin bomb design, honoring Hammett's 1934 novel of that title, and Fat Man, a legitimately fat and round bomb, named after the character Caspar Gutman in The Maltese Falcon, which had just come out as a Humphrey Bogart movie in 1941. As they got into the work, though, the design for Thin Man, the proposed plutonium-fueled gun-type atomic bomb, had to be abandoned, delivering perhaps the most severe crisis to Los Alamos of its short existence. Instead, thoughtful work and a quick pivot by Oppenheimer would lead to the bomb known as Little Boy.
Stanislav Ulam. Most of the physics at Los Alamos could be reduced to the study of assemblies of particles interacting with each other, hitting each other, scattering, sometimes giving rise to new particles.
Luis Alvarez. The easiest way to start a nuclear explosion is to bring 2 subcritical pieces of fissionable material quickly together in a gun to make a critical mass. A critical mass is not some absolute number of kilograms of fissionable material. The amount of fissionable material to be used depends on the density of the material chosen and its shape.
Edward Teller. Szilard's original idea for a fission weapon was simple enough. Start from one neutron and let it multiply. After sufficient neutron multiplication occurs, a few pounds of fissionable material will liberate energy equivalent to thousands of tons of high explosives. There is just one small hitch. That multiplication must occur in less than 1/1,000,000th of a second. Otherwise, the material will pre-detonate, fly apart with moderate energy before a full chain reaction can occur.
Robert Bacher. You've got to get it together pretty fast, because if you don't, it will just go poof as you put it together.
Edward Teller. The most obvious way to assemble the critical mass was to use a high-velocity gun to propel one half of the nuclear material into the properly positioned second half. But this solution created new problems. First, building a device that could be transported by plane was a challenge, and separating the fissionable material into two portions meant that the device had to be large. Second, shooting half of the material with sufficient accuracy, velocity, and reliability was difficult, and there was also a danger that the rebound from the impact of the projected material would break the system apart before the initiating neutrons could be injected and could multiply.
Edwin McMillan. The gun method. Firing two chunks of fissionable material together at high speed and then releasing some neutrons to start the chain reaction. The gun method was the method.
Robert Christie, physicist, Los Alamos lab. It was such a straightforward assembly that no one was worried about it. At that time, everyone felt that they could predict exactly what would happen.
Robert Bachner. This was indeed the method subsequently used to make the Hiroshima bomb. It had a number of difficulties, but it looked straightforward. And with the known nuclear constants of uranium-235, it should be something that could be done without a wholly new art being developed.
Edward Teller. Those problems proved only moderately difficult. Solutions to the mechanics of size and of combining the material were worked out, and the problem of rebound was overcome by activating a neutron source just as the halves were in proper position.
Robert Bacher. There seemed to be no reason why plutonium shouldn't work this same way too, though there was very much less known about its nuclear properties.
Edward Teller. After we had been working for a few months, a real difficulty showed up. We had assumed that a uranium or plutonium nucleus would not split unless it was struck by a neutron. In the summer of 1943, Emilio Segre discovered that uranium-238, plutonium-239, and plutonium-240 all undergo fission spontaneously.
Robert Bacher. When a pilot plant at Oak Ridge came into operation, we got some of the first samples out of that. We had decided we had to make measurements on this to find the nature of the work and to check for neutron emission. This was done, very fine physics, under the direction of Emilio Segre from Berkeley.
Emilio Segre. The difficult but important part of the work came with the study of plutonium-239. Once we had milligram samples, we soon recognized that plutonium-239 had a rate of spontaneous fission high enough to interfere seriously with the proposed methods of bomb assembly through pre-detonation. These findings, starting in April 1943 with a few counts, became firmer with better samples and longer observation times. We also checked the number of neutrons emitted per spontaneous fission.
Robert Bacher. What was found by Segre and his group at Los Alamos was that the material produced in this pilot plant at Oak Ridge had different properties from the material we'd had before. It emitted neutrons, indicating spontaneous fission. This created a major problem. The more we found out about how sensitive this was to the amount of irradiation in the nuclear pile where it was made, the more we became convinced that it just wasn't possible to make a bomb out of it. We were then struck with the difficult problem that, with the way we were making a bomb, using the gun assembly, you couldn't use plutonium. Plutonium was valueless to us. We were all glum. This caused a great crisis for the whole project.
Emilio Segre. By July 1944, our results brought the Los Alamos lab to a real crisis, although the relevant information was based on a few counts only. Spontaneous fission in plutonium was so frequent that the plutonium alternative for making a bomb was excluded unless one could invent and develop a totally different assembly method.
James B. Conant. For the first time, it was discovered that the plutonium, as manufactured, contained an isotope with undesirable nuclear properties. As a consequence, neutrons were being constantly emitted from the material. It could not be certain that two portions of the fissionable material could be brought together without a chain reaction starting before the total was well above the critical mass. In all the arguments in favor of the plutonium route to an explosive, it had been assumed that the design of a bomb could be made irrespective of whether U-235 or plutonium made in a pile was the fissionable material. The assumption was now shown to be wrong.
Emilio Segre. The predicament was grave indeed. It meant that about half of the total work of the project might be useless for war purposes.
John H. Manley. This terrible shock, and an inescapable one, was that the gun assembly method could not be used for plutonium.
Colonel Kenneth D. Nichols. There was no question that the gun method could not be used for plutonium. Evidence was overwhelming.
John H. Manley. The choice was to junk the whole discovery of the chain reaction that produced plutonium, and all of the investment in time and effort of the Hanford plant, unless somebody could come up with a way of assembling the plutonium material into a weapon that would explode. It was again a Los Alamos challenge to do just that. It was the only possible way out at that stage of the game.
Colonel Kenneth D. Nichols. Development of implosion on a crash basis was the only possibility worth considering. My concern was Hanford. What to do about it? We did not know how long it would take to develop an implosion weapon. I thought that we should proceed at Hanford until scientists at Los Alamos determined it was absolutely impossible to develop an implosion bomb in time to be useful in this war. Not to continue building Hanford ran the obvious risk of determining that an implosion bomb was feasible, but then not having plutonium to fuel it. On the other hand, continuing to build would make our loss that much greater if implosion proved impossible. Groves again demonstrated guts by approving continued construction at the Hanford Engineer Works at the same urgent pace.
James B. Conant. An alternative weapon had to be found at once. Fortunately, a design was already at hand, but far from complete. It had been suggested some months earlier by a member of the Los Alamos staff, S.H. Nettermeyer. It was known as the implosion weapon. The principle was simple. A mass of fissionable material not quite critical would become critical if powerfully compressed. The compression was to be brought about by means of specially designed conventional explosives. To reduce this idea to practice, a whole new branch of the science of explosives had to be developed.
Emilio Segre. Fortunately, the implosion method invented and suggested by Seth Nettermeyer avoided the pre-detonation problems connected with the slowness of the gun assembly of the bomb.
Robert Bacher. Work on implosion that Nettermeyer had started had gone ahead slowly, but it was far from indicating that it was a usable method.
Luis Alvarez. Implosion involved compressing a subcritical mass of fissionable material to higher density with shock waves from a surrounding high-explosive shell, squeezing it to supercriticality. The immediate and obvious advantage of implosion is that the material assembles so quickly under the pressure of the high-speed shock wave that it doesn't have time to pre-detonate.
Edward Teller. Seth's effort received limited attention until Johnny von Neumann showed up in Los Alamos. Johnny von Neumann was so valuable, not only as a mathematician, but in virtually every field, that he was welcome to work with us even for very short periods. He was allowed to come and go freely. Johnny gave a talk in which he proposed a method of assembly that involved shaped charges. He then came home to see Michi, meet Paul, and have dinner. Afterwards, as we sat in the living room, I told him about Seth Nethermeyer's approach. Johnny immediately got interested in a quantitative manner. Assuming, as was natural, that the fissionable material was incompressible, Johnny could easily calculate the spherical flow of material toward the center.
Nicholas Metropolis, physicist, Los Alamos lab. Von Neumann was very quick in seeing all of the implications of a really good idea. He could just run through like no one else could the consequences that might ensue from any new idea.
Edward Teller. In the midst of this discussion, our furnace began a booming serenade so impressive that Johnny stopped talking and looked about with some alarm. When I told him that it was only the steam in the system, he responded, "I would never live it down if I were killed by a mere subcritical explosion at this particular project." After a few more minutes' work, Johnny found that, under Seth's proposal, pressures of hundreds of millions of atmospheres would develop. At that point, I was reminded of a fact I had learned at the George Washington University Theoretical Physics Conference on Geophysics. Iron, in the core of the Earth, under an estimated pressure of 5 million atmospheres, is compressed by about 30%. I pointed out that at the high pressures Johnny was talking about, the fissionable materials would be compressed. In that case, the critical mass would become much smaller. Needing less fissionable material for an explosion, particularly at the time when such materials were in short supply, seemed to us a splendid idea. At the same time, we could achieve a speed of assembly great enough that premature neutrons would not cause pre-detonation in plutonium, at least if the percentage of plutonium-240 was not too high.
Robert Christie. Von Neumann had an idea that if you put a lot of explosive around a little shell of material and hit it hard and drive it together symmetrically, not only will it assemble into a sphere, but it will compress. You'll compress the metal into something denser than ordinary uranium, and it was known, of course, by everyone in the business, that if you had uranium at twice normal density, the critical mass would be a quarter as great, or something like that. So this meant that, with a smaller amount of material, you might be able to get a big explosion by using this concept of compressing the metal.
Edward Teller. The next morning, Johnny and I presented our findings to Oppenheimer. He immediately grasped their implications. Within a week, magnificent administrator that he was, he had turned the direction of the research around. From then on, our main efforts were no longer devoted to a gun-assembled weapon, but rather to the implosion assembly.
Robert Christie. It was an idea that everyone was taken with.
Emilio Segre. As a consequence of this discovery, the Los Alamos project took a sharp turn.
Robert Bacher. The laboratory was completely reorganized early in July of 1944. The Experimental Physics Division, of which I was the head, was split up, and so was the Weapons Division, under Captain William Deke Parsons. 2 new divisions were formed to replace the Experimental Physics Division. We had some work on explosives. The other division that was set up was called G Division. G stood for Gadget. Gadget was what we called the implosion bomb.
Charles L. Critchfield, mathematical physicist, Los Alamos lab. George Kiszczakowski came here from Houston to head up the explosive work. He was the nation's most qualified person to direct the scientific approach to high-precision casting and machining of explosives, which was what was required. Ordnance Director Captain William S. Deke Parsons got mostly interested in the delivery problem for the gun device, the one that was used on Hiroshima. The implosion work really fell into Kiszczakowski's hands, and I was transferred from Deke's division into Bacher's. Robert Bacher had been head of the Physics and Research Division, and Robert chose him to head up what they called the Gadget, or G, Division.
Edward Teller. Johnny began what proved to be his third extremely important contribution to the work on the atomic bomb during that same visit. he began persuading us to use computers, pointing out the usefulness that computers would have in our calculations. Johnny von Neumann brought the first computers to Los Alamos. The equipment, provided by International Business Machines, now known as IBM, was advanced only in the sense that it provided electrical connections to drive mechanical motions.
Robert Christie. IBM tabulating machines. These great big machines about 4 feet high and 6 feet long, where you feed a deck of cards into one end, and it will process the numbers punched into them. We could get it to do multiplication, actually, and then it spews out a deck of cards at the other end with this information on it. The advantage of this machine was that, although it's doing only one operation, multiply A by B and write down the answer, it does that for one item after another. So you could do that operation on a whole sequence of things, and then you'd take the deck of cards over to another machine, and it would go through and do another operation. It was the strangest sort of computation ever devised.
Edward Teller. But even those machines were a great help. They were promptly put to work for the numerical integration of the hydrodynamics of implosion.
Robert Christie. Feynman helped to organize the operation to make things go. They devised a system with a bunch of machines and people carrying decks of cards from one machine to the other, and everything humming and clacking away. That was the computation laboratory. A most amazing thing.
Edward Teller. Our next problem was how to produce a sufficiently spherical implosion. Johnny knew enough about explosives to propose the use of explosive lenses. Just as a beam of light changes its direction when it passes through water and can be focused by passing it through a glass lens, the direction of a shock wave produced by an explosive can be focused and redirected by passing it through different explosive materials. Explosive lenses consist of various pieces of explosives that are fitted together so that the detonation wave moves at different speeds as it passes through different portions in the explosive. Such a composite of explosives can thoroughly reshape the shock wave and, at least in theory, can produce the desired shock wave along the surface of convergent spheres.
George B. Kistchakowski. I always lectured von Neumann, if I may use that outrageous word with respect for him, on our attitude toward high explosives, that they were completely controllable, exact mechanisms. Otherwise, it's just a blind, destructive force. It was because of that von Neumann began telling Oppenheimer that implosion was not a wild shot, but was something conceivable.
Luis Alvarez. George was certainly the most competent high explosives expert in the United States. He had been director of the NDRC Explosives Laboratory at Brewston, Pennsylvania, and was unhappy at first to be sent into the boondocks to work on a program he thought could not help win the war.
George B. Kistchakowski. I didn't think the bomb would be ready in time, and I was interested in helping to win the war.
Luis Alvarez. He soon changed his mind. He was a tall, vigorous Ukrainian, and the contributions he made were vital to the bomb program's success.
Robert Christie. Implosion is a very complicated hydrodynamic calculation in which you ask what happens to all this material 1/10 of a microsecond by 1/10 of a microsecond. As the pressures build up and it gets closer and closer together, you have to follow that by calculations of what's going on throughout all the material. You have to follow every little bit of a layer.
George B. Kistchakowski. When you design the charge in a clever way, you end up with a spherical wave traveling towards the center of the charge and centered on the plutonium sphere in the middle.
Luis Alvarez. To make implosion work, we thus required 2 inventions. The first was the explosive lens, which behaves much like an ordinary glass lens. It takes a spherical wave that is expanding from a point and turns it into a spherical wave that is converging on a point. The second invention was simultaneous detonation. I led the team that made the second invention.
George B. Kistchakowski. The electric detonators then in existence had horribly poor timing, so that to explode them simultaneously looked to us at least absolutely impossible. Mind you, since detonation waves travel almost a centimeter per microsecond, the timing we were concerned about were fractions of a millionth of a second. Luis Alvarez in the summer of 1944 started experimenting with electric detonators, and, I must say, completely to my surprise, found a way of setting them off in such a way that the simultaneity was very acceptable.
Luis Alvarez. One day, I suggested to George Kiszczakowski the possibility of starting the detonation wave in a detonator by discharging a high-voltage capacitor, a device for storing electricity, through the detonator's bridge wire. George was skeptical, but agreed I should give it a try. Larry Johnston, my former student, had just arrived at Los Alamos from MIT. He prepared to try out my idea.
Lawrence H. Johnston. Alvarez asked Kiszczakowski why they did not use 32 electric detonators fired simultaneously to do the job. Kiszczakowski said that electric detonators had an intrinsic delay of several milliseconds in firing, which would spoil the simultaneity. Timing of all the lenses was required simultaneous to within less than 1 microsecond. Alvarez then decided there was no basic physical law which would require this amount of delay if you could put enough electrical energy fast enough into the right design of an electric detonator. So he gave me the job of designing a detonator and electric firing system that would have no substantial delays in initiating a high explosive. At Los Alamos, you could get things and services fast if you were working on a high-priority project. Within 2 days, I had a portable building set up on lonely South Mesa, 2 miles from the main tech area. Also, a big workbench, some stools, a gasoline-driven generator, a few electric cords, an assortment of mechanical and electronic tools, an electronic power supply giving up to 5,000 volts DC, an assortment of high-voltage capacitors, a large roll of primacord, a gasoline blowtorch, some chemical glassware, some matches, a box full of DuPont electric blasting caps of the usual kind, and an olive drab-colored automobile to get me around.
Luis Alvarez. The detonators in Larry's first test fired simultaneously within less than 1 microsecond. In a few days, he was firing independent electrical detonators with a timing spread of less than 1/10 of a microsecond, at which point he changed to more precise time measurements. In a few months, my group, now abruptly enlarged, brought the timing spread for hundreds of detonators fired simultaneously to within a few billionths of a second. Now, we had to develop our new detonators and devise methods for studying the time spread in hundredths of a microsecond between groups of 32 and even 64 detonators fired simultaneously.
George B. Kiszczakowski. Up to 25 tons of HE was trucked up the hill monthly during the most active period. The manufacture of the HE charges was really hard, tough, and dirty work. A lot of people thought it was also very dangerous. And because of that, I went to S-Site very frequently and tried out new operations, simply to show confidence in what we were preaching.
Luis Alvarez. Our South Mesa operation was different from any I had ever been associated with before. Some of our Army men were technically skilled. Others served us as laborers. A large force of Spanish-American women imported from nearby towns loaded detonators behind armored shields. We used insensitive explosives and lost not so much as a finger. We experimented to decrease the timing spread, sorted different particle sizes, varied packing pressure, changed all the engineering variables we could think of. It was cookbook work more than scientific, but we knew it was important and pushed it hard.
George B. Kiszczakowski. We ended with a spherical charge of high explosives, almost 5 feet in diameter with a metallic pit in the middle. In the center of the pit was the plutonium fissionable material. Our job was to induce the pit and the plutonium to be compressed in an orderly fashion under the extreme pressure of a detonation wave, many millions of pounds per square inch, into something very much smaller than it normally was, whereupon it would become supercritical. A nuclear reaction would then spread, and a big bang follow.
John H. Manley. In spite of many difficulties, the scheduling of the whole project was never held up by a weapons problem. It was always the production of materials for weapons that determined the timescale.
Brigadier General Leslie Groves. In September, it became clear that we would use both a gun assembly bomb, the little boy, and an implosion bomb, the fat man. We decided to freeze the external shapes of the three models then existent, one little boy and two fat men, to permit completion of the necessary modifications to the B-29 that would deliver the bomb.
Colonel Kenneth D. Nichols. Our best guess at that time was that sufficient U-235 for one gun-type weapon would be available about August 1st, 1945. Groves was determined to drive ahead with the implosion weapon with the objective to beat the U-235 bomb. He still hoped we might have a plutonium weapon ready between March and July 1945. Both Compton and Oppenheimer thought this was possible, but Conant was not so optimistic. At the same time, we continued to plan on the gun-type weapon instead of implosion for U-235 in spite of the larger quantities of U-235 needed because Oppenheimer felt more confident that the gun type would work. We wanted to be certain that we had at least one type of atomic bomb.
Hanford. Life in a construction camp. Long before the X-10 reactor in Oak Ridge had come online, DuPont and the Met Lab were at work designing a comparably giant version of the graphite reactor to refine plutonium at scale. Groves and the Manhattan Project seized some 400,000 acres along the Columbia River, displacing about 1,500 locals as well as native tribes. Major excavation work for the first Hanford reactors began in the fall of 1943. And as progress continued, the Hanford construction camp grew into the largest ever in the U.S., aiding a total workforce of about 45,000 personnel, and making it by war's end the fourth largest city in Washington state. Like many aspects of the Manhattan Project, its construction was a lesson in sheer audacity, as it swallowed enormous quantities of industrial resources. Just preparing the vast site, before even counting the first shovelful of dirt, piece of lumber, or drop of concrete, required building more than 300 miles of road, 700 miles of railroads, and erecting 11,000 utility poles to provide electricity.
Brigadier General Leslie Groves. Hanford was then a very small town.
Annette Hereford, resident, Hanford. We owned 30 acres of Jonathan and Winesap apple orchards. We had planned to switch to Red Delicious. Our place was located 3.5 miles from Hanford and 4 miles from White Bluffs. We were called the in-between people. When the government arrived, the combined population of Vernita, Cold Creek, Hanford, and White Bluffs was between 1,200 and 1,500 people.
Ray Derenlow, resident, Richland. We got notice from the government on March 6th, a little before noon, in the mail. I was plowing a field, and I came in for lunch, and my parents were telling me about it. After I ate, I went back out and cranked up that tractor. I bet I hadn't been plowing an hour and a half, and somebody called up and told them to get that tractor out of the field.
Annette Hereford. In March 1943, when I was about 22, we received a letter from the government saying that we would have to move in 30 days. It was a terrible shock. I can't describe it. It was unbelievable. The only thing that made it credible to us was because of the war. Our town had been chosen for the war effort. We were so patriotic. Although we could go along with that idea, it was still a terrible blow. Even to think about it now, I can't even describe it. In spite of our patriotism, I remember one man stood there with a shotgun and said they would have to move him.
J. Perry, town appraiser. If a bomb had been dropped in the community, it would not have caused any more uproar. I liken it to what happens when one kicks a hive of bees. Gradually, it became known that the government planned to acquire 400,000 to 500,000 acres in northern Benton County and across the Columbia River in Franklin County, on which some kind of plant connected with the war effort would be built.
Lloyd Wheel, attorney, Yakima. It came like a bombshell. They announced they were taking the whole valley. For what? We didn't know.
C. Mark Miller, appraiser, Army Corps of Engineers. The negotiators for the Corps of Engineers had great difficulty in negotiating for the acquisition of any of the land because of the very low appraisals. Much of it went into litigation.
Lloyd Wheel. Charles Powell, later a federal judge from Kennewick, and I got together and we took most of these land cases to court, and the verdicts were so much over the appraisals. We had them reappraised. It was so ridiculous that the government finally confessed that they were wrong. We settled nearly all of the cases out of court. If they'd gone ahead with that original deal and everybody had signed up, it would have been a tremendous injustice.
Kathleen Hitchcock, daughter of White Bluff's newspaper publisher. My mother took the evacuation very hard. They had always expected to live there the rest of their lives. And it was pretty hard when the Army engineers came in and told them to, get out. It was a pretty hard thing. Some of them ended up at Medical Lake, a state mental hospital. Couldn't quite face it. My mother never really adjusted to it.
Brigadier General Leslie Groves. Long before all this confusion in the courtroom began, the first DuPont employee, an engineer named Les Grogan, arrived in Hanford on February 28, 1943.
Bob Gilbert. Prisoners from McNeil Island were brought in to harvest the abundant crops remaining after the farmers were evicted. Living quarters were established for them at the north end of the Benton City Road on the west bank of the Yakima River. It was a large camp upstream from the Horn Rapids Dam where Indians maintain a fishing platform. It is a beautiful spot on the hillside and occupied several acres, all immaculately maintained by the inmates. This site is still referred to as Columbia Camp. Father Sweeney ministered to the inmates at this camp.
Frank Buck, age 16, member of Wanapum tribe. We used to live in the tools, reed huts, until spring. Then we take them apart, put them away, and we move. First we move after the root feasts, clear up to Soap Lake and Waterville, then down to Ellensburg. Horn Rapids for fishing, Notches Pass for berries and more fishing for several weeks. After this, we come back to Priest Rapids, where our home was for winter. We just went over this year after year. We just circle the same way every time. When the Army came into Hanford, they said we can't go in there.
W.K. McCready, Project Liaison. The first shovel was stuck in the ground at Hanford in the early summer of 1943. All of the buildings, all of the facilities, all of the roads, railroads, all of the interim structures necessary to carry on construction were built. The Hanford plant was finished, all of the temporary stuff was cleared out and construction gone by the 6th of February, 1945. 3 reactors were built, 3 major separations plants, and all of the affiliated stuff. All were built in less than 2 years.
Claude Rawlins, farmer, White Bluffs. We didn't hate the government over it. We hated DuPont. I remember never buying a DuPont product after that. If it said DuPont, we didn't buy it. There was the Japanese and the Germans and DuPont. Those were the enemies.
Brigadier General Leslie Groves. At the time the design of Hanford was begun, plutonium had been separated from uranium only in infinitesimal quantities and by laboratory methods. The most feasible process was largely a matter of opinion, and the equipment needed was even more conjectural.
Frank Mackey, Construction Manager, DuPont Corporation. Hanford was quite the largest plant DuPont ever built up to then. And other than dams and things of that sort in faraway places, I guess it was the largest thing anybody had ever built.
Bill Compton, DuPont Corporation. Soon construction of homes began, including A homes, 2-story duplexes, B homes, 1-story duplexes, H houses, 3-bedroom single units, E houses, 4-bedroom single units, and J houses, 2-story 4-bedroom single units. All were the same basic construction, but they were painted different colors. These homes were primarily for the operating personnel. A few were allocated to key construction people. There was a housing list, and the day you came to the Hanford Works, your name was entered on the list. When your name came up, you were called and assigned a house based on the size of your family and your job position.
Leon Overstreet, steam fitter, American Can Company.
I was the 9th fitter lured on the DuPont construction job, and my brother Paul was the 10th. We came in together. I was working at the Sunflower Ordnance Works in Kansas near Kansas City. I was a steam fitter. On a day in May 1943, I heard two laborers talking. They said, "Boy, there's a big job out at Walla Walla, Washington." I called after work that day to the union business manager at Walla Walla, Washington, and he said to come on out and bring all of them who are willing to work. He said he heard it was the largest construction job in the world. I got my brother and the welder I was working with interested, and we got our coupons for gasoline and tires and came on out.
Harry Petcher, head of box lunch department. My wife and I got married in May 1943, and I was managing a nightclub in Chicago at that time, and during the day I was working for the Army Signal Corps on Pershing Road in Chicago as a nomenclature clerk. My wife called me at work one day and said, "Honey, I just took a job for both of us at a place called Hanford, Washington." I said, "You gotta be kidding. What are we going to do there?" She told me I would be a waiter and she would be a waitress. "What's it going to pay?" She told me 55 cents an hour. I said, "You gotta be kidding." They promised a 12-hour day, 7 days a week, time and a half after 8 hours. That was 85 cents an hour, room and board. Big wages.
William J. Dowis. After a night at the transient quarters, I joined a group of new construction workers waiting to be taken to the construction site. Our vehicle was a cattle carrier or cattle car, a long covered flatbed. The wood floor bore the marks of cattle hooves and had a trace of straw. 2 long benches were placed along the sides. This carrier had been pressed into service in lieu of a bus. The car filled up with about 40 people, all men except for 2 young women. As we started moving, all one could see through the cracks in the side panels was frosty sagebrush on the desert.
Leon Overstreet. This fellow we rode out there with, a carpenter or somebody, he said it was the largest construction job in the world. When we came over the hill and looked down on this Hanford site, all we saw were 8 or 10 frame buildings under construction. It didn't look very big to us. That was the 7th day of May, 1943.
Margaret Hoffarth, waitress, Hanford Mess Hall. People, including me, came out here thinking Washington was the evergreen state and got dumped in a desert.
Louise Cease, project spouse. When we first came here, it was wild. There was nothing here. The sand was knee-deep. We picked out our first house, a 1-bedroom prefab.
Jesse Brinkerhoff, fireman, DuPont Corporation. There was no electricity out there, no inside facilities, an outside toilet. Our water was brought to us each day in a barrel with ice in it. We lighted with coal oil lamps. My wife washed clothes on the washboard. We used wood and coal for fuel in a stove.
Jerry Saucier, operator. I worked as many hours as I wanted to work, sometimes 52 hours a week or more, time and a half after 40 hours. We always had lots of problems, like leaks in the steam lines. The living conditions were good, for a barracks, the same as if you were in the service, like any army camp. They were built to standards, rough but ample.
Betsy Stewart, secretary. We went down to dinner the first night at the transient quarters, and the salad dressing was so wonderful. We pigged out on the salad, and we had diarrhea for days. They were making the salad dressing with pure mineral oil. You couldn't get regular salad oil. Everybody got a good case of diarrhea when they came to Richland.
Harry Petcher. The way the food was prepared was all family style. The waitresses or waiters would run with these big carts up to the front where the cooks were dishing this stuff into family pans, like fried chicken. They would heap these big pans with fried chicken and run down the aisle and scoot it on these tables where all these guys were sitting, banging their hands. Francis J. Frank McHale, safety engineer and fire marshal, Army Corps of Engineers. For $13.25 per week, each worker was provided a room in the barracks with 3 unlimited meals per day and a lunch packed for carryout. Because of the shift work, the cafeterias were kept open around the clock. You could eat all day and all night. Harry Petcher. We were making sandwiches for box lunches, putting them in a paper bag. The first day I made something like 500. The box lunch was about 1,500 calories. We had 3 sandwiches with 3 ounces of food in each sandwich: cheese, beef, or ham or chicken. There was fresh fruit. Every once in a while we had salad. We used to give them a cold baked potato. A potato is a good vitamin source. Another thing, we dropped in 2 salt tablets in the box lunch. Toward the end, we started putting in candy bars, chewing gum, and cigarettes, a sample pack of 4. Our lunch cost was about 38 cents. We charged 55 cents. Francis J. Frank McHale. Initially, church services were conducted in a big old worn-out circus tent we purchased from the Ringling Brothers. If you poked your finger on the canvas when it rained, it leaked. Fortunately, it did not rain much. It kept the sun off, and it kept people happy.
Monsignor William J. Sweeney, Project Priest. The circus tent was big. A regular 3-ring circus tent. It was so big you couldn't see the people sitting in the back. It was a movie theater during the week.
Francis J. Frank McHale. Each week, 50,000 people were paid. Each worker was given a payroll number. There were 50 lines. The first line was labeled for payroll number 1 through 1,000. The second was for payroll numbers 1001 to 2000, and so forth. The accounting and payroll people worked around the clock. At first, workers were paid with checks. Merlin True, a payroll truck driver and teller, noticed that no checks had been cashed by one of the workers. Merlin asked the worker why he did not cash his checks. The worker responded that he did not know what to do with his checks. After they found other workers were also having difficulty cashing checks, they paid cash. That worked out much better.
Robert E. Bubenzer, Security Supervisor, DuPont Corporation. We had to bring cash in every payday for the bank. We had an armored car, and we had 2 cars in front of it and 2 cars behind it and an airplane overhead. We would bring it from the railroad station at Pasco. We were transporting between $1 and $2 million in mail sacks. This was on a Friday, and every Friday we would have 12 armed guards at the bank. Colonel Franklin T. Mathias. We made up our minds when we first started that we would put people in barracks regardless of what they looked like. It wasn't more than a few weeks after we started getting people in our camp that I had a visit from a whole bunch of black guys led by a black minister who said they would rather have their own barracks. They hadn't had any real trouble, but they figured they would.
Luzelle Johnson, cement finisher. Everybody played baseball together. The teams were black and white.
Roger W. Fulling, Division Superintendent, DuPont Corporation. Baseball was a great source of relaxation, and at Hanford each craft, like carpenters, fitters, and so forth, had its own team, and there was an organized league between the crafts. One craft in particular was not doing too well. The head of the craft, the superintendent, said he wanted some changes in the league standings. He instructed recruiters in that craft to do some screening in the selection of candidates for hiring. This craft superintendent, unnamed but known to me, told his recruiters to concentrate on the Pacific Coast League baseball players. As a result, the craft went from the bottom to the top of the league. DuPont corrected this method of recruiting labor.
Annette Hereford. 3 shifts were employed around the clock to construct a big auditorium. Robley Johnson said it was completed after only 10 days. A Quonset hut was set up for a youth center. I was the director in the youth center. I taught tumbling, dancing, and also swimming in a man-made lake. The new residents also enjoyed ping pong, pool, and a well-stocked library. Nothing was too good for the young people that were needed to keep the families happy.
Francis J. Frank McHale. We built a recreation hall at Hanford. We brought in big-name bands. It had the longest bar in the world, but because of state regulations, no one could stand at the bar. Everyone had to sit at tables. A pitcher of beer with as many glasses as you needed was $1. The dance floor in the recreation hall was the biggest in the Northwest at that time. Occasionally, shows and acts were brought in to perform in the recreation hall.
Jerry Saucier. The beer hall was pretty good-sized. A long bar, but the longest I had seen. They had a special crew to take care of the beer and the ice. It was a popular place, all during the day, people working different hours. It got pretty rough some nights. One night, I was in there, and all of a sudden all hell broke loose. They had a riot squad with trucks, and they backed it up to the door, and a guy gets up there with a bullhorn and tells them to break it up. Finally, the cops started using clubs and throwing guys in the wagon. Things got back to normal again. It was like an old western town where Marshal Dillon came in and had to straighten things out.
Robert E. Bubenzer. At the peak, in July 1944, we had 1,395 patrolmen. We had our own kangaroo court and our own jail. Every morning, we would screen them, and unless it was awfully serious, a pat on the back and "don't do it anymore" was our theory. In some cases, we would terminate lawbreakers, but in most cases, it was important that we got them back to work. We needed workers.
Harry Petcher. You would get up in the morning and walk through your barracks, and there's about 20 more barracks that weren't there last night.
Vera Jo McCready, project spouse. People got confused. What with the new streets and the way the houses looked a lot alike. Several times I would be in the kitchen and a man would come in the back door, and usually I would know him and knew he just got in the wrong house.
Sam Campbell, patrol captain. One of our busiest periods was keeping people from being run over there at shift change, primarily 4 to 6 in the afternoon.
Margaret Hoffarth. Everything out there was sheer hurrying.
While much of the work at the Hanford Engineer Works was unprecedented and carefully guarded, the plants also faced one threat unique among all U.S. industry during the war: direct attack by Japanese bombs. From November 1944 to the spring of 1945, the Japanese Army lofted thousands of Fugo balloon bombs into the Pacific jet stream, in hopes the bombs would traverse the ocean and land and explode in North America, sparking forest fires and instilling panic in the homeland.
Leona H. Woods. Large flocks of geese flew across the Columbia to the dry-farmed grain fields and irrigated mint fields on the east side for breakfast and dinner, and returned at night, sleeping somewhere on the reservation. Night after night, the Army Air Force Detachment mistook the radar image of the geese flocks for attacking enemy planes, flew their planes out, and searched fruitlessly. After a few such abortive alerts, we all became sky-conscious, especially because Japanese fire-carrying balloons began to drift overhead in significant numbers.
Walter O. Simon, Operations Manager, DuPont Corporation. Japanese balloon bombs were a real worry. Everybody at the plant was always looking up because of the statistical chance of one falling. I remember seeing 40 at one time going over. The Navy planes at Pasco chased them regularly, but they had poor luck. Matthias and I went over to prod them about getting better protection. They never managed to shoot one down, although a number came down on the project but away from the buildings. The bombs never went off, but the balloons blew around, and the military were a great sight, trying to round these up without being blown up themselves. The only balloon that caused any damage to Hanford was the one that landed on the power line from Grand Coulee Dam.
Leona H. Woods. One of them tangled on a power pole, shorted the transformer, and shut off power for the better part of a day.
Walter O. Simon. It knocked out the reactors very briefly. The only American war plant shut down by enemy action during the whole course of the war. We mentioned that to Groves, and he said, "I suppose all you fellows will apply for the Purple Heart."
Leona H. Woods. At noon one day, we stood outside staring at the sky while we ate our sandwiches. It wasn't long before someone spotted Jupiter in the daytime sky, a pale sphere about the apparent size of a high-flying balloon, and we called out the planes to shoot it down. The plane went up and up until it reached its ceiling, and the pilot returned to reprimand us for frivolity.
Thomas L. Hankins, Professor, University of Washington. The real achievement of the Manhattan Project was the organization of it. After the war, there was this problem of espionage, and the popular press seemed to indicate there was a secret to the bomb, and these scientists had discovered a profound equation somewhere. That wasn't the case. What was needed was an enormous industrial effort at Oak Ridge, at Hanford, and at Los Alamos. It was a very large industrial effort, a major effort that required a lot of very skilled engineering and designing.
Roger W. Fulling. The missing link in the Manhattan Project story is that the atomic bomb was a product of American industry. This story has not been told. I want people to understand, before I go, the importance of industry to this project.
Hanford. Making plutonium en masse. The Hanford Engineer Works has been traditionally overlooked in Manhattan Project histories, failing to capture the public imagination like Los Alamos with its larger-than-life personalities. But there is an argument made by Hanford historian Steve Olson and others that the Washington State site is actually the most important location of the nuclear age. Its first full-size nuclear reactor is the parent of all reactors since, and plutonium, first created en masse in Hanford's pools, remains the basis for effectively every nuclear weapon since. The main production facilities at Hanford consisted of a two-step process. The reactors, located in what was known as the 100 area that produced the plutonium, and then about 10 miles away, 3 giant chemical separation facilities located in the 200 area. These enormous windowless buildings, about 800 feet long, 65 feet wide, and 80 feet tall, were nicknamed the Queen Marys, after their resemblance to a giant ocean liner sitting in the Washington desert. There, the irradiated slugs from the reactor were chemically treated and dissolved to remove the uranium and retrieve the 1 part in a million that was plutonium. A third part of the site, known as the 300 area, housed the metal fabrication and testing facilities, where uranium was heated and extruded into tens of thousands of slugs for use in the reactors. The first reactor started operations September 26, 1944. It was a vastly more powerful one than the pilot plant that had been built in Oak Ridge. The X-10 reactor achieved about 4 megawatts, but the 3 reactors in Hanford, known as B, F, and D, were designed for 250 megawatts. D reactor was operational by December, and F followed in February, all beginning to churn out plutonium for the bombs. The Hanford plant area, which operated well into the 1980s, eventually left an environmental disaster for future generations. Today it's estimated that the decades-long cleanup effort might cost $500 billion. The land seized by Groves in World War II may forever be too polluted to hand back to the public.
Leon Overstreet. We went out to 100B, the first reactor, in May 1944. We were among the first steam fitters on the job. I was amazed. I couldn't figure it out. I looked at that thing we were working on. It had all kinds of tubes and pipes running through it, and graphite blocks that the other crafts were laying around the pipes. Nobody could understand what kind of a contraption it was. They had never seen anything like it. You can usually understand what you're doing, but boy, that one floored us.
Joe Holt, construction worker, DuPont Corporation. We were the first carpenter crew out there at the first reactor, and everybody worked with the engineers driving stakes. And then they started bringing in equipment. Heavy equipment, cranes, there was a trainload a day. Some of those cranes were so big they sat right on the track. All kinds of heavy equipment. Everything they asked for, they got.
W.K. Mac McCready. While the plant was being built, there were only 2 people in the construction organization on site that knew the purpose of this construction. We must never say anything that would give any inkling to any of the construction people of what the plant was for.
Walter S. Carpenter. This operation, it was so complicated and so obscure.
Brigadier General Leslie Groves. Security necessitated special handling of the multitude of drawings, reports, and correspondence that passed between the various offices. To speed up construction, working drawings were broken down to disclose as little information on the overall project as possible. By this means, it was possible to treat many of them as unclassified. Such measures were particularly necessary when drawings were sent to subcontractors or used by construction workers at the site.
Blake Miller. I was commissioned to do drafting. I was assigned to an inner room constructed from concrete and with no windows. A patrol officer was stationed at the door. The room had only a drafting table. One day, my supervisor brought a gentleman in with an attaché case attached with a chain to the man's wrist. With 2 keys, he opened the case, laid the blueprints on the table, and told me to go to work. Many copies were needed. The maps had symbols, large grooves from which they made the graphite for the piles. Security was so tight that I would walk out of the inner office accompanied by a patrolman. Patrol followed me all the way to the John and all the way back.
DeWitt Bill Bailey, Special Material Handler, B-Reactor, DuPont Corporation. No way did I have a notion of what we were doing during the war. I don't think anybody else did. They only had one guy who could look at the blueprints. A general foreman or superintendent would go in and get a pencil sketch off of the main blueprint.
Joe Holt. They started digging this hole for the reactor building, and it was like going down to China. They put in 3 different concrete mixers to pump the concrete. I don't know how deep that hole was, just for the base.
Brigadier General Leslie Groves. The complications were many. Many pieces of equipment weighing as much as 250,000 pounds each had to be assembled with tolerances more suitable for high-grade watchmaking.
Joe Holt. They got the first reactor building up and then started laying the graphite. I helped on that. It was wonderful, very precise work. The blocks were different lengths, but all had to be fitted to tolerances in the thousands. We had to wear protective clothing, shoe coverings, so there wouldn't be any contamination of the graphite. There were guys running a vacuum cleaner all the time to keep anything loose off the graphite.
Roger W. Fulling. Initially, we had a hell of a time getting the graphite block program through Union Carbide. I had to go up to the Union Carbide New York offices and present the program to their senior executives as to how important this was and why we had to have it in large quantity and on schedule.
Brigadier General Leslie Groves. It was through the assistance and the strength of the industrial companies of America that DuPont was able to solve the hundreds of difficult design and material problems that had to be mastered. It is hard now to realize how difficult some of our developmental problems were.
Roger W. Fulling. The graphite blocks were laminated with a very special composition of fiberboard. The machining was very, very interesting and requiring very high precision, and the only people who could do this was Vermont Marble in Rutland.
Joseph O. Hirschfelder. In order to make the plutonium piles at Hanford, so much carbon black was required that for a period there was a shortage of rubber tires in the United States.
Raymond P. Genero, Design Project Manager, DuPont Corporation. I had engineers of every calling on my team: mechanical, electrical, civil, metallurgical, chemical. It was that combination of people and talent that you needed.
Frank Mackey. We had our design division in Wilmington, with the nucleus of a design group at Hanford. If we got into a problem one night, we tried to have it solved by our construction and design groups by the next morning. We had quite a few design men at Hanford, and they were only a telephone away from the big group in Wilmington.
C.N. Gross, construction consultant, General Electric. The teletype between Hanford and Wilmington was going 24 hours a day on design changes.
Francis J. Frank McHale. I had been cautioned not to recruit people from Oklahoma or Arkansas because they were a bunch of hillbillies who would not work and would not take orders. The Okies and the Arkies are the people who built this project. They did the hard manual labor and attended our schools where they learned to be plumbers, steam fitters, and all the other trades.
Joe Holt. It didn't matter what. If a man had only one arm or one leg, if he wanted to come to Hanford, he had a job. Most of the men were older than me. A lot of them were in their 60s. They needed help so bad, they were determined to build a plant at all costs.
Frank Mackey. As far as materials were concerned, Hanford had the highest priority for government work, and we could almost pick and choose what we wanted and when we wanted it.
DeWitt Bill Bailey. There was no reason to run out of anything, because they could tap into anything in the United States.
Brigadier General Leslie Groves. Before the Hanford works were finished, DuPont employed over 10,000 subcontractors.
DeWitt Bill Bailey. We were running 3 shifts. They had electricians, pipe fitters, millwrights, and those people were working all around the thing. Everything was being done at practically the same time. And it was so engineered that when one phase finished out, all of it was about finished and was ready to pull the switch. We would repeat the work on the other reactors.
Brigadier General Leslie Groves. When our needs grew even more pressing, we were unable to find enough pipe fitters to maintain our schedule. Investigations showed that there were simply not enough in the United States to fill the demands. The solution we adopted was to locate a considerable number of pipe fitters, all union members, who had been inducted into the Army. These men were given the opportunity to be furloughed to the inactive reserve on condition that they would accept employment at Hanford as civilians at the going rates of pay.
Joe Holt. The concrete was made right there. They had the gravel and sand. All they hauled in was the cement. They started pouring this concrete, and it got below zero, so they brought in steam locomotives. They must have had, 10 or 15. They built the railroad and run the steam locomotives in there. They took all the steam the engines could produce. They had the concrete covered with tarps, and these steam locomotives was furnishing steam underneath to keep the wet concrete from freezing before it set. Steam was flying every place.
Brigadier General Leslie Groves. Originally, 8 separation plants were considered necessary, then 6, then 4. Finally, with the benefit of the operating experience and information obtained from the Clinton Semi-Works, we decided to build only 3, of which 2 would operate and 1 would serve as a reserve. I should like to point out that these separation plants were designed when we only had submicroscopic quantities of plutonium.
Raymond P. Genero. We called the main separations building a canyon. We built 3 canyons, T, U, and B, and used 2. 2 were 810 feet 6 inches long by 102 feet and 85 feet 2 inches from bottom to top. The other one was 65 feet longer because we added a lab for handling hot materials.
Leona H. Woods. One of my bosses took me on a tour of the Queen Mary's, carrying with us blueprints of the construction and plumbing diagrams. These huge concrete canyons were positioned about 10 miles apart in the desert, taking advantage of low hills between for shielding from each other.
Raymond P. Genero. One day, some workmen were at one of the 221 buildings, our designation for the canyon buildings, and the building was just up to grade. The bottoms were about 50 feet into the ground, and one of the workmen said, "I don't understand anything about it." The other guy said, "Yeah, I think they're building it upside down."
Leona H. Woods. These were the processing units for solution of the irradiated uranium slugs in nitric acid, and for separation of plutonium and uranium from the fission products, and of uranium and plutonium from each other. The irradiated slugs were to be brought into the first vat of the canyon on railway cars, in large tanks of cooling water. We went along the empty and echoing balconies of the canyon, checking pipes and valves, going step by step through the process, as yet tested only in pilot plant stage. How does this effluent get removed? How is that precipitate carried into the next cell, and so on? We found only one mistake. It had already been discovered a day or so before by an independent checking team. It was a pipe that had been blocked off in a maze of pipes.
One of the most significant challenges for the reactor was the design and manufacturing of the uranium cans that would make up the reactor. As the building construction advanced in the 100 area, little progress had been made in the 300 area in perfecting how to clad the uranium in aluminum necessary for the reactor processes.
Major General Leslie Groves. The aluminum tubes illustrate how complicated even the most simple item could become.
Groves was promoted in the spring of 1944 to a 2-star general in recognition of his leadership of the Manhattan Project.
Arthur Holly Compton. The task of soldering and enclosing the uranium billets in aluminum cans came critically close to holding up the entire project. The final stages of this task were accomplished in a developmental laboratory set up by DuPont for the purpose in the Hanford area.
Major General Leslie Groves. 7 months of persistent effort, principally by the Aluminum Company of America, were required to perfect a metal of the proper characteristics so that a satisfactory tube could be produced in quantity.
Walter O. Simon. The summer of '44 was coming along, and the reactor was shaping up, and there would be nothing to put into it. It was a little terrifying, because if we didn't have them, it would stop the whole thing. The reactor would be ready on September 15, and we would have nothing to put into it.
Leona H. Woods. With 10 days or so to go before startup, only a few % of the required slugs were on hand and successfully processed.
Walter O. Simon. The uranium was held in an aluminum can, a slug, about 8 inches long and 1 5/8 inches in diameter. The can had to fit very tightly, with no airspace or bubbles. They couldn't leak because if water got into the uranium, it destroyed the ability to react. So the concept was that the scientific people would find out how to do this and give us instruction. They found out how to design it, but they never made a slug in the laboratory that didn't leak.
Roger W. Fulling. Extrusion is an art. You would start with a stock, and you would extrude at the right temperature. Cooling atmospheric conditions had to be just right.
Walter O. Simon. We had a production superintendent at Hanford named Earl Swenson, who was a real dyed-in-the-wool production man. He said, "They'll never make one of these in the lab, even if they work on it for 10 years. It's a statistical matter. Why don't we make 1,000 a day? We'll examine each one and test them all, and the poor ones will strip the aluminum can off and save the uranium, and the next day we'll make another 1,000.
Roger W. Fulling. The welding of the uranium containers was intricate. The welders working on the aluminum cans to contain the uranium fuel were not like you would see welding a steel plate to a steel beam or two steel beams together. These men were artists. They were the top of the craft, like the old goldsmiths.
Walter O. Simon. The first day, 1,000 failed, but there were maybe 10 better than others, and we tried to figure out why these 10 were better. The next day, maybe they had 18 that were better. They kept doing this, and lo and behold, after about 3 weeks, there was one perfect can. Purely statistical. If you made 1,000 a day for 3 weeks, you had made 20,000 until you got one good one. They made 5 good ones the next day, and 10 the next, and after a while, out of 1,000, they were making 500, and then 600 a day that were all right.
William P. Bill McHugh Sr., Project Staff, B Reactor. I think Earl Swenson canned 30,000 pieces before they finally got a successful one, without voids. Somebody said something about that, and Earl said, well, if necessary, we'll can another 30,000 until we get it right.
Roger Hultgren, chemist, tea plant. The canning process was critical. If we had not been able to protect the uranium from corrosion by the coolant, it would not have been possible to operate the B reactor. As it turned out, we successfully canned the uranium slugs in aluminum jackets, bonded and welded them, machined them to the correct dimensions, and tested them in high-temperature, high-pressure water in autoclaves as a final quality test. In early September 1944, I accompanied a shipment of fuel elements from the 321 building to the B reactor.
Walter O. Simon. The director of DuPont's plutonium effort, the TNX division, was Roger Williams, and the success of the project was due to his skill and guidance. He was a genius. The books to date on the Manhattan Project rarely mention him. He was a modest man and avoided the limelight.
Hanford. The B reactor. The chemical separation process, developed by Glenn Seaborg at UC Berkeley, took irradiated slugs from the nuclear reactor and dissolved them in chemical solutions inside the giant Queen Mary facilities. An intricate multi-step procedure that eventually allowed the plutonium to be isolated and removed. The first irradiated uranium slugs were ready for the Queen Marys just after Christmas 1944, and the first plutonium shipments to Los Alamos began February 2, 1945, almost exactly a year after the reactor assembly began. The reactors consumed enormous quantities of water from the nearby Columbia River, equivalent to the needs of a 1 million-person city. The functionally identical F and D reactor complexes followed the creation of the first B reactor and came online in November and February 1945, finally allowing Hanford to manufacture plutonium at a meaningful scale.
C.N. Gross. The design level for plutonium production per reactor was 250 grams a day when the power level was 250 megawatts. Each megawatt was supposed to produce a gram of plutonium per day.
Leona H. Woods. This was the first big reactor in the world. Here were all these big shots lining the walls to watch the startup. The operators were all coached. They had manuals. They had been through the routine XYZ times. So here comes startup. You can see the water getting hot, the readings going up on the recorders. You could hear it rushing in the tubes. You could see the control rods coming out and out and out.
Robert D. Miller. I remember the day we started B Reactor. I was on the 412 shift. When I got to work, Enrico Fermi was sitting in the office with an old mechanical, hand-cranked Marchand calculator, studying why the reactor had shut itself down several hours before being started.
Dale Babcock, chemist, DuPont Corporation. The first nuclear reactor at Hanford died almost right away.
Leona H. Woods. Something happened, and there was no more reactivity. The reactor went dead, just plain dead. People stood around and stared at each other.
Alvin M. Weinberg. The pile shut itself down after a few hours of operation. The entire plutonium project seemed to be turning into a fiasco. We, in Wigner's group, tried to figure out what was going on. Could some impurity in the water be depositing on the fuel elements and absorbing neutrons?
Leona H. Woods. During the night, after we had gone home, leaving John Wheeler and Don Hughes on watch, one of the operators pulled out the control rods and found that the pile was regaining reactivity. The operators followed the buildup of the neutron flux, and then, once again, watched it die away.
Dale Babcock. John Wheeler decided it probably was caused by a fission product. He selected 3 pairs of decay products, and he decided we should calculate how these would behave. We divided into 3 teams. I certainly was low end on the totem pole as far as knowing how to do it was concerned. It so happened I was part of the group which had the fission product that caused the problem, but we were so slow, John and Charlie Wend finished up their products, and they came over and worked over our backs. It was the Xenon 135.
Edward Teller. The explanation was quickly identified. One of the radioactive fission products, iodine, decayed into radioactive xenon. Xenon, it turned out, was a fierce neutron absorber. At low power levels, the xenon had time to decay into harmless cesium before absorbing neutrons. But at high power levels, the only way to solve the problem was to destroy the xenon by providing it with extra neutrons.
Eugene Wigner. One problem we never foresaw, that some of the chain reaction's undesirable fission product would have an absorption large enough to stop the reaction. When the first large-scale chain reaction was attempted, this soon occurred. A fission product, Xenon 135, was produced, with an enormous cross-section. It absorbed neutrons vigorously, and the chain reaction halted.
Leona H. Woods. By the time Fermi and I arrived the next morning, Wheeler and Don Hughes had largely solved the problem. What remained was several days of hard work following mathematically the observed buildup and decay of reactivity of the pile, fitting it to coupled differential equations, and evaluating the absorption cross-section. We did this with hand computation, using desktop computers, step by step, in steps corresponding to intervals of about 10 minutes.
Alvin M. Weinberg. In this instance, DuPont's conservatism, which irked Wigner so, was sound.
Edward Teller. Crawford H. Greenewalt took a remarkably positive and imaginative approach. In planning the Hanford reactors, the MetLab scientists insisted that only minimum-sized reactors were required. Making them as small as possible, they declared, would put them into production faster, thereby speeding up the collection of weapons-grade material. Greenewalt, whom we called Greenie, was concerned that the project was moving too fast. He believed the reactors were risky, even with the inclusion of the safety factors on which he had insisted. Greenie insisted that the size of the reactors be increased.
Dale Babcock. We suggested enlarging each one of the 1,500 fuel assemblies so that they would contain more uranium and expanding the number of fuel assemblies to 2004. The added fuel assemblies were what allowed us to overcome the later poisoning by xenon.
Edward Teller. Greenie, by cautiously building a bigger reactor than theorists wanted, had made it possible to increase the number of fuel rods, and thus the power.
Dale Babcock. If we had not been able to add more fuel, I'm certain we would not have been able to produce plutonium at the rate we had calculated, which was 250 grams per day per reactor.
David Hall, head of Reactor Division. The DuPont people say their foresight provided for the unexpected, as in the case of the xenon poisoning. In fairness, and I am not criticizing DuPont, I think they may not have done what they had done if they had been in a competitive position. They were running at cost, and they did not get a profit, but there was no expense to them. For example, my wife and I, both with PhDs, were hired to do really quite menial tasks, jobs that could have been done by people without training. It was overkill, and it paid off.
Leona H. Woods. It was a victory for conservative DuPont engineering practice that the empty tubes were available. Fermi calculated that if all the extra holes of the reactors were loaded with uranium slugs, the reactors would have enough reactivity for successful operation. It was so done in the next few days, with the slug canning assembly line again working around the clock. The first plutonium production reactor again started up, this time with no drama. The babysitter shifts of physicists sat around the clock.
Dale Babcock. I'm biased, but I think John Wheeler's analysis of the xenon poisoning at Hanford was in the Nobel Prize category. The problem appeared, it was solved, and we were going again.
Leona H. Woods. 3 months later, the first batch of irradiated slugs were pushed out and were trucked on the short railway to the Queen Mary, where they were dissolved in nitric acid and the metal separations carried out.
W.K. Mac McCready. To run a batch through took about 12 hours through 221T building, the big rascal with the thick concrete walls, and 224 building, a more normal building of concrete blocks. By the time you ran through 221T building, you had separated most all of the fission products, as well as the uranium from the plutonium. By the time you got to 224, it was 99% plus pure. The radiation exposure was very low, so they could run through the next stages of purification in a more normal building without all the shielding or the remote operation. Eventually, the product was a 99.99% pure solution of plutonium as a nitrate salt in solution.
Leona H. Woods. When the Queen Marys began to function, dissolving the irradiated slugs in concentrated nitric acid, great plumes of brown fumes blossomed above the concrete canyons, climbed thousands of feet into the air, and drifted sideways as they cooled, blown by winds aloft. The plumes cooled and descended on the desert, where the iodine vapor stuck to the artemisia leaves. These leaves were eaten by the rabbits, which in turn were eaten by the coyotes. The army guards of the huge reservation, with nothing else in particular to do, were asked by the medical staff to procure some coyotes at regular intervals, and so they drove around in jeeps over the desert floor, bucking across arroyos and gravel residues of ancient high water, shooting a monthly quota of coyotes. From the carcasses, the increasing radioactive content of the coyotes' thyroids was regularly monitored.
John A. Wheeler, nuclear physicist, metallurgical laboratory. An observer from afar, looking upon the scene in 1944, would have been convinced that he was looking at one alchemist's dream inside another. It was preposterous enough to think that dead uranium, put into regularly spaced crannies in tons of dead black graphite, would come alive. It was still more preposterous to imagine this life, this silent darting back and forth of invisible neutrons, as producing in the course of time not merely a few atoms of plutonium, but billions upon billions of them, the philosopher's dream of synthesizing a new element achieved in kilogram amounts.
Leona H. Woods. Less than 2 months later, the first batch of plutonium arrived at Los Alamos.
Walter O. Simon. There was extreme pressure to produce a certain specified number of grams of plutonium, which, in retrospect, must have been enough for a test bomb and the Nagasaki bomb.
Oswald H. Grager, chemist, DuPont Corporation. At the end, it was a semi-solid of jelly-like consistency and was put into a simple can, a strong spherical container of stainless steel. This was shipped to Los Alamos.
Walter O. Simon. We shipped it in a solution. It looked like brown molasses. We shipped enough by June that we were cleaned out.
Bill Compton. Big Simpson was in charge of picking up the plutonium nitrate and trucking it to Los Alamos.
Second Lieutenant O.R. Big Simpson, project courier. It was May when we started the convoys. We had 3 panel trucks with a lead car and a rear car. The cars were ordinary Ford sedans. There would be 2 people in a truck and 2 people in each car. We drove directly through. Everybody was armed. We carried shotguns and .38 caliber revolvers, and we had a submachine gun for each vehicle. When we stopped for chow, one guy would stay with each vehicle while the other guy ate. We would go down through Idaho. From there, we cut down into Utah and to Fort Douglas in Salt Lake City. From here to there was something like 707 miles. We tried to make the run all at once at first, all the way to Los Alamos. But we decided that was not the way to do it. So Los Alamos came to Fort Douglas to meet us. The Los Alamos crew would arrive a day ahead of us so they could get their rest. We switched vehicles, unloading our containers into their vehicles. It was the dullest thing in the world. It was the most routine deal I have ever run across in my life.
Walter O. Simon. I don't know how much plutonium we shipped. We were strictly forbidden to keep notes or diaries.
Cyril S. Smith, metallurgist. The plutonium we metallurgists received was actually a fluoride, a dry powder. It came to Los Alamos from Hanford as a kind of syrupy nitrate, which was treated by the chemists in a series of ingenious purification processes. The powder was kind of a pinkish color, a pale pink.
Oswald H. Graeger. They converted it into plutonium metal and made the parts for a weapon.
Paul Numeroff. Late one evening, my concentration was interrupted by the sound of hurried footsteps. This had to be investigated. Who was running, and why? Had there been an accident with the radioactivity scattered all around? Had there been a chemical explosion? Was there a fire in one of the laboratories in the building? 1,000 thoughts raced through my head. I saw someone walking in the hallway and asked him if there was a problem. No problem, he said. They've just completed the plutonium reduction. A small group of men were looking at 2 metal hemispheres. If placed together, they would have been about the size of a large grapefruit. As it was, they were just 2 gray-black pieces of metal, which were not of this world. They were man-made. In a few more days, these 2 pieces of metal would destroy the city of Nagasaki, Japan. I couldn't help but contrast these 2 ominous pieces of metal with what I had seen a year before, when the first tiny piece of metallic plutonium had been produced. It was the size of a very, very small pea, and it sat in an inch-long glass test tube. Now this.
Leona H. Woods. Plutonium is a very dense metal. When you hold a lump of it in your hand, it feels warm, like a live rabbit.
John A. Wheeler. People at Los Alamos gave me a piece to hold. The marvelous thing about it was the temperature of it. Here, day in, day out, producing enough heat to keep itself quite warm. Not for 10 years, not for 100 years, but for thousands of years. It gives you an immediate sense of energy capacity.
Part 4. Readying the Bomb, 1944 to 1945. By the fall of 1944, progress on the atomic bombs had advanced to the point where the leaders of the Manhattan Project were ready to think about how they would deliver the still-on-the-drawing-board weapons to targets in Europe and the Pacific. Much like the rest of the project to date, the actual use of the atomic bomb necessitated creating an all-new elite military unit with specially modified planes and training it in never-before-imagined tactics that would allow the crews to survive the largest explosion ever. Boeing's bomber. Getting the Fat Man and Little Boy bombs to their target safely proved its own enormous effort, one that ultimately relied upon a military advance even more expensive than the Manhattan Project itself. The B-29 Super Fortress was a giant. It weighed around 140,000 pounds fully loaded, contained 55,000 parts and 600,000 rivets, had a tail as tall as a 3-story building, and its wingspan of 141 feet was longer than the entire first flight by the Wright brothers. It was the Air Force's most advanced bomber. and with a development cost of $3.7 billion, the most expensive weapons system of the war. The B-29 was the weapon, planners hoped, that would knock Japan out of the war. Its long range would allow the U.S. to bomb the homeland directly from bases on the Asian mainland and from Pacific Islands, captured at great bloody cost by the Marines. Time felt short. Germany had been under air assault by British and American bombs for nearly 4 years before Japan would suffer its first sustained raids, and now the Air Force felt enormous pressure to deliver devastating blows quickly.
Robert M. Robbins, ex-B-29 test pilot, Boeing Company. In late 1938, Boeing had started thinking about a super bomber, an airplane for which, at that time, there was no established military requirement and no money. Also an airplane which no one knew how to build. The Army talked about an airplane with a 5,000-mile range capable of hitting an enemy aircraft carrier when it was still at least 2 days offshore. The B-17 could strike a carrier that was only 1 day out, too close for comfort. By August 1939, there finally was a super bomber configuration that Boeing could be proud to propose to the Air Corps. It was called the Model 341. It would later grow into the Model 345 and eventually become the B-29. Support for a super bomber spread rapidly. On 5 February 1940, Boeing was one of several aircraft manufacturers to receive from the Army an invitation to bid on a high-altitude, high-speed bombardment airplane with a requirement for a 5,333-mile range with a 2,000-pound bomb load. A month later, Boeing proposed the Model 341 with a gross weight of 85,000 pounds to meet the requirement.
Colonel Paul W. Tibbets. Although designed as a replacement for the B-17 and built by the same company, it was much more than an overgrown version of the Fortress. It contained many innovations, including a fire control system that would permit mounted guns outside the airplane to be fired by a gunner who had no manual contact with the weapons. As a result, one man could control more than one of the 5 guns.
William E. Shine, instructor, Base Communication and Radar School, Smoky Hill Army Air Base, Kansas. The B-29 airplane was designed around a radar set, the AN/APQ-13. In all other airplanes, radar was an add-on modification. But on the B-29, both bombing and navigation were performed using radar.
Colonel Paul W. Tibbets. The B-29 was also pressurized, enabling the crew to get to the target in shirt-sleeve environment, reducing the fatigue on long missions. For me, it meant that I could puff on my pipe during the flight instead of having to wear an oxygen mask at high altitudes. In addition to carrying more and larger bombs, the B-29 could fly higher, faster, and farther than the B-17. These qualities were urgently needed if we were to wage a devastating aerial war against Japan.
Robert M. Robbins. 2 of the very tough choices they made were to put the B-29 into production even before the engineering was completed, and to commit them to combat before developmental testing could get them more fully debugged.
General Henry Hap Arnold, Chief, Army Air Forces. It was so large and complicated that it required about 10,000 drawings before it was possible to put it into production.
Major General Curtis LeMay, Chief, Strategic Air Forces, Pacific. Hap took the chances, cut the corners, and ordered this unique airplane into production before the prototype was even completed. Arnold took a calculated risk of unprecedented proportions. Everything could have exploded in his face.
Colonel Paul W. Tibbets. In Washington, where I reported for assignment to the B-29 program, I found that the big bomber project was a shambles. I don't know whether we'll ever have a B-29, General Eugene Eubank told me. Only the week before, on February 18, 1943, Boeing's chief test pilot, Eddie Allen, and 10 top technicians had been killed at Seattle in the crash of a B-29 in a test flight.
Major General Curtis LeMay. It was a test program disaster of unparalleled proportions.
Robert M. Robbins. Shortly after Eddie's accident, Brigadier General K.B. Wolfe was directed